Good day, everyone. It's been a while since I did one of these math videos, but I have a perfectly good reason for it, but I figured you won't be interested in what those reasons are. And welcome back to this channel. And I'm going to be doing 100 integrals like last year, but more difficult integrals. And some of them aren't even integrals, so what the hell, right? So, without further ado, let's do it. Our first integral is e to the arc sine of x. What can we do here? Well, first we can substitute arc sine x as theta. Uh, this would mean x equals sine theta. Uh, Getting the derivative on both sides, dx is equals to cosine theta d theta. And there we go. Substituting it, we get the integral of e to the theta, and then for dx, it turns into cosine theta d theta, so we turn dx into cosine theta d theta. From here, we can use integration by parts. And again, the setup for integration by parts is di. What do we put in d and what we put in I is up to our discretion. For here, it doesn't matter where you put it. I'm just going to put e to the e theta and cosine theta here, like that. The derivative of e theta is itself all the way down, so not much is going on there. For cosine theta, this is going to be sine theta here, and then negative cosine theta here. And you can see that it checks out. Then the diagonals, and then since the last one is a repeat of the first one, we put the integral like this right here. So first answer is e to the theta sine theta minus e to the theta and the negative cosine, so it's going to be a plus e to the theta cosine theta. And then plus minus, so it's negative, then integral of e theta cosine theta. Let this be I, and let this be another I. So we get I equals e to the theta, and then parentheses sine theta plus cosine theta for ease, so it's easier to write. Then minus I. I can we can add I to both sides. So on the left hand side we get 2I. On the right hand side we get this. So let me rewrite it again. There we go. So that means I is 1 half E theta sine theta plus cosine theta. Now what is theta? Remember, sine theta is x. So we can use a triangle, and theta is the angle since it is inside sine. And since it is inside sine, sine theta is x. So that means opposite over hypotenuse is x over 1. So x and 1 right here. X over 1 is x, same thing. And using the Pythagorean theorem, we can find the length of the third side, which is going to be 1 minus x squared. Yes. So this means cosine theta is adjacent over hypotenuse. So that's going to be 1 minus x squared. The final answer then is, this is going to be arcsine. So 1 half e to the arcsine x. And then sine theta is x. Cosine theta is 1 minus x squared. And don't forget plus c. This is our answer. For the second question, e to the x sine x cosine x. It seems overwhelming at first because there's three transcendental functions here. But remember that sine 2x is 2 sine x cosine x. Cosine x. So if we divide 2 on both sides, we get sine x cosine x. So let's do just that. First, e to the x, and then sine x cosine x becomes sine 2x over 2. So we put the over 2 as 1 half here, and sine 2x over here. Now, this is another case of integration by parts. So let's do the di setup here. This time, I'm going to put sine 2x on the d, and then 1 half e to the x on the I. We know that the integral of this is also 1 half e to the x. That's very obvious so far. And for the derivative of the sine 2x, this is going to be cosine, then the inside, then the derivative of the inside, which is going to be 2. And similar for this one is negative 4 sine 2x. Again, we do the diagonals thing. And then let's say this is I, so we don't forget. This is equal to 1 half e to the x sine 2x, then minus 2 times 1 half is just 1. So we put 1 times e to the x cosine 2x. And then here is where it gets a bit tricky. So minus, then 4. We put 4 outside. And then 1 half e to the x sine 2x on the inside. This is also I. So let's put everything on one layer. So I equals 1 half e to the x. Actually, just put e to the x outside. So e to the x. And then 1 half sine 2x uh, minus cosine 2x. Like that. Minus 4i. We can add 4i on both sides. So we get on the left-hand side 5i. On the right-hand side, we get e to the 2x. Then 1 half sine 2x minus cosine 2x. I'm just checking. So I, dividing both sides by 5, gives us 1/5 and e to the 2x, and then 1 half sine 2x minus cosine 2x. You can expand it if you want, but I'm going to leave it at there. And the answer is, don't forget plus c. That's the answer. Question number 3. Ah, e to the e to the e to the e to the x, then like that, cascading downwards. It's like a triangle, essentially. So, what can we do here? Well, we can sequentially do u equals e to the x and all that, but let's skip a few steps. Let's just say e to the e to the e to the x. There we go. And then the yes. So the derivative of this is going to be, well, derivative of the outside, which is e to the thing. So e to the e to the e to the e to the x. Then derivative of the inside. Is that correct? Yeah. Derivative of the inside, which is going to be, well, e to the e to the e to the x. And then derivative of inside again, e to the e to the x. Derivative of the inside again is e to the x dx. This is going to be du. This is going to be u. No, sorry. This is going to be e to the u, then integral. So that's going to be the substitution. And this is very simple, really. If you don't know this, then I don't know. This is just e to the u. Then, since u is e to the e to the e to the x, let's substitute that back in. Let me check if this is right. Yes. So the answer is e to the 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 x plus c. Don't forget plus c, everybody. That's question number 3. Let's move on to question number 4. X times e to the sine x dx. So what do we do here? Let's just use integration by parts again. So let's put it here. Here, yes. Di. Okay, so first we get x here because if we go down derivative path, we eventually reach 0, which is very good. So that's what we want. So what do we put in I? We put in I e to the x sine x. And that's where we start getting into trouble because what is the integral of e to the x sine x? For that, we have to use integration by parts again. So we need to find integral e to the x sine x as a side quest. So how do we use that again? We use integration by parts. So we use integration by parts at least 2 times here. So e to the x here, sine x here. Derivative is just e to the x down, and then integral of sine x is negative cosine x, and then for that is negative sine x. Then here, diagonals, so we get negative e to the x cosine x plus e to the x sine x. And then for here, we get minus e integral of e to the x sine x dx, which is the original I. Let's call this I. So minus I. So we put I on the other side, we get 2I, and then rearranging this and factorizing e to the x outside, we get e to the x times sine x minus cosine x. That's much easier to read because we're going to have to solve that later again. You'll see. And then dividing both sides by 2, we get 1/2 of that. All right. So that's one done. 1/2 e to the x, then sine x minus cosine x. The next vital question is what is the integral of that? And what do we do again? We have to use the DI method for a third time just to solve this. So now our integral is 1/2 e to the x sine x minus cosine x. I told you this was going to be tricky. So let's set up the DI setup. Uh, plus minus plus. Here, 1/2 e to the x on the d part. No, you know what? Actually, let's not do that, and let's put it on the integral part since it is easier. Then on the d part, we put sine x minus cosine x. Derivative of that is cosine x plus sine x. Derivative of that is negative sine x plus cosine x. Do this thing again. We get 1/2 e to the x, then sine x minus cosine x minus 1/2 e to the x, then cosine x plus sine x. And then this is just minus I. So I equals this. So 2I equals 1/2 e to the x. Then combining this two, so sine x minus cosine x plus minus ulit minus sine x. Canceling sine x, we get like minus 2 cosine x. All right. So dividing both sides by 2, we get I equals dividing both sides by 2, remove this, so we get negative 1/2 e to the x cosine x. So that's the third one. That's still not the answer, by the way. So negative 1/2 e to the x cosine x. Let me check. Yes. So now we have completed the table, so we can just do the diagonals. So the answer is going to be, let me just set it up here. First is 1/2 x e to the x, and then sine x minus cosine x. Second part, second part is minus minus, so it's plus, then 1/2 e to the x cosine x plus c. And that is going to be the answer. So it's a lot of the integration by parts, but using the DI method is much easier than using the others method. Oh, so uh, here we have a Taylor series or a Maclaurin series or whatever you call it as sum. So how are we going to solve this? Well, we're going to be using just the power rule. You can turn this into a trigonometric equivalent, and from there you can integrate very easily. But we can use the just the power rule in order to find this. So let's set up the sum. All right. So since it is dx, let's try to find where x is here. and it is only an exponent, so x to the 2n. So the only thing we have to do is the power rule. So negative 1, this is negative 1 over 2n factorial. These are just constants. So we can push them to the side. And then x to the 2n, that's a variable x. So we get 2n plus 1 over 2n plus 1 as this is the power rule. So let's just remove the integral sign here. There we go. So let's simplify this a bit. 2n plus 1 times 2n factorial, that is just 2n plus 1 factorial. Or, yes. And then negative 1 to the n works like that. And then x to the 2n plus 1. Yeah. Sure. And plus c. Now, don't forget plus c. All right. And if you notice, the original one is cosine x, and this new one is sine x. So that is pretty cool. Next, 2 over 1 plus e to the x dx. I think we have a similar problem in the first 100 integrals video, but we can multiply both the numerator and the denominator by e to the negative x. So we get that. 2 e to the negative x over e to the negative x plus 1. Why did we do this? Because in the original, we can't really do anything. We can't use integration by substitution or whatever. Maybe you can use parts, but I don't know if that's possible. When in here, we have e to the x, we have e to the negative x on both the numerator and the denominator, and only a constant that's separated. So that means we can use integration by substitution. So let u be e to the negative x plus 1. Its derivative is negative e to the negative x dx. And we have e to the negative x dx. Just the negative is missing, so we can put that right here. There we go. So, put negative here, then 2, then du over u. Du over u plus ln of u. So, negative 2 ln of u. Let's put e to the negative x plus 1 back. So negative 2 ln of e to the negative x plus 1. And don't forget plus c, and that is our answer. Nice. Question number 7. X to the negative 2 over e to the 1 over x plus 4. Now, what can we do? Maybe we can use 1 over x as u integration by substitution. And a vital part in problem solving is to use every conceivable solution you can think of. Don't be afraid of being wrong because maybe you think that's wrong and it's actually right. So in here, the derivative of 1 over x is negative 1 over x squared or negative x to the negative 2. Then let's put the x here and du here. We have x to the negative 2 on the numerator. So this seems right. This seems just right, so we can do this. Okay. So x to the numerator becomes negative du. The denominator becomes negative e to the u. Hold on. Yeah, hold on. Plus 4. Okay. Now, how do we solve this? From earlier, let's go back earlier. We had a similar situation. So we multiplied both the numerator and the denominator by the inverse of e to the x. We're in this similar situation, so we can do that trick again. So, negative e to the negative u du over 1 plus 4e to the negative u. Let 1 plus 4e to the negative u equals, let's say, v. And then negative 4e to the negative u du equals dv. Let's just divide both sides by 4 so it's cleaner to look at. And there we go. Let's put 1/4 on the outside. Then dv on the numerator, and then v on the denominator. And from there, we can We can use natural logarithm, so ln of v. And v is 1 plus 4 e to the negative u. So 1 over 4 ln of 1 plus 4 e to the negative. U is 1 over x. So let's put that. 1 over 4 ln of 1 plus 4 e to the negative 1 over x plus c. That is the answer. All right. Next question. All right. E to the x minus 1 over x e to the x plus 1. Hmm. If this was plus, would things be easier? I don't know. Maybe it's impossible with just plus. But with minus, how can we solve this? Let's try the trick we used for two questions now. Let's multiply both the numerator and the denominator by e to the negative x. So the top becomes 1 minus e to the negative x. Bottom becomes x plus e to the negative x. And look at this. I think it's possible now. If we let u be equal to x plus e to the negative x, du then becomes 1 minus e to the negative x dx. Exactly what we have in the numerator. So we can put du on the numerator now. And then on the bottom is just u. So we get ln of u. And u is just ln x plus e to the negative x. So we can put that there. And we don't forget plus c. And that's the answer. Okay. Question number 9. X to the x squared over ln x plus 1. Doesn't seem solvable. Well, let's try this. Since there's a plus 1 here, we can express this as x times x to the x squared over ln x. That ln x reminds me of e to the ln x equals x. And this is x here, so we can put e to the ln x and then x squared over ln x. In situations like this, we can multiply the powers. So multiplying the powers, we can cancel the ln x out, leaving us with e to the x squared. So this is actually just e to the x squared. So put that here. And we can use integration by substitution here again. So x squared equals u, and then 2x dx equals du. We have x here and dx, so we just divide both sides by 2 to get 1 half. So 1 half and then du, then e to the u. Solving that, we get e to the u, obviously. And substituting x squared back, we get 1 half e to the x squared plus c. Nice. Number 10, secant x dx, but we have to use the Weierstrass substitution. We know how to integrate secant x. You probably even memorized it. But have we considered using another method? The Weierstrass substitution is just this. Tan of x over 2 equals t. That may sound a bit, sounds a bit weird. Why are we doing this? But here's the secret sauce. Let's have the let's take the arctangent of both sides. So we get x over 2 equals arctangent of t over t, just t. All right. So x equals 2 arctangent t. So that means dx is 2 over 1 plus t squared. And if you take the identities of this, you will find that sine x is 2t over 1 plus t squared, and cosine x is 1 minus t squared over 1 plus t squared. For proof, you can find other videos for this. I don't have time for that, but let's use this substitution in order to solve this. All right. So secant x is just 1 over cosine x, and then we can have dx here. Okay. So dx again is that. So 2 over 1 plus t squared over cosine x is this, so 1 minus t squared over 1 plus t squared. We can cancel this denominator on both the numerator and the denominator. So we get integral of 2 dx over 1 minus t squared. It's not the arctangent. It is, you can use hyperbolic, but I'm not going to. Instead, what I'm going to do is split this into two fractions. We're going to be using, oh, sorry. We're going to be using partial fractions for this one. All right. So let's remove the two figures. So we know that the numerator is 2. It has to be 2. So let's uh let's try finding a and b. We can use the cover up method, so let's try that. The cover up method says let's turn this into its root. So 1 minus t and then 1 plus t. And then the numerator has to be 2. How about that? There we go. The cover up method states that we have to, number one, find the root of 1. So 1 minus t, t equals 1, right? And for this one, we have to make the fraction such that the root does not appear on it. If we have to remove 1 minus t, so we get 2 over 1 plus t instead. And then t equals 1 on here, so 2 over 1 plus 1, so that's just going to be 1. So that is the value of a. And for the other one is t is negative 1. So b is 2 over 1 minus t, since the root is 1 plus t. So let's insert that. So 1 minus negative 1. That's going to be 2, sorry, 2 here. So it's going to be, sorry, 1, right? So it's just both 1. So 1 over 1 minus t plus 1 over 1 plus t dt. And this is very easy. It's just ln. Oh, for here we have to use the reverse chain rule. So negative ln of 1 minus t. You have to pay attention to what goes on in antiderivative, right? The chain rule says that we have to make it negative. Just a little precaution. And then here we can add ln of 1 plus t. No chain rule shenanigans going there since it's just positive. All right. Since t earlier is tan x over 2, we can substitute back. So the answer is negative ln of 1 minus tangent of x over 2 plus ln of 1 plus tangent x over 2. You can rearrange all that stuff, but I'm going to leave it there. Plus c, that's the answer. In Weierstrass substitution form. I bet you've already seen the other forms, but this is just one of them. So there you go. Question 11 is sine cubed x cosine to the seventh x dx, the integral of that. So the exponents for sine and cosine are odd, so this we can solve it using the following. So you can either turn the sine into 1 minus cosine squared or the cosine into 1 minus sine squared. In this case, I'm going to separate the sign. So this is going to be sine squared x, then cosine to the 7x sine x dx. Sine squared x can be 1 minus cosine squared x. This is the Pythagorean identity. And cosine to the 7x, this x should be down here. And then sine x dx. Now we know that the derivative of cosine x is negative sine x. So we can substitute for that. Now, the problem here is that this is only sine x and not negative sine x. So we can just multiply both sides by negative 1. So like that. Negative 1, then multiply again by negative 1. That's what I mean. Then, yeah, there we go. So we can substitute negative sine x dx for du. And for everything that has cosine in here, we can substitute with u. So 1 minus u squared times u to the 7. Let's put D closer. Okay, there we go. For simplicity, let's flip the 1 minus u squared because we have a negative outside. So we get u squared minus 1 times u to the 7 du. For even further simplicity, let's distribute u to the 7 to both terms in the parentheses. So we get u squared times u7 is u9 minus u7 du. This is very basic. So the integral of u to the 9 is u to the 10 over 10 minus u to the 8 over 8. And then substituting back into the cosine x world, we get cosine to the power 10x over 10 minus cosine to the power 8x over 8. And don't forget the c. Oh, and by the way, I forgot the c in the previous question. Oh, no, I did not. Sorry. Uh, so never forget the term c because we need constants for indefinite integrals. For definite integrals, we can forget about it, but for indefinite, we don't. Here, sine to the 5x cosine to the 6x dx. Much like the previous one, we have an odd term here, sine to the 5x. Cosine is not also, we can't do anything with cosine for now. It's easier to do things with sine. So here's what we're going to do. First, make sure that sine is even. So sine to the 4x, then cosine to the 6x. Then we have an extra sine x here, dx. So we turn this into something that cosine, and we know sine squared x equals 1 minus cosine squared x. And this is sine to the fourth x. Sine to the fourth x is like sine squared x squared, so something like that. And then we can square this side as well, so that those two are equal. And this is what we can replace here. So sine to the 4x becomes 1 minus cosine squared x squared, and then cosine to the 6x times sine x dx. Again, we can substitute cosine x as u, and then negative sine x dx is du. We can insert the negative anyway, so we do not worry about that. So negative, and then this becomes du. This becomes 1 minus u squared, and then squared, times u to the 6. All right. Let's expand this. So this is going to be 1 minus, check my notes. Yeah. 1 minus 2u squared plus u to the 4 times u to the 6 du. Next step, we gotta distribute u to the 6 to all the terms in the parentheses. So it becomes u to the 6 minus 2u to the 8 plus u to the 10 du. After that, we just integrate using the power rule, which is very basic. Oh, so u to the 6 becomes u to the 7 over 7. 2u to the 8 becomes 2u to the 9 over 9. And u to the 10, of course, becomes u to the 11 over 11. There's still the negative sign outside, so let's distribute that. Negative uh, u to the 7. Let's bring back the cosine x. So this is going to be cosine to the power 7x over 7. Minus minus is plus 2 cosine to the power 9x over 9 plus, minus cosine x, cosine to the 11 x over 11. And then don't forget plus c. There we go. Next question. Sine to the 4x, cosine to the 6x. The problem now here is that both of them are even, and we can't really do the previous things that we did because it required either one of them to be odd. So how are we supposed to do this? Let's do this. Sine to the 4x. Then let's Let's have a cosine to the 4x on one side and cosine squared x on the other. There. This is sine x cosine x to the power 4. And cosine squared, you can put that on the side. Yeah. So, yeah. After that, we can turn this, since we know sine 2x equals 2 sine x cosine x, we can divide both sides by 2. So we can remove this and sine x cosine x remains. This is what we have. So 1 half sine 2x is in the inside now to the power of 4. Now cosine squared x is a bit trickier, but it is also, we can also use trigonometric substitution here. So we know cosine 2x is cosine squared x minus sine squared x. We want cosine squared x, and we don't want this. How can we remove this? So what would happen if we subtract cosine squared x here? Ignoring the cosine squared x for now. This becomes negative 1. This becomes negative 1, right? Because sine squared x plus cosine squared x is 1. And the negative of both means that the answer is now 1. But that would also change the entire thing. So we need to add back cosine squared x. Because cosine squared x minus cosine squared x, that would equal 0. Therefore, we didn't really change anything, right? But we can equate this to, we can add this to, so that would be 2 cosine squared x. This would be minus 1. And it would still equal cosine 2x because the only thing we did is add 0 creatively, might I add. We need to isolate cosine squared x. So we just add 1 to both sides. We get 1 plus cosine 2x, then 2 cosine squared x. Divide both sides by 2. We get that cosine squared x is 1 plus cosine 2x over 2. Yeah, there we go. So we add back, multiply that back in 1 plus cosine 2x over dx. Hmm. There's 1 half here to the power of 4. There's 1 half here to the power of 1. We multiply all of them together and put them outside, we get 1 over 32, which is 2 to the power 5, right? 2 to the power negative 5, this entire thing is. So, next, we have sine to the 4, 2x here, and we have 1 plus cosine 2x here. Let's multiply sine to the 4x to both terms in this. Just distribute them. So, multiply by 1, we get sine to the power 4 2x. Multiply by cosine 2x, we get plus sine to the power 4 2x cosine 2x dx. This is easier. This is a bit harder. So let's integrate them separately. Let's call this I1. Let's call this I2. All right. Let's ignore the 1 over 32 for now. That will come in handy later. Let's solve I2 because that seems easier. So I2 is sine to the 4 2x cosine 2x dx. So let's put that here. There we go. Let cosine 2x be equal to u. Let's not use u. Yeah, let's just use u. We haven't used substitution yet. So the derivative of cosine 2x is negative 2 sine 2x dx. Don't forget dx. And then du. So we have, oh no, wait, hold on. That's wrong. Sine. This is supposed to be sine 2x because sine is here. I made a mistake. Sorry. So sine, it's sine 2x equal u. And then cosine, yes, and we need to multiply it by the derivative of the inside, which is going to be 2. That's just the chain rule. There we go. So cosine 2x dx we have. The 2 we can divide. So we will put 1 half here. Then integral of u to the 4 And then cosine 2x dx becomes du. Since we divided 2 already. All right. This is easy. 1 half times u to the 5 over 5. Or u to the 5 over 10. Substituting sine 2x back in, we get sine to the 5. Hold up. Oh no, yeah, it's correct. Sine to sorry, sine to 5 2x over 10. Something you gotta think about is that these notes were written like like a year ago or something. So I'm not too familiar with it, but yeah. So that's correct. That's the first part. The next part is going to be I1, which is going to be a bit more difficult, but not that difficult. Let me explain why. So this is sine to the 4 to x, right? That is the question, dx. We can integrate that immediately. What we can do is transform it back into a lesser power, like this. But instead of cosine, it's going to be sine that we're going to have. And there's actually a really good, uh, explanation, yeah, solution for sine squared x. So here we go. We know that cosine squared x is 1 minus sine squared x, right? So what if we did this? Sine squared x minus 1. This becomes negative of the entire thing here. So negative 1 minus cosine 2x over 2. We add 1 to both sides, we get that sine squared x equals, well, 1 plus 1 minus 1 half is just 1 half. So we can retain that here, minus cosine squared x. And this is just a minus version of this. So we're going to be using that. So this is going to be, sorry, uh, 1 minus cosine squared 4x over 2, right? 2x. Hang on. Sine. Oh no, wait, hold on. This is wrong. This is just cosine, but the outside is squared. Yeah, here we go. It's a bit more complicated. So that's wrong. And then let's expand this so we can get to know it better. 1 minus 2, hold on, cosine 4x plus cosine squared 4x over 4 dx. All right, next. We still have a cosine squared here, and that is a bit problematic. So we need to have another reduction here, power reduction. So write this down, and then power reduce it. So we get 1, since it's cosine now, so we can have plus cosine, so excited, cosine to the 8, cosine 8x, sorry, over 2, all over 4 dx. Let's have them in separate chambers. So we get 1 minus 2 cosine 4x over 4 plus 1 plus cosine, got it, cool, cosine 8x over 8, I think. Yeah. 1/4 becomes 1/4 x. This thing becomes, since 2 over 4 becomes 1 half, so minus 1 half. Cosine 4x, the integral of that is sine 4x over 4. This becomes 1 over 8 x. And this becomes 1 over 8 times sine 8x over 8. There we go. Combine the 1/4 and 1/8, we have 3/8 x. We can combine these two, but that's okay. We're just going to have to simplify them. So this becomes sine to the 4x over 8. This becomes sine, after 8, sine 8x over 64. And this is I1. Let's combine I1 and I2 like this. So the original integral, which we're going to call big I, is 1 over 32 I1 plus I2. I1 is this, so 3 over 8 x minus sine to the sine 4x over 8 plus sine 8x over 64. I2 is this. Hold on, is it correct? Yeah, sine to the 5 2x over 10. Yeah, sine to the 5 2x over 10. Let's distribute 1 over 32. 32 times 8 is 256, so it's 3 over 256x minus sine 4x over 256 plus 32 times 64 should be 2048. Sine 8x over 2048. It's a good game. And sine to the 5 to x over 320 plus c. That should be the answer. Number 14. X to the 2025 current year plus x squared to the power of 1011 dx. So what is going to be our solution here? Well, the common for both terms in the parentheses is x squared. So let's bring that outside like this. So x squared and then x to the 2023 plus 1. And then on the outside to the power 111. Yes. Bring x squared outside by multiplying it to 1011. We get x to the 2022. Then x to the 2023 plus 1 to the power 1011. Let x to the 2023 be equals to u. Then 2023 x to the 2022 dx equals du. Divide both sides by 2023. So this gets removed from that side. And we have x to the 2022 dx on that one. So we can replace it with du over 2023. Then 20 x to the 2023 uh, becomes u. But actually, we can include the plus 1 here. Oh, we can include the plus 1 here because the derivative of 1 is just, it's just 0. So u to the 1011. And the integral of that is u to the 1012 over 1012 times 1 over 2023. U again is x to the 2023. So, and let me check the denominator. It is 2,047,276. On the top is x to the 2023 plus 1 to the power of 1012. And don't forget plus. Question number 15. 1 over square root of e to the 2x minus 1. I want e to the x as substitution, but there is no e to the x in the numerator or close to the x. The golden rule is if there is no, if we need an e to the x in the numerator, we just add one or we just multiply an e to the x in the numerator and the denominator, so nothing changed. So we get e to the x here and e to the x down here, right? What good does that do? Because it now sounds like we just, we just multiplied both the numerator and denominator by e to the x. We just added another problem in the denominator. Not quite. Look at this. E to the x, let that be u. And then e to the x dx du, right? So this on the numerator becomes du. On the denominator, e to the x becomes u, and then square root of u squared minus 1. What does that look like? That looks like, to me, arc secant. So this is going to be our arc secant u. And u is just e to the x. So the answer is arc secant e to the x plus c. You can even check if that is arc secant, but that is the derivative on arc secant. Arc secant is rarely used. As I see, it's only arc sine, arc cosine, and arc tangent. Never arc secant. It's pretty good. Next, x e to the x over 1 plus x quantity squared. What do we do here? Hmm. Let's try using integration by parts, the DI method. DI. What do we put in D? What do we put in I? You can test. For now, I'll say that I can put x e to the x here and 1 over 1 plus x quantity squared here. What is the derivative of x e to the x? Well, that's going to be x e to the x plus e to the x. This is just the product rule. We can simplify that to x plus 1 e to the x. All right. Next, what is the integral of 1 over 1 plus x squared? You can use chain rule. You can use integration by substitution, but I'm just going to say it. It's negative 1 over 1 plus x. It's like 1 over x, but there's an extra plus 1, Now, this we can multiply. So let's put that in. Negative x e to the x over 1 plus x. This we need to integrate. So minus minus is plus. Integral of x plus 1 e to the x over 1 plus x. This is what I love about these kinds of questions. Look at this. We can cancel these two terms out because they're essentially the same. What does this leave us? E to the x. And the integral of e to the x is, so unsurprisingly, e to the x. So let's write it down. There we go. And we had plus c for good measure, and that's going to be our answer. Next, dx over x to the 6 over 5 plus x to the 4 over 5. Hmm. There is a term x to the a negative 4, x to the 4 over 5 in the denominator. That's the common term. So let's isolate that. So x to the 4 over 5, then x to the 2 over 5 plus 1. All right. What we can do from here? Let's put the x to the 4 over 5 numerator. Let's see if that leads us to something useful. Over x to the 2 over 5 plus 1. At first glance, this doesn't look anything new. X to the negative 4 over 5 doesn't help because the derivative of x to the 2 over 5 is x to the negative 3 over 5. So what we can do? Let's look at it this way. Numerator remains the same. Denominator, I will do this. So x to the 1 over 5 squared plus 1. Does that look like something? The derivative of x to the 1 over 5 is x to the negative 4 over 5. So we can do this. X to the 1 over 5 dx. U. Sorry. Just u. Sorry. U. Derivative of this is 1/5 x to the negative 4 over 5. That's what we have in the numerator. And dx du. Multiply both sides by 5. So we can cancel this out. We get the numerator, which I should probably remove this. The numerator is 5 du. The denominator is, well, x to the 1 over 5 is u squared plus 1. This is just the arctangent. So 5 arctangent u. And u is x to the 1 over 5. So let's replace that. There you go. And we have plus c. For good measure. There we go. Question number 8. 2x cubed minus 7x squared plus 8x minus 3 over 2x. This looks threatening. Hmm. What can we do? Are we even sure that 2x minus 3 is a root of the one above? It looks like it. Because it's 2 and negative 3. Is it? Maybe it's just 2x minus 1 and then x is 3 or something like that. We don't know. What can we use? First, with these types of questions, we first check for the roots. So let's sweep the easy ones. X equals 0 is not a root because all these terms, this would all become 0. But what would remain is negative 3. So x equals 0 is not a root. How about x equals 1? That would be easy because we only have to add the coefficients. So 2 minus 7 plus 8 minus 3. 2 plus 8, 10. 7 minus, negative 7 minus 3 is negative 10. So 10 minus 10 is 0. So x equals 1 is a root. How can we divide that further? Let's use the synthetic method. So let's put the coefficients of the cubic here. 2, negative 7, 8, negative 3. Let's put our one root, 1. Bring, let's make this thing bigger. Okay, like that. So what we do is bring this down, multiply 1 by this. So 1 times 2 is 2. Add here. Now, we need to add negative 7 plus 2. So that's negative 5. Multiplied by 1, we get negative 5. 8 minus 5 is 3. Multiplied by 1 becomes 3. And then negative 3 plus 3 is 0. So it is a root, number 1. And this is our remaining terms. So x minus 1 and 2x minus 5 plus 2x squared minus 5x plus 3. We can also check for roots, or we can guess. Let's see. We want 2 and negative 3 here, so let's check for that. And then maybe 1 and 1, since those are the factors. So we need negative 1 here because this is positive 3, right? So this is negative 2. This is negative 3. Add that together, it's negative 5. So this is indeed our solution. So this is x minus 1 squared, since there are now 2, then 2x minus 3. Bring it down. Our integral is now x minus 1 squared 2x minus 3 over 2x minus 3. We just cancel this and this. We get x minus 1 squared dx. You can expand it, or you can just apply the power rule here. X minus 1 equals u. You can use the substitution, but I'm just going to hurry up. So you can do this. There we go. There we go. That's the integral of that. And let's see. Hey, we can do that because the derivative of the inside is just 1. So there's no chain rule or integration by substitution shenanigans. So that is the answer. You have to be careful about it though, because uh, the chain rule can be a bit tricky if you don't know how to work around it. Here, e to the cube root of x dx. Now, you think to yourself, maybe this is one of them, e to the x squared, where it's unsolvable. Let's try solving it. So cube root of x, let that be u. Cubing both sides, we get x equals u cubed. Find differentiating both sides, we get dx equals 3u squared du. So dx becomes 3 u squared du. E to the cube root x becomes e to the u. Let's put du on this side. So there you go. This is just a simple integration by parts. 3 squared here, here. Nice. Derivative of this, 6u. Derivative of this, 6. Derivative 0, we stop. And e to the u all the way down. Then we find the diagonal sums. We get the diagonal product, sorry. 3u squared du minus 6u eu plus 6eu plus c. Not plus c. Let's remove that for now. We will add that later. U is cube root x, so u squared is 2/3. E to the, we can have x. E to the x 1/3, but I'll just put this here. Minus 6 to the 6x to the 1/3. E to the cube root x. You can use cube root x or x to the 1/3, whatever you want, but I'm just going to use this for simplicity's sake. When add plus c, that's our answer. Question, yeah. Question number 20. Dx over x plus 2 times 2x plus 5, 2x minus 5, sorry. Alright, so we have to use partial fractions here. Let me show you how to do this. So on top, we put a over x plus 2, and then usually we add b, but let's add the derivative of this. Let it be 2b over 2x minus 5. Alright, you'll see why later. Let's use the cover-up method, or you can use the cover-up method in your own time, but I'm going to be using the long method. So here we go. Okay, so let's cross multiply this together. So a times 2x minus 5 plus 2b, then x plus 2 over the denominator. There we go. Now, let's gather up all the uh, let's gather up all the x terms, and let's gather up the constant terms. For the x terms, we have 2 times a, we have 2b times 1. That is equal to 0, since there's no x term. For the constant term, we have negative 5a, we have 4b, and that gives us 1. And you can use any method you want here. I will just cut to the chase. This video is gonna be long enough as it is, and I have a calculator. A equals negative 1/9, B equals 1/9. That is your A and B. So now what we can do. First, since these are just constants, we can put them outside. So A, we put that outside. So negative 1/9 times the integral of dx over x plus 2. Then the 1/9 we can also put outside, and 2 over 2x minus 5 inside. That's why I had 2 in here, because we can just take the thing that that we got, put it outside immediately, like that. All right. This one is just negative 1/9 ln of x plus 2. This is 1/9 ln of 2x minus 5, because we need the derivative of 2x minus 5 in the numerator. There we go. You can combine this together. You can, like this, 1/9 ln of 2x minus 5 over x plus 2. But any one of them is the answer. So that's the answer for question number 20. On to question number 21. 3x minus 1 all over x plus 1 times x squared minus 2x plus 1. You notice something here. This is just a perfect square trinomial. So let's do that. So this is just x minus 1 squared. Let's not forget the x. There we go. Now, in order to partial fractions this, we need to split it into three partial fractions: x plus 1, x minus 1, and x minus 1 quantity squared. This is going to be a, b, c. All right. So the derivative of x is just 1. We don't need to put any other coefficient in the numerator besides 1. So let's combine this into one mega fraction. Pardon the very curvy fraction bar. That's the best I can do. And let's be about no. Anyway, a x minus 1 quantity squared plus b times x plus 1 x minus 1 plus c x plus 1. All right. A x squared minus 2x plus 1 plus b times x squared minus 1 plus c x plus 1. Let me just there. And then the x. Okay, let's put the x squared term, the x term, and the constant term. X squared term, we have a, we have b. There's none in the original because the original is 3x minus 1. There's no square there, so we can put that. For the x term, we have negative 2 here, none here, and plus c. And that is 3. The original has 3. And the constant term, a minus b plus c. That's negative 1, since we have minus 1. Again, you can solve this, or I'm just going to use my calculator. A equals negative 1, b equals 1, c equals 1. So that's easy. So let's go back here. Let's copy this. This is why a computer is better. You know. There. But let's remove the A, the B, and the C, and let's replace it with negative 1, 1, 1. Here, this is just negative ln of x plus 1. This is just positive ln of x minus 1. And this is going to be negative 1 over x minus 1. Add plus c, and that's your answer. Question number 22. 4x squared minus 3x plus 2 all over 2x minus 3 times x squared plus 1. Okay. Hmm. How can we do this? Partial fractions again. So we partial fractions this. So 2x minus 3. Let's put 2a in up there. And for the next one, we have 2bx plus c over x squared plus 1. All right. How can I solve this? So let's put this into one mega fraction yet again. So 2x minus 3, then x squared plus 1, 2a times x squared plus 1 plus 2bx plus c multiplied by 2x minus 3. Let's fix the numerator there. So 2a, then x squared plus 1 plus 2b, 2x squared minus 3x. So yeah, we don't get confused about the x. Plus c, then 2x minus 3 over uh, this. All right, let's set up the x squared term, x term, and constant. Gather up the x squared term, so it's 2a plus 4b, and that's it. The x terms, we have negative 6b minus 3c. No, sorry, minus 2c. Hold on, let me check. Plus 2c, sorry, negative 3. This is going to be equal 4, since it is 4x squared minus 3x plus 2. Constant term, we have 2a minus 3c, which is going to be 2. The answer is going to be 1, a equals 1, b is 1 half, and c equals 0. So, yeah. So, let's separate them. 2 over 2x minus 3. Nice. Plus 1 half times 2x over x squared plus 1. And since c is 0, we don't have to bring that in. That is going to be our two integrals. This one becomes ln of 2x minus 3. This one becomes arctangent of x. Oh, no, sorry, not arctangent. Ln of x squared plus 1. Sorry. There we go. And we end up with a plus c, and that is going to be our answer. On to the next. Dx over 1 minus x squared. Partial fractions versus hyperbolic trig sum. So let's put partial fractions first, like we did earlier. And this is going to be a bit. Oh, hold on. So, partial fractions. 1 minus x squared is 1 over x and 1 minus x, 1 plus x. So we can do this. Nice. We can use the cover up method here. I'm just going to say that a is 1 half and b is also 1 half if you do the cover up method. So 1 half 1 minus x plus 1 half 1 plus x. This becomes negative 1 half ln of 1 minus x. This becomes positive 1 half ln of 1 plus x and plus c. Now for the other part, hyperbolic trig sum. The hmm, all right. This is yeah. So for hyperbolic trig sum, the property I want to exploit here is sec h theta. Let's not call it theta, that's phi plus tan h phi. You can also use trigonometry. I just want hyperbolic here. Squared both we get 1, which is similar to sine squared x plus cosine squared x plus 1. This time it's sec. So let tan tan phi, sorry, be equal to x. Sec squared phi equals dx or d phi. I am butchering that drawing. Anyway, uh, we replace dx with sec phi, sec squared phi d phi over 1 minus tan squared phi. Bottom becomes like this. So sec squared phi, then sec squared phi. I'm butchering that down. The phi. Cancel, cancel. This becomes an integral of the phi. And this becomes phi plus c. Phi is r tan x plus c, since tanh phi is x. Phi is our tanh, which is the inverse hyperbolic tanh. That's going to be the alternate answer. So you can ask, is the first result and the second result the same thing? Maybe not, because there's still c, an arbitrary constant, which may differ depending on either answer. So not necessarily the same, but similar is a good answer. Next, x cubed y plus y ln x dx. What do what do we do with y? Hmm. Uh, what do we do with y? In this case, y is just a constant. Maybe it's a variable in another. But y doesn't depend on x in this case. And I've seen a lot of other other students who use like y, who use the substitution irresponsibly. So like maybe they have u ln x and then they forgot to remove the ln x. And they already did everything. So what they do is just put ln x outside like that. That's not correct. This is not correct. You don't do that. Why? Because u is a substitute for something in the x world. So it's just a package essentially. So you don't do that because there's a package of x in there. You don't put x outside just because it isn't u. No. X and U are related to each other. That's why they don't get to, do that. What? Uh, but in here, Y and X aren't related to each other. They are independent variables from each other, despite usually being dependent variables. But Y is usually a variable, right? We can treat it as a constant in the X world, like this one. The integral of X cubed is X to the 4 over 4. Let's put Y there. The integral of ln x is x ln x minus x. So let's just put y in there. So xy ln x minus xy. You can check why that's true. And then since y is a variable, we have to write g of y, which is an arbitrary function. What is an arbitrary function? Essentially, since y is in here, uh, the original function which this is derived from, there has to be a function that is only y without x, that eventually uh, differentiates to zero. It's like plus c, the arbitrary constant, except it's g of y, the arbitrary function. This will come in handy later in differential equations. And yes, there are going to be differential equations later. Question number 25. E to the x dx over 2 e to the 2x plus 7 e to the x plus 6. This is just another integration by substitution exercise. So let's integrate by substitution. Let's just put this here. So du on the top, and then 2u squared plus 7u plus 6. And I am hiding a partial fractions question in here. So there you go. Separating the trinomial, we get 2u plus 3 and u plus 2. Use the cover-up method if you want. I'm just setting this up. And I'm going to tell you that A is 2, so here, and B, or the second one, is negative 1. Here, ln of 2u plus 3. Here, negative ln of u plus 2. And turn back into the e to the x. So ln of 2 e to the x plus 3 minus ln of e to the x plus 2. Don't forget the c. Now, here's a very interesting question. XP3, where P is the permutation operator. So, what is the permutation operator? Essentially, permute B is equal to, usually it's thick P right here. This is a factorial over b factorial. That's essentially the permutation operator. It's mostly used in statistics and probability, but I've decided to put it here because it has some interesting side. This is actually wrong. Sorry, this is not b. This is a minus b factorial. That's the permutation operator. I apologize about my prompt earlier, but the so as I said, the permutation operator is used in statistics probability, but I'm going to use it in integration for a specific reason. XP3. Using this formula, this is going to be x factorial over x minus 3 factorial. Alright? This simplifies to be x minus 1, x minus 2. That's essentially it. This becomes x cubed minus 3x squared plus 2x. X cubed is x4 over 4 minus 3x squared minus x cubed. Then that becomes x squared. And half plus c. That's just it, essentially. Uh, this may not make sense in terms of statistics and probability. I mean, what is the integral of a permutation operator? But I think it is still interesting. So let's go to the next one. The combination operator. The combination operator is similar to the permutation operator. It's also used in statistics and probability. It is x factorial over x minus 3 factorial, but with the added 3 factorial in here. So it's going to be 1 over 6 times the integral of x factorial over x minus 3 factorial, or the permutation earlier. We just added 1 over 6 factorial here. So what we can do now is, what we can do now is just substitute what we had earlier. So, you know, x to the 4 over 4 minus x cubed plus x squared. And then x to the 4 over 24 minus x cubed over 6 plus x squared over 6 plus c. Answer. That's it, essentially. Question 28. 1 over 1 plus x squared, not using arctangent, but using the power series. Now, how can we do this? We know that 1 over 1 plus x squared, we can express that as 1 over 1 minus negative x squared. We can also further express that into the power series expansion of that using the geometric series. This is its alternate form. Yeah. So let's put that back. Integral of the sum n equals 0 to infinity, negative 1 to the power n x to the 2 n dx. This is just a constant. This is the variable. So let's integrate only that. Then x to the 2n plus 1 over 2n plus 1. Sorry. There we go. Yeah, I forgot something there. Plus c. This is the Parse's expansion of arctangent, actually. Maybe a few constants ahead or behind, but that's it. Here, 1 over x to the 4 plus 4. This looks a bit deceptively simple. It is not very simple. What can we do here? Well, x to the 4 plus 4. Let's add plus 4x squared minus x squared. This is a perfect square trinomial, x squared plus 2 quantity squared. Uh, this is 2x quantity squared. We can do this. X squared plus 2x plus 2, x squared minus 2x minus 2, right? So we can put that in the original one. Uh, for the top, let's put 2ax plus b, 2cx plus d. And you are going to go insane if you don't use a calculator here, but let's put the terms on hold. If you're going to do this manually, we gotta have the systems of equations. So for the x cubed term, what is going to be x cubed? It's 2a, because 2a x times x cubed here, so 2a plus 2c. There's no x cubed in the original since it's only 1, so 0. X squared. So what's going to have an x squared term here? First is b, and then d, and then 2a times negative 2 minus 4a, and then 4c, since 2c times 2. Again, 0. What is going to have an x term here? First, we have b times negative 2, so negative 2b, then 2d, then 2a times negative 2, so 4 minus 4a plus 4a. Hold on. Oh, this is plus 2, yeah. Plus 4a plus 4c. For the constant, the only constant is 2b plus 2d, which is going to be 1. Solving this, we will get 1 over 16, 1 over 4, negative 1 over 16, and 1 over 4. So first, hold on. First, we put everything back here. So this is going to be very long. So 2 times 1 over 16x plus 1 over 4 over x squared plus 2x plus 2 dx plus integral of negative 2 times 1 over 16 plus 1 over 4 over x squared minus 2x plus 2 dx. On here, let's put 1 over 16 outside. 2x plus 4 over x squared plus 2x plus 2. Over here, let's have 1 over 16 outside. Let's have negative, sorry, negative now. So, yeah, it's negative. Jesus. Negative 1 over 16, 2x, we got x here, minus 4 over x squared minus. Alright, derivative of the bottom is 2x plus 2. So we kind of have 2x plus 2 on top. We just set up everything. And then what we have to do is to put the remaining plus 2 on another part of the, like this. And then let's do the same for the other one. And put the remaining negative 2 here. Jesus. Except in here, it's more appropriate to write it in its completed square form. So x plus 1 quantity squared plus 1. And in the other one, it's x minus 1 quantity squared plus 1. So let's write that there. Now we can see how it forms. So in here, 1 over 16 ln of x squared plus 2x plus 2 plus 2 times 1 over 16 is 1 over 8. And then this is our tangent of x plus 1. Let's put the rest down here. Negative 1 over 16 then ln of x squared minus 2x plus 2. Negative 1 or 16 times negative 2 is positive 1/8. Then arctangent of x minus 1 plus c. That is the answer for question number 29. Question number 30, the last of the indefinite integrals. Sine squared x plus cosine squared x plus tangent squared x plus secant squared x plus cosecant squared x plus cotangent squared x. It's just a little challenge I'd like to process. So sine squared x plus sine squared x is 1, obviously. For these, it's a bit tricky, but tangent squared x is secant squared x minus 1, and secant squared x we retain, and cosecant squared x we also retain. For cotangent squared x, we replace it with cosecant squared x minus 1. Let's add the constants together. 1 minus 1 minus 1, that's negative 1. So put negative 1 on the end, like that. So secant plus secant, 2 secant squared x. Cosecants, we have 2 cosecant squared x's. And our answer now is 2 tangent x minus 2 cotangent x minus x plus c. Oh, that's the answer. For our first definite integral, we have the integral of 1 over 1 plus x squared dx as x goes from negative infinity to positive infinity. Now, this is very simple. We just have to find the antiderivative of 1 over 1 plus x squared, which is going to be arctangent x. And then we set the bounds from negative infinity to infinity. Now, from here, we need to apply the limits, but I'll just tell you what it is. So, arctan of infinity is going to be pi over 2. If you look at a graph of a tangent, it looks something like this. Never mind the poor drawing. This is negative pi over 2. This is pi over 2. If you look at the tangent, it actually looks like that, correct? Where at pi over 2, it goes up to infinity, and at negative pi over 2, it goes down to negative infinity. So we can say that the arctan of negative infinity, or at least the limit as it goes to negative infinity, is negative pi over 2. And remember, the integration technique is to substitute it first in the if we substitute the top limit first and then subtract it by substituting the bottom limit. The answer for this is pi. Question number 32 is the integral from negative 2 to 1 of the floor function of x squared dx. The floor function states that if you have something like, I don't know, 2.718, the floor function of that would be just the whole number. All right. This is different from the ceiling function, where the answer for this would be uh the decimal but up. So it's going to be 3. All right. Is essentially rounding down for floor function or rounding up for ceiling function. And if you're rounding, as in both rounding up and down, depending on the decimal places, that's just round. It's not floor or ceiling. However, you can say, let's say 2.99. The floor function of that is going to be 2. And the ceiling function of that is 3. But add zero point 0.1 more, so 3.0. The floor function of this is now 3 and not 2. The ceiling function of this is also 3, since it has no decimal places above 3.0, right? So that's how these work. So how are we going to find the integral of the floor function of x squared? Well, for one, we know that the floor function is going to be piecewise. How? So this is the original graph of y equals x squared. The floor function states that only the whole numbers remain. The decimals get thrown out. So what's going to happen is something like this. Yes. So, so what was once the parabola became the just a couple of broken lines, and we need to set where those lines are going to be. So how are we supposed to find that? Well, let's first uh, figure out when x squared would be an integer. So this is x squared. So we need to know the bounds. So it's negative 2 and 1. So negative 2 here. Let's put 1 right here. So it's 4 and 1. All right. When is it going to be uh, an integer? So it's only integer if x squared is 4, 3, 2, 1, 0, 1, because it goes up, right? So what are the values of in the betweens? So in here, it's going to be negative root 3, negative root 2, negative 1, 0, and then 1. Those are going to be the values in which they are integers. And what happens at those values? So, for example, this is negative 2. Then, and then it goes on like this. And it drops down actually to here, from negative 2 to here, which is negative square root of 3. Then it drops down again like this, all the way to square root of negative square root of 2. And then drops down to here to negative 1. And then it drops down for for the last time to get to 0. Something like that. Anyway, yeah, 0. And then it goes up to 1, like that. So that's going to be the area. Mm, yes. So we're going to have to break this into piecewise function. We can ignore the functions that is here. Uh, this one, we can ignore that one, and we can focus on these ones. So first, the value of this is going to be 3. And then we can find the integral of 3 from negative square root of negative 2, since that's lesser, to negative square root of 3. Next, the integral from negative square root of 3 to square root of negative square root of 2 times 2, since the length of that is going to be 2, or the height, sorry. And then from negative square root of 2 to negative 1, 1 x. And from here, actually, it's going to be all 0, not this one. I kind of misspoke. Well, it's all going to be 0 from there, since the 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 floor function of anything between 0 and 1 is just 0. So it's going to be 0. So we're going to ignore that for now because we know it's right. So in this is going to be 3 times, since this is 1 dx, we just have to subtract the bounds. So it's negative root 3 minus negative 2 plus 2 times negative root 2 minus negative root 3, and then plus negative 1 minus negative root 2. And if you add them all together, it is approximately 1.85. That is our answer. Next, the integral of arctan squared x over x squared sine to the 4x as x goes from negative 2 to 1. This sounds unnecessarily complicated, but Are there any clues? First clue is the bounds. When we have a function that is odd, for example, like this, odd functions essentially, it is symmetric across the y-axis, but opposite. Even functions is just the first part. This is even functions. This condition makes it odd. And what's good with odd functions is that if the absolute value of the bounds are the same, such as like this, the area is automatically zero. But we have to find out if the function we have is odd or even. If it's even, we have to do something else. If it's odd, the answer is immediately zero. So we just have to prove that it is odd. So first, let's decompose this into three functions: arctan squared x squared, and sine 4x. What do we know about these functions? X squared. We know x is odd because, well, if you look at the graph, it is symmetric, but it is opposite. And if we find the area of like negative 1 to 1, it's going to be 0. So x is odd. But x squared is even, right? If we look at the graph of x squared, it is symmetric, but it is not opposite. It's the same values. If we had like that, we would not get 0. Like, so x squared is even. In fact, if you square anything, it would be even. Much like how if you multiply 2 to an odd number, it would be even. This is even. And this is also even. Regardless of whether or not arctan x is odd or even, the presence of the squared indicates that it is even regardless. And as a side note, arctan x is odd. It's an odd function. So there you go. Sine 4x, if we know the shape of sine, it looks something like this. Sine 4x is an odd function. Actually, sine as it is an odd function. How can you know it's an odd function actually? Well, one way to find out is to to turn the x into negative x. What would the result be? This is going to be negative sine 4x. Alright? And if it is negative of the original, it is going to be odd. Check for the others. So x squared and then negative x quantity squared is x squared. If they're the same, this is even. Alright? And same thing for arctan squared x. Alright? So going back here, this is even, this is even, this is odd. There are an odd number of odd functions. Therefore, the whole thing is odd. And if it is odd and the absolute values of the bounds are the same, or at least one of them is the same but flipped in the sign, it is going to be 0. And that's the answer. Next, the integral of x cubed dx as x goes from negative infinity to positive infinity versus the same thing but formulated as if it is a limit. What is the difference between these two? First, let's address this one. The integral of this, we know that this is an odd function. So this must equal 0 for any value of a that is not 0. Actually, if it is 0, the bonds would be the same. So it would be 0 regardless. But for any value of a, this integral is 0, right? Because the function inside is an integral. Even if we had the limit as a go to infinity, it would still be 0, right? Contrast to this, just directly uh, putting infinity into the bounds. This is actually undefined. Why? even though they look the same, we can formulate this using a different integral. The limit as a goes to infinity, the same thing, but we can do 2a and negative a here, right? And this would still be that. This would still equal that because 2 times infinity is still infinity. However, that is not an odd function because the bounds, their absolute values are not the same. So, so actually, this has a different solution. This is actually infinite if you think about it. But since one variation is zero and the other variation is infinite, this is undefined. Or at least it has no answer. Next, let me just, let me just, there we go. Okay, so the integral of cosine x over sine x plus cosine x from x equals 0 to pi over 2. So over here, we're going to use a slightly less known property of integrals, and that is the king property. Essentially, if you have an integral with bounds a to b of f of x dx, we can replace f of x with f of a plus b minus x dx. Let's prove this. So let x be equal to a plus b minus u. All right. Dx then is negative du, the bounds. So when x equals a, what is u? Well, we need to retain a, so we have so u equals b, right? A plus b minus b is a. So there we go. Same thing for x equals b. U is going to be a, so they just switch. Okay, so here, negative t. There we go. We put the negative on the outside, and with the negative side, we can flip the bounds, and then we can rewrite there. U is just a dummy variable, which means it's not that different if we put x in there because variables are you can alternate them for any letters, and nothing in this still clings onto the others, so we can substitute it with x. And there we go. We proved the property. How can we use this property? Well, let's try it out here. Uh, since the king property holds true, we can say this is correct. So cosine x becomes pi over 2 plus 0 minus x. So just pi over 2 minus x. Same thing on the denominator. Sine of pi over 2 minus x plus cosine of pi over 2 minus x. And then on the top becomes, if you remember your the trigonometric identities, the top becomes sine x, the bottom becomes cosine x plus sine x. Now let's uh let's symbolize this as I, and since this is the same due to the king property, this is also I, right? Now let's add I plus I. First, we add this. There we go, the original, and we add its copycat, which is sine x over let's switch this, so sine x plus cosine x, and there you go. We can add them together since they have the same bounds. So there you go. Sine x plus cosine x over sine x plus cosine x. Doesn't that cancel each other out, leaving us with 0 to pi over 2, then dx. Easily, this is just pi over 2. So we know 2i is pi over 2. That implies I is pi over 4. That's the answer. Next. Uh, the integral of 1 over x cubed dx as x goes from negative 2 to 3. Let's try it out. So the antiderivative is negative 1 over x squared. Negative, uh, sorry. So the antiderivative is negative 1 over 2x squared. And if we check that that is in the answer, and we just go from negative 2 to 3. So putting 3 in here is 1 over 18, so negative 1 over 18. Putting 2 is 4, so negative 1/4. Negative. Oh, it's negative. Yeah, right? Oh, 8. Sorry. It's going to be 8. So minus the negative 1 over 8. So it's going to be that. Negative. Yes. And this is equal 1 8 minus blah blah blah. I can tell you this is wrong. Why? Let's look at the graph of 1 over x cubed. It looks something like this. Ah, there's our problem. Our bound is here and here. There is this section of infinity that we have not discussed in this. So we're ignoring that. So how can we solve this? So first, let's separate them so that we don't ignore infinity. So negative 2 to 0 first, and then from 0 to 3. And to avoid having the same bounds in here and here because it's going to be infinite because I have to put this minus and plus in here. All right. So first we have 1 over 0 plus minus 1/4. It's from here. Uh, Plus 1 over 9 minus 1 over 0 plus. This should be minus. There we go. Sorry. And then then multiply that by negative 1. This is negative infinity. This is positive infinity. And mm, hang on. I think I'm mistaken. Hmm. Oh, no, no. They're both plus because if we integrate this, this will become squared. So it will be 0 plus and 0 plus. 0 minus is going to be 0 plus if we square it. So it's going to be negative infinity. This is going to be positive infinity and negative infinity. The problem here is that infinity minus infinity is going to be an indeterminate form. So we have to find another way to solve this. Okay, so if we had this as an integral instead, what would you say the answer be? Well, this is an odd function, so this is going to be 0. Despite the indeterminate in between it converges to a 0, right? The sum. If we go both directions at the same rate, and we don't go it like weirdly, like slower here or something. If if we did everything right, the integral of this should be 0, ideally. So we're going to assume that we're going to have to solve this remaining part. Since 2 and negative 2 are 0 already, we just need to find the bounds 2 to 3. And that is much easier than the other one and much more correct. So again, the integral of this is negative 1 over 2x squared from 2 to 3. So we get negative 1 half times 1 9 minus 1 4. And if we calculate this, this is going to be around 5 over 70. That is our answer. Sine to the 4x, cosine to the 4x. This is a bit hard. What can we do here? First, we have to discuss the Wallace property. Essentially, if your bounds is between 0 and pi over 2, not 4, we can be sure that the uh, this form has an easy answer, which is n minus 1 double factorial, then m minus 1 double factorial over n plus m double factorial. Double factorial is not factorial and then factorial again. It is not that. That's too big. Double factorial is skipping by 2. So 4 factorial, you know, is 4 times 3 times 2 times 1. 4 double factorial is just 4 times 2. Similarly, 3 double factorial is 3 times 1. So for example, 7 double factorial is 7 times 5 times 3 times 1. Right? And then we multiply this by L. L is pi if m and n are even. Both of them should be even for this to work. We just so L, let me just remove this. So for clarity, L equals pi if m and n are even. L is 1 otherwise. So if there's an odd number in anything else, it's going to be 1. So that's right here. The bounce is pi over 4. That's a bit problematic. We can't use the Wallace property right now. But we know that sin x cosine x has itself a trigonometric identity we can use. Sin x cosine x is 1 half of a sine to the 4 2x, right? So we can use that. Oh, this is wrong. Sorry. Hold on. Okay. To the power of 4 outside. 1 half times to the power of 4 becomes 1 over 16. And the sine 2x becomes sine to the power 4 2x. Let 2x be equal to u. 2 dx is du, right? So du is dx over 2. As x is 0, u is 0. X is pi over 4. The double of that, or 2 times that, is pi over 2. Rewrite the new bounds. Since there's 1 half, we can put it outside. We replace 2x with u, and we have a form of the Wallace integral. Wallace integral here has cosine to the mx. M can be 0. The m terms just have to disappear. So there. And in here, sorry, in here we have no cosine. So we just remove that. We just have n minus 1 double factorial over n double factorial. So 1 over 32 times the Wallace property of this. So 3 double factorial over 4 double factorial, which is 3 times 1 over 4 times 2. And since this is even, we have to multiply by pi. Don't forget pi. So top becomes 3, bottom becomes 1024, and pi remains. So that is the answer. Next, sine cubed x cosine to the 7x dx as x goes from 0 to pi over 2. This is again uh just the Wallace property. And we have both sine and cosine. So it's going to be n minus 1 double factorial, then m minus 1 double factorial over n plus m double factorial. N minus 1 is 2 double factorial. 7 minus 1 is 6 double factorial. And adding up together makes 10 double factorial. Instead of answering this by hand. So 2 becomes 2 times just 2 actually. 6 is 6 times 4 times 2. Bottom becomes 10 times 8 times 6 times 4 times 2. These terms cancel each other out. This and that cancel. We get 1 over 40. That's the answer. Next, the integral of x times square root of 1 minus x squared as x goes from 0 to 1. We can use trig identities, trig sub actually. So let x equals sine theta. Dx becomes cosine theta d theta. All right. And then x equals 0, sine, x equals 0, theta should be 0, right? X equals 1, theta should be pi over 2. Sine pi over 2 is 1. All right. So for sine x becomes sine theta, 1 minus x squared becomes square root of 1 minus sine squared theta multiplied by cosine theta d theta. This becomes square root of cosine squared theta. So it becomes cosine theta. Multiply that by the existing cosine theta, we get cosine squared theta. And then sine theta somewhere here. We can use the Wallace property now here. So uh yeah, what can we, so one of them is odd, so L has to be 1. So one double factorial times 2, no, 0 double factorial times 1 double factorial over 1 plus 2 is 3 double factorial. 0 double factorial is 1, and 1 double factorial is also 1. 3 double factorial is just 3, so it's just 1/3. Last, sine cube x dx as x goes from 0 to pi over 3. Pi over 2 we need, but we don't have, and we can't exactly do that. So we're just going to have to use the traditional way. We know sine cube x can be decomposed like this. Sine x and then sine squared x. Let's skip that part and think about 1 minus cosine squared x. Alright? Let cosine x be equal to u. That means negative sine x dx equals to u. X is pi over 3. Cosine pi over 3 is 1, 1 half. X equals 0. Uh, u is equal to 1. Alright, bounce. And then 1 minus u squared, and then negative du. The negative can switch the bounds, so we have 1 half and 1, then 1 minus u squared. Integrate. There we go. And from 1 to 1 half. Calculate. 1 minus 1/3 minus, then 1 half minus 1 half cube is 1/8 over 3 is 1 over 24. 1 minus 1/3 is 2/3. This becomes, if we multiply this by 12, we get 12 over 24. 12 minus 1 is 11 over 24. And from here, we multiply both numerator here by 8. So 16 minus 16 over 24 minus 11 over 24. That's 5 over 24. All right. Next up, the integral of x cubed minus 1 over ln x dx as x goes from 0 to 1. Let's call this one as I. Let In be the integral from 0 to 1 x to the n minus 1 over ln x. And yes, we're going to be doing the thing that Richard Feynman popularized, which is finding the derivative under the integral sign. So let's find the derivative of I prime of n. I of n, which is I prime of n. And what we're going to do here is to find the partial derivative with respect to n of this function. So x to the n minus 1 over ln x. Ignoring everything that isn't n, which is x, and just looking at here, we can see that the derivative is x to the n ln x, and 1 is just a constant in terms of n, so that's going to be gone in respect to this. So here it is. 1 over ln x, since ln x is in the denominator there, then x to the n times ln x. The reason we did this, which is called Feynman's technique, is because ln x cancel each other out like this. And now we have the integral of x to the n as x goes from 0 to 1, which is simply this, x to the n plus 1 over n plus 1, and then from 0 to 1. If we solve this, we will get 1 over n plus 1. Now, the integral of this, since this is still derivative, we need to find the antiderivative of that. So the antiderivative of 1 over n plus 1 is simply ln of n plus 1. Don't forget plus c. We need to know what plus c is before we put 3 in n, because I of 3 is I. So this is going to be I of 3. But we need to know what c is first. So how do we find that? First of all, let's set something the easiest value of n that we can find. Uh, you can find maybe it's 0 or infinity or whatever. For this one, it's going to be 0. Let me show you why. So I of 0, let's refer back to here. N here becomes 0. This n becomes 0. So x to the 0 is 1. 1 minus 1 is 0 on the numerator over ln x, and that becomes 0 dx. And the area of a graph that has just 0, it looks like this, by the way. So 0 is just that. So there's no area, it's just 0, no matter where the bounds are. All right. So I of 0 is 0. On the other side, I of n equals ln of n plus 1 plus c. Let's check. We replace this n, not this n, this is natural logarithm, not that one, with 0. ln 0 plus 1 is ln 1. ln 1, the logarithm of any base with 1 as the input is always 0. So 0 plus c equals c. And since these two are equal, c must equal to 0. So let's go back. C equals 0. So this is the complete I of n. Alright. And then plus 0. So we don't put that there. And to find the original integral, we have to find I of 3, which is ln of 3 plus 1 is 4. And that could be your answer, but I'm going to simplify this to be 2 ln of 2. Don't ignore the absolute values because 4 is 2 is positive at this point. So there we go. That is the answer. E to the negative x squared cosine 3x dx as x goes from 0 to infinity. Can we use the Feynman technique here again? We can use it this way. So let's use A for now. And let's copy this part. But we're going to make this thing, the 3 here, a variable. So it's going to be AX. There we go. Now, we need to find the derivative with respect to a of the original integral. So we're going to be doing the Feynman trick again. There we go. So what's the derivative of this one? Mm. Mm. So this doesn't have a in it, so that's just going to be treated as a constant multiple. This does have a in it with x as the multiple of a in the inside. So we're going to be differentiating this part. So the derivative of cosine is negative sine. So let's rewrite this. The negative sine of ax. And then by the chain rule, we have to find the derivative of the inside. So derivative of ax with respect to a is going to be x. All right. All right, there we go. So what can we do here? Well, an insanely helpful trick is this. 2 times 1 half equals 1. So we can put 2 here and 1 half outside. And if you multiply that, that would equal 1, right? So nothing would change because we're multiplying by 1. But we can do this. So let's rearrange. The negative goes here. The x goes here. E to the negative x squared goes here. Sine of ax dx. What we've what we have here is negative 2x e to the negative x squared, which if you integrate that part alone is, well, it's not non-elementary. It's e to the negative x squared. That's the integral of that. So we're going to be using differentiation by, sorry, integration by parts for this one. Let's use the DI method. For the D column, we put sine AX. So sine AX. For the I column, we put negative 2x e to the negative x squared. Don't forget the signs here. The derivative of sine AX now, with respect to x, is a cosine AX. And this integral, again, is e to the negative x squared. And we stop there because we don't have the integral for e to the negative x squared, so uh, we're going to be multiplying this from here. But we can multiply this to get the answer. Negative e to the negative x squared sine ax from 0 to infinity. This is x, not a. And then we subtract integral of a e to the negative x squared cosine ax dx. There you go. Here, e to the negative infinity is 0. Sine of 0 is 0. So this is just going to be 0. And I can do that. I can do the e to the negative infinity because sine of any input is only between negative 1 and 0. So if you look at the graph, it looks like that. That's the graph of e to the negative x squared sine ax. So it doesn't matter if, it doesn't matter if the sine or cosine because it's only between 0 and negative 1 and 1. And the oscillation thins out as e to the negative x squared approaches 0, right? So it's something like that. Uh, yeah. So 0 minus 0 here. So that's just 0. Minus this integral, which let's rearrange. This might look a bit familiar. This is the original integral from earlier, I of a, right? So let's put it as, so negative a I of a. And that's 1 half. We have to multiply that by 1 half to get the original I prime of a. So I prime of a is negative 1 half a I of a. All right. Now this is a differential equation. If we divide both sides by I of A, we can cancel this out. We get here is I prime of A over I of A. This is a natural logarithm situation. So we integrate both sides. This becomes a natural logarithm. So ln of I of A on this one, we have negative 1 half A. Its integral is going to be negative A squared over 4. It's just power rule stuff. And plus C. Don't forget plus C, of course. Raise e to both sides. We get I of A equals e to the negative a squared over 4 plus c. But since that means that e to the c becomes a constant, we can just put a constant outside. So c, e to the negative a squared over 4. So that's I of A. We want I of 3, right? But we still have C. So let's put I of 0, perhaps, because we need to find the value of C. I of 0. From the original, I of 0 would just make e to the negative x squared cosine ax. A being 0 here, cosine of 0 is just 1. So this would be the integral of e to the negative x squared as x goes from 0 to infinity. And this is a very popular result. It's going to be square root of pi. And I of 0 on this part, a just becomes 0. So uh, a becomes 0, so the exponent of e is 0. E to the 0 is just 1. So 1 times c is c. So I of 0 is just c. Or, since I of 0 and I of 0, same thing, c has to be square root of pi. So I of a is square root of pi e to the negative a squared of 4. We need 3. Oh, sorry. Over 2, since this is only 0 over 2. There we go. Let me just yeah, erase this one. All right. So I of 3 is 3 squared is 9. So e to the negative 9 over 4 here. The square root of pi over 2 here. That is the result. That is an interesting integral, and it yielded some very interesting results. Oh, this is not an integral. The limit as n goes to infinity of 2 over n times the sum from 0 to n of 2 plus 3i over n quantity squared. How is this related to integrals? Let me show you how by rearranging some stuff. Okay, so 2 over n seems to be major, so I'm going to keep that in. My problem with here is that this is 3 over n, not 2 over n, so I'm going to do this. So we have 2 over n here times I, and then 3 over 2 is just a multiple, so that's fine. What is this now? This is a Riemann sum. You can imagine it as like a graph going from 0 to 2, and then solving the graphs, approximating the sum requires you to put some rectangles like this. And if the rectangles are smaller and um, there are more rectangles in quantity, there are more, how to say this? It just gets more accurate the more rectangles you put, right? So that's why n goes to infinity, because we need infinite rectangles to find the exact value of the integral. And this is actually an integral. This sets the bounds. This is our equation, and we can go set up the mm, set up our integral. So essentially we need to replace 2i over n with x. So 2 plus 3 over 2 x. That's going to be our integral. And then 2 over n represents our bounds from 0 to 2. So that's why there's 2I over n representing as x, right? So that's what it is. Finding the integral here is very easy. We just have to, well, you can do anything you want. You can use integration by substitution, but I just expanded it. So the expanded form is 4 plus 6x plus 9x squared over 4. Integrating that gives us 4x plus 3x squared plus 3x cubed over 4 from 0 to 2. Let's evaluate 8 plus 12 plus 6 minus 0 minus 0 minus 0. This becomes 26. That's our integral. Or that's the limit, actually. But this is a Riemann sum, which is going to be useful for our next one. The limit as I goes from 0 to as n goes to infinity of the sum from 0 to n of n over n squared plus I squared. How are we going to do this? Observe earlier that we needed blank over n. So 1 over n, 2 over n, blah, blah, blah. We need to produce an I over n somewhere in this. So how are we going to do that? Let's try multiplying both the numerator and the denominator by 1 over n squared. One of the things you have to learn in mathematics is that you just have to do things like multiplying both sides or multiplying both top and bottom. And this is particularly useful in here. Let me just write this. So on top, it just becomes 1 over n. On the bottom, it becomes 1 plus I squared over n squared. All right. Put I over n on the outside of the sum because we're talking about I as this in the within the sum. So we can safely put 1 over n here. And there we go. We put I over n quantity squared like this. So it's easier to see that this is another Riemann sum. Again, 1 over n sets the bounds. So it's from 0 to 1. And then the I over n is going to be our replacement for x. So it's 1 over 1 plus x squared. All right. This is very easy. What the integral of that is going to be arctangent of x. No need to explain. And arctangent of 1 is pi over 4. Arctangent of 0 is 0. So it's going to be pi over 4. That's the answer. How about this one? Instead of n on the numerator, it's I. How can we solve this? Let's try the trick again. So let's multiply 1 over n squared, both top and bottom. For here, we get I over n squared, which doesn't make sense. But remember, I over n squared is just I over n times 1 over n. And 1 over n, we need that in order to set the bounds, right? So we can put the 1 over n on outside the sum. There we go. I over n here. Then 1 plus I over n quantity squared, like earlier. And we have a Riemann integral yet again. So the bounds is set by this, so 0 to 1. I over n is the x term, so x over 1 plus x squared. This is very easy. We just have to multiply by 2 and divide by 2 at the same time. So we get the derivative of the bottom. We need the derivative at the bottom so we can put ln or natural logarithm. There we go. From 0 to 1, set the bounds. So ln of 1 plus 1 squared is ln 2, so 1 half ln of 2. And then if this is 0, ln of 1 is 0, so 1 half times 0 is 0. So that's going to be our answer. Next. This is a bit tricky. So f of x dx, the integral of that from negative 1 to 2. If x equals x, if x is greater than 0, f of x is 3x squared minus 2. If if x is less than or equal to 0, f of x equals negative 2 times x plus 1. So how does this look? Firstly, it says if x is greater than 0, so on the positive side here, f of x is 3x squared minus 2. So how would that look like? 3x squared looks like a parabola. It is a parabola actually. And it's if x equals 0, it's like negative 2. So it's like right here. And then it goes up like that. Pardon the drawing. It's not the scale. It's even slanted. So I don't know how that happened. If x is less than or equal to 0, f of x equals negative 2 times x plus 1. At x equals 0, this becomes 0 plus 1. So 1 times negative 2 is negative 2. So this has a point. And then if we're going, hold on. So if we're going negative, it has to go that way. And if you continue, it would go like that. So that makes sense. So this is the look of our graph. This is a piecewise function. All right, how do we solve this? First of all, we need to integrate this. We need to integrate the left side and then the right side. The left side consists of values from negative 1 to 0, and the right side consists of values from 0 to 2. So from the left side, negative 1 to 0, and from the right side is from 0 to 2. Now you say, well the right side or x greater than 0 does not involve 0 at any point. That I say is this 0, this 2, this negative 1, this 0. It's all just limits anyway because it's calculus. It's all just limit. It's approaching 0, but sometimes if you don't want to, it's not 0. It is just approaching 0. So we can. This is still legit. So for this one, we need negative 2 of x plus 1. So there we go. So negative 2, then x plus 1, dx. And then we add from 0 to 2, the positive condition, 3x squared minus 2. Okay. So for here, we can simplify this to be negative 2x minus 2. The integral of that is negative x squared minus 2x from negative 1 to 0. In here, the integral of this is x cubed minus 2x, again from 0 to 2. Now from 0 to 2 actually. So, yeah, I'm just looking at my notes. In here, we get, well, 0 first. So 0 minus 0 is just 0, 0, 0, whatever. So 0. Then minus the negative 1. So negative 1 squared is negative 1. Minus 2 times negative 1, positive 2. So that's going to be the one side, left side, and x cubed minus 2x. So 2 cubed is 8. Then 2 times 2 is negative 4, since it's negative. And then 0, all of that is 0, so it's 0. So this is 4, this is 2 minus 1, 1, negative 1, negative 1 plus 4. The answer is 3. That's the integral. 47. The absolute value of x squared minus 4 dx. As x goes from 3 to negative 2. Spicy. First of all, the bounds, they're inverted. We can invert them back into their proper bounds by multiplying it by negative 1. So here, uh, like that. And then the absolute value of x squared minus 4 dx. Second of all, the absolute value is another piecewise function. But we need to know where x squared minus 4 becomes positive because x squared minus 4 looks like this. However, it dips below the negative line, so absolute value looks like this. So we need to know when it crosses the x-axis. X squared minus 4, its roots are negative 2 and 2, right? So this is negative 2 and 2, and that's where it crosses the x-axis. We know that after between negative 2 and 2, it's negative. So this is going to be a bit tricky, but in here, it's going to be positive. So in here is positive. This one is negative, then positive. We need to multiply the area of the thing inside here by a negative 1 in order to find the positive area. So that's going to be our agenda. So we have the negative. So positive or negative. Well, to the left, negative 2, we don't have anything that we need to solve. So from negative 2 to 2 only. X squared minus 4. And then negative on the outside. And then positive integral from 2 to 3 of x squared minus 4. There we go. Hmm. So let's multiply the negative on the outside, on the inside already. So negative negative is positive. So we that's positive now. The integral of x squared minus 4 is x cubed over 3 minus 4x from negative 2 to 2. And then negative positive is negative, and then the integral of that is again x cubed over 3 minus 4x from 2 to 3. All right. So 2 cubed over 3, 8 over 3. Minus 4 over 2, 4 times 2 is 8. Minus, and then negative 2 cubed is negative 8 over 3. And then minus 4 times negative 2 is positive 8. There we go. Minus this part. So 3 cubed over 3, that's 27 over 3, that's 9. Minus 4 times 3 is 12. Minus. Inserting 2 again, 8 over 3, then minus 8. There we go. You can solve for this, and my results indicate that it is negative 13. Yeah, I think I used a calculator for this one, but it is negative 13. That's the answer. Ah, the integral of sine x over x dx as x goes from 0 to infinity. Remember the infamous limit of sine x over x as x goes to 0. But now this is the advanced version of that, which is the integral from 0 to infinity. And this is going to be a bit difficult. We're going to be using the Feynman method earlier. So let this be I. I of s, let's just use s, because you'll understand why later. From 0 to infinity of sine x over x e to the negative sx dx. And you might say, whoa, why did we just multiply e to the negative sx? You'll understand later. And if you already know why, you might know the name Laplace, but we'll understand later. So I prime of s 0 to infinity, and then the derivative of with respect to s, then sine x over x times e to the negative sx dx. What we can do here is to find the derivative of e to the negative x. The sine x over x is just a constant with respect to s, so we're just going to have to settle with e to the negative sx, and the derivative of that is negative x e to the negative sx. X here cancel each other out. That's very nice. And that is the entire purpose of the partial derivative. So negative e to the negative sx sine x dx. From here, we can use integration by parts. So di. So for d, we put sine x. For I, we put negative e to the negative sine x. Sorry, sx. And then plus minus plus derivative is cosine of the negative sign. Integral is 1 over s e to the negative sx and negative 1 over s squared e to the negative sx. All right. Integral like this. So it becomes, hold on, 1 over s e to the negative sx sine x plus 1 over s squared e to the negative sx cosine x from 0 to infinity. And then we add the integral of the bottom term. So positive, negative, negative is positive, and then e to the negative sx sine x over s squared x. All right. So here, the e to the negative sx term, if it comes into contact with the infinity, it just makes it zero, regardless of if sine x or cosine x are negative or positive. It's just zero. So it's zero. And then the problem is with the zero term, because sine of zero is zero, but cosine of zero is one. So that is kind of a problem, but not to worry. We can just put negative one over s squared in there. Since it is the bottom bound, so it's negative, then e to the 0 is 0. Cosine of 0 is 1. E to the 0 is 1, sorry. And then we multiply by 1 over s squared, it's just 1 over s squared. Or negative 1 over s squared. And then we add 1 over s squared times the integral of e to the negative sx sine x dx. Alright. Let's go back to I prime of s. It's negative e to the negative sine x dx. So this is also I prime of s. This is negative I prime of s. Uh, yeah, it is that. So we can substitute negative I prime of s in that. So I prime of s is negative 1 over s squared minus negative 1 over s squared again, I prime of s, which is negative 1 over s squared, then 1 plus I prime of s. Yeah. And after that, it's a bit confusing. My notes are sorry. I prime of s over 1 plus I prime of s equals negative 1 over s squared. Let's flip both sides. 1 plus I prime of s over I prime of s negative s squared. Ah, the left hand side becomes 1 over I prime of s plus 1 s the negative s squared. And then after this, we subtract 1 on both sides to get that. And then we flip it again to find I prime of s. And this is what we get. We now have I prime of s on its own, which is this. Awesome. We need to find I on I of s. So that's just the antiderivative of I prime of s, which is negative arctangent of s. plus c. Don't forget the c. Now, remember I of s earlier is this. If we have I equals 0, it's just the original integral. So we cannot use 0. But if we have s, sorry. If we have s going to, if we have s equals 0, it just becomes 1 and sine x over x. This is the original one. So 0, not solution. What if we had infinity instead? That's going to be a bit tricky, but uh, as s approaches infinity, this is not rigorous or formal, but we're going to roll with it anyway because it's valid. So this, our original, which is the original I of s, this becomes negative infinity, negative infinity is 0. So everything in this is going to be big fat 0. All right. So what is I of infinity in this one? Arctan of infinity. Well, as s goes to infinity in that situation, arctan goes to pi over 2. So it's going to be negative pi over 2. This is a negative here, and then plus c. We know this is 0. Adding pi over 2 to both sides, we get c equals pi over 2. And that's our c right there. So I of s equals negative arctan s minus pi over 2. And since s equals, what is it earlier? 0. I meant pi over plus pi over 2. Since s equals 0, I of 0, or our original integral, is pi over 2. Since arctan of 0 is just 0, yeah, just makes pi over 2 right there. Very nice. 49. Sine squared x over x squared dx. This looks like the one we just had earlier, but it's a bit different. So how are we going to solve this? Let's use integration by parts. So the I plus minus to set up. Remember this one? Sine squared x and then 1 over x squared here. Sine squared x, we get 2 sine x cosine x. 1 over x squared, we get negative 1 over x. So diagonal is the integral first. So sine squared x over x negative. From 0 to infinity, what is this? Well, since sine x over x here on the bottom, oh yeah, sorry, I just spaced out on it. Uh, infinity on the bottom becomes 0, minus, and then if this is goes to 0 plus, since this is positive infinity, this is 0 plus, or just 0, because there's a limit here. What does the sine squared x over x? If we put 0 in both of these, is 0 over 0, so that's undefined. But the limit, what's the limit of that? We know that the limit of sine x over x as x goes to 0 is 1, right? We can use that here, but there's sine squared x, so there's another sign here. So we just have to multiply sine x over x by another sine x to get sine squared x over x. And the limit as x goes to 0 is very easy. This goes to 1, this goes to 0. The limit is just 0. So 0. So this term is just 0. The second term is the one that's important. 2 sine x cosine x over x as x goes from 0 to infinity. How do we do this? Well, 2 sine x cosine x is a trigonometric identity, right? Sine 2x. So we can put sine 2x here over x here. And we want the input of sine to be similar to the denominator. So we just put 2 here, but at the same time, we multiply by 2 in order to cancel it out. So here we have our equation. Yeah. So how can we solve this? Integration by substitution. Very easy for now. So 2 dx equals du. That means we have 2 dx here. So that's very good. The limits. So x equals 0, u equals 0. X approaches infinity, u also approach infinity. 2 times infinity is just infinity. Uh, don't think too much about it. Sine u over u, and then 2 dx becomes the u. And we know this is pi over 2. So that's the answer. Pi over 2. That is the original, yeah. And 0 is the other term. So pi over 2 is the answer. Easy as that. Now here is something that's more difficult. Sine cube x over x cubed. Intuition says it's pi over 2 again. But let's see. Let this be I. And I of t this time is sine cubed of tx over x cubed. So t equals 1, original equation. Let's find the derivative with respect to t. Derivative of this is 3 sine squared of tx times derivative of sine, which is cosine of tx. Derivative of tx, which is going to be x. On the bottom is x cubed. All right. So this x cubed on the bottom, we can cancel that out. That becomes 2. And what else can we do? Sine squared we can produce 1 minus cosine squared there. So we can do this. And I swear this is all leading to some great answer. It's not just random. Uh, and there we go. Let's separate the 1 and cosine term by distributing. So from 0 to infinity, 3 times 1 times cosine tx is 3 cosine tx minus uh, cosine cube of tx over x squared times 3 here, like that. Hmm. So an identity we can use is cosine of cube x. You know cosine squared x as cosine 2, 1 plus cosine 2x over 2, but cosine cube of x, uh, just if we use theta actually. So cosine cube of theta is 1/4 cosine of 3 theta plus 3/4 cosine theta. That's that. So what we can do now is replace this cubed with this cosine 3 theta plus 3/4, whatever. So on the first part, let's not separate. Let's put the 3 on this. Let's join the integral, the fraction. So 3 cosine dx remains. This is now this. So minus 1/4 cosine of 3tx minus 3/4 cosine tx. Yes. Oh, the 3 is removed here. There we go. So yeah, if you pay attention, cosine tx minus 3/4 x is 1/4, 1/4 cosine tx. So we can put the 1/4 on one side, on the left side, we get 3/4 on that side. So cosine dx minus cosine of 3tx over x squared. We're not even finished yet, according to this. because what we're going to do next is a bit horrifying. I prime of t, remember? Double derivative. And this is where it gets banana. We get a bit bananas, but you can see where we're going after this one. Trust me, trust me. So 3/4 remain. On the inside, cosine tx derivative is negative sine tx. And I think oh, and then we multiply by x since it is the derivative of the inside. The negative negative is positive, and then 3 sine 3 dx. 3 times x over x squared. The 3 is from the derivative of 3 dx with respect to t. So it's 3x. There you go. I just separated it. We can cancel this and just that. There we go. Hold on. Negative 3/4, and then the first part, sine tx over x. And then we add 3/4 of the second part, which is actually 9/4, since it is multiplied by 3, by sine 3 tx over x. Oh my god, so long. So from here, we can use integration by substitution. Let's just try using a pattern we know earlier. From here, sine 2x over x, we did all this in order to arrive at pi over 2. If 2 was different, like for example tx, it would be the same result, right? We just replace 2 with tx, t, or 3t. Sorry. So we just put t, and then t here. This would be same. Pi over 2 would be the answer. So this thing is just pi over 2, as well as this. Again, just place the 2 with 3t. The 2 cancels out anyway, so it doesn't matter. Oh my god. So 3/4 times pi over 2 plus 9/9 over 4 times pi over 2. What is the answer for that? I prime prime of t is, and this is negative 3 pi over 4, 9 pi over 4, 8, sorry. So what's going to be the answer? Uh, so we can do pi over 2 here, and then 9 over 4 minus 3 over 4. That's going to be 6 over 4, which is 3 over 2. 3 over 2 times 2 is 3 over 4. So 3 over 4 pi. This is I prime prime of t, which is nowhere close to I of t. So you need to find the antiderivative. So I prime of t equals 3 pi over 4 t plus c1. Do we know what c1 is? Not yet. Do we know what I prime of 0 is? Okay, so let's go back. I prime of 0 here. Hmm. I prime of 0 is 0, I think. Hmm. Ah, see here. Sine of tx times x squared. That's just 1, I think. That's just 1, since here we go. Sine x over x, the sine squared over x squared, and then the limit as x goes to 0. Let's just do sine x over x's, right? Let's just sine of x times sine of x over x. So it's just 1 times 1, which is going to be 1. And there's the t here. There's the t here, which is, guaranteed to be, this is going to be messy, but that doesn't matter. What matters is that the x squared on the bottom is gone. It means that with cosine 0. Whatever. Let me skip over some work. I of 0 equals 0. All right. So there's some justification in why I of 0 is 0, but I'm not going to go into it today. Too boring. I think the infinity has something to do with, but it's 0. So what now? Well, in here, if I of 0 is 0, this becomes 0, and what remains is C1. So C1 is 0, so just gone. So I prime of t is 3 pi over 4, my god, t. Then I of t is 3 pi over 8 t squared plus C2. Since we have another constant, oh my god. I of 0. So let's go back to the beginning. I of 0. If this was 0, sine of 0, x over x cube. I get it now. Oh my god, I am very, very not good. This becomes 0, so everything is 0. That's why it's 0. This also becomes 0, so it's just gone. The area is just 0. Sorry for being confused there. I have 0 is 0. And then this becomes 0, so this is just C of 2. So C2 equals 0. That means I of t is finally 3 pi over 8 t squared. Oh my god. And since t equals 1 in the earlier example, in the original, I of 1, which is the original integral, is 3 pi over 8. That is the answer. All right. So the next question is the integral or the double integral of xy dA, where R is the region enclosed by the x-axis, the y-axis, and the line x plus y equals 2. This is a multivariable integral wherein the bounds is not just from 0 to 1 or something like that. It's actually a 2D area. So the x-axis is this, the y-axis is this, and the line x plus y equals 2. We can think of it as y equals negative x plus 2. So 2 would be around here maybe, and then negative x would look like that. This would be the point 2. So x equals 2. This is y equals 2. Oh, there we go. Y equals 2. Um, actually, yeah, x equals 2, y equals 2. So that's going to be where our region is. So it's enclosed by the x-axis, the y-axis, and the line x plus y equals 2. This is referring to, of course, this bit of area right here. So that's going to be our area of interest. Now, from here, we need to find out what are uh, our bounds. So it's a double integral. So let's set it up, and then we set xy here, and then dx dy. Or you could do dy dx, but I will prefer dx dy. Now, for the x values range from 0 to infinity, right? But in here, it's from 0 to 2. But it can also be from 0 to here. So, in the x direction, it's in this direction. It goes from x equals 0 to this, which is x equals 2 minus y. All right, this is another form of saying x plus y equals 2. So x equals 2 minus y. So it is from 0 to this line, which we can describe as 2 minus y. For the y values, it goes from 0 to, to 2. Hold on. Let me, oh, 2 minus y. Let me erase some detail in here. Oop, too much detail. Still too much detail. Not erase it without, yeah. There we go. So, x, we have covered it from 0 to 2 minus y. So what it's going to cover is actually this entire thing, including the negative 1. That's the bounds of 0 to 2 minus y. But we only want this bit of area here. We don't want this. We don't want this. So we only want from 0 to 2, which is this bit of area right here. All right, we don't want the negative bit from negative infinity to 0. We only want 0 to 2. So that those are going to be our bounds. And from here, we can integrate like we usually do, except we're doing partial integration in which we ignore y, or we consider y as constant, like partial derivatives, right? So the integral of xy is going to be x squared y over 2, since that's we pretend that y is a constant, right? So we set the bounds from x equals 0 to x equals 2 minus y. And then we integrate that from 0 to 2 in the dy world, the y world. There you go. Now from here, we can actually just uh we can uh we can substitute 2 minus y in here. There you go. Over 2. And then for the 0, when x equals 0 in here, everything is just 0, since 0 times anything is 0. So we're not going to write that in. Then from 0 to 2 dy. From here, you can use your calculator or you can solve this on your own. I'm just going to use my calculator. This is apparently 2/3. All right. But we can still solve this using manual. So let's try using manual. Uh 2 minus y is 4 minus y 4y plus y squared. Multiply that all by y and then 1/2. All right, we can put that outside so we can integrate like that. Dy in here. From here, we can multiply y. So 4y minus 4y squared plus y cubed. Then dy from 0 to 2. Integrate 4y, we get 2y squared. Integrate 4y squared, we get minus still 4 over 3 y cubed. And integrate this, we get y to the 4 from 0 to 2. And then, of course, we have to multiply all that by 1/2. From there, we can substitute 2 in here. Is For 0, everything in here has a y, so it's all going to be 0. So we're not going to have a problem with that. So we're just going to substitute 2. 2 times, uh, hold on. 2 times 2 squared, that's going to be 8. 4/3 multiplied by 2 cubed is 8. And then we add 2 to the 4, which is 16 over 4. Okay, so this is 8. This is going to be minus 32 over 3 plus this is going to be 4. All right, so let's combine. So 8 plus 4 is 12 times 3 over 3. So denominator is 3. We get 36 over 3. So it's 36 over 3 minus 32 over 3. That's going to be 4 over 3. Don't forget the 1/2. We get 2/3, which is exactly we need. There we go. Answer is 2/3. Question number 2. The integral as y goes from 0 to infinity. The integral as x goes from y to infinity. And then e to the negative x squared dx dy. Now, e to the negative x squared, that reminds us of root pi, but this is not that kind of problem because this is now two-dimensional. Let's start by defining the bounds. So from our, let's draw it, there we go. One of the bounds is x equals y. So we have to draw x equals y in there. This is x equals 0, which is just the y-axis. Infinity is, well, up to infinity. There you go. So what does this mean now? Hold on. Now then, the bounds of x goes from y, so x equals y, up to infinity. And the bounds of y go from 0 to infinity. So this can go anywhere starting from here. So the area starts at that, and then it goes up to infinity. If it was negative infinity, we would include the one on the bottom, but we don't include that since it is only from 0 to infinity. So let's make it clearer, and there we go. Uh, Going to infinity and then infinity. Yeah, so these are our bounds. All right. Now, e to the negative x squared like this, we can't integrate this because it is a non-elementary antiderivative. It contains the error function, which is a function defined by this. So it's not going to be very helpful. What we need to do is to switch the dx and the dy. How are we going to do that? Carefully. So we want the integral from dy dx, e to the negative x squared. This is easier to integrate because e to the negative x squared is just a constant in the y dimension. So now, what are going to be our bounds? Note on this, we cannot have the outer bounds be a function. So something like that is not advisable because actually something like that is not advisable because at this point that is the final answer, which is going to be a number. And having a variable on the outside means that we're not going anywhere. So we need a variable on the inside, and on the outside, we just need constants so that the answer later is going to be constant, like what an integral should be. So from here, let's look at the y. So on the y-axis, it goes from here to here, right? So from 0 to y. So every part of it goes from 0 to y. It's not from y to infinity, of course. That's not the thing we want. We want 0 to y. For the x-axis, we want from 0 to infinity, right? We don't want this extra bit. We just want from 0 to infinities. So that's what we're going to place here. Now, this is easier to integrate because this is literally just a constant in the y dimension. So that's its integral from 0 to y. And then we integrate that from 0 to infinity in the dx. All right. Oh, 0 to x. Sorry. This is x. Okay, so from 0 to x, this is y equals x. I forgot about that. Sorry. There we go. From 0 to x. Okay. This is y equals 0 and y equals x. Okay. If we substitute 0 here, this would be 0. So we just ignore that. So this is going to be x e to the negative x squared dx. And integrating that is easier than the other one since this is elementary. Uh, I don't think we need to integrate. I don't think we need to substitute by parts since we already know how to do that. But uh, shorthand would be, let's move the integral sign a bit farther. We want there to be negative 2 in here. Why? Because the integral of this is negative 2x, right? But we need to multiply by negative 1 half so that we don't get into trouble, right? So this is still the same from the earlier result. So now we integrate negative 1 half, and then the integral of this we know is e to the negative x squared. Again, we follow integration by substitution and we just do it in our mind, right? In this level, we do have to do mental mathematics at this rate. So in here, we need to substitute infinity in here. Usually, if you want to do this rigorously, you would do infinity. But let's just substitute infinity for all time's sake. So infinity in here, e to the negative infinity is 0. All right. If you don't believe that, you can plot the graph of e to the negative x squared. It looks something like that. So at infinity, it is 0, right? Then we subtract by whatever 0 has in store for us. So negative 1 half times e to the negative 0 squared. This is going to be 1. Negative 1 half is positive 1 half, and that is our answer. Here we go. Question number 53. the integral of e to the negative x squared minus y squared dx dy if r is the unit circle. Let's draw the unit circle. So the unit circle, forgive my wonky drawing, but that is how I draw. The unit circle looks like this with radius 1. So this is x squared plus y squared equals 1. Now, we're going to do the polar coordinates here. So this is rectangular. We need to do polar. All right. Uh, Polar substitution works like this. X equals r times cosine of theta. Y equals r sine theta. Okay, why is this the way it is, right? So we draw a point from the origin to the circle that has a radius of r. For in this case, it is 1. Well, let's just pretend it is r. What is the x and y component of this radius? Well, we have an angle theta here. All right, that's our second coordinate for polar coordinates. So the x is r cosine theta, if you remember your trig, and the y is r sine theta. So this is why it is, right? Because sine theta is the opposite of this, so r times the opposite is the y value. And of course, r times the adjacent is the x value. From here, we can use the Jacobian determinant trick. All right. So we can plot a table in here. On the top, dr and d theta. On the bottom, on the sides, dx up and dy. And then we can have a matrix. Hmm. So in here, we want dr over dx. Or, hmm, sorry, dx over dr. Dx over dr, all partial, is dx over d theta, dy over dr, and dy over d theta. All right. And then we want to find the derivative of that, to find the Jacobian determinant. That is the name of what we're doing. Okay. This is dr, sorry. Okay, so the partial x over r is going to be the partial derivative of this with respect to r. Differentiating r, that's just 1, so it's cosine theta, since that is a constant in the r dimension. For y, same thing, but there's no sine theta. For dx over d theta, in here, r remains since it is a multiple, but cosine theta is derivative differentiated, so it's negative sine theta. And for dy over d theta, that's going to be r cosine theta. From here, we do the determinant. You can search the determinant, but it is essentially if you have a determinant of this matrix, we multiply like this, cross multiply, and the determinant AD minus PC. The three-dimensional determinant, which is a 3 by 3 determinant, is much complicated than this, and usually you can do that on a calculator. But in here, we need to do it manually. So yeah, maybe in a future video, I'll do determinants. But in here, our cosine theta times cosine theta is r cosine squared theta minus then negative r sine squared theta. So we have r cosine squared theta plus sine squared theta, which is just 1. So we are left with r. What are we going to do with r? Well, after finding the Jacobian determinant, we can use that to substitute. So remember, in integration by substitution, we we do the, for example, sine x equals u sub, right? Then we do cosine x dx equals the u. Like we need to do that in order to make our calculation easier, right? In here we do the same thing, except we find the Jacobian determinant. So this actually means that dx dy equals r dr d theta, right? So it's the same concept with integration by substitution, just one dimension higher. All right. Now, let's go back to the circle and we will now set the bounds for the unit circle in here. So since this is dr theta, we need to go from dr first. So dr is the radius. So if we're trying to find the area of this, if we're trying to find the integral in this area, in this whole area, we need to find the radius from 0 to 1. There we go. And then the angle, theta, well, it's the entire circle, so we need to go one rotation, the full rotation, or from 0 to 2 pi. All right. The next is we just put our function e to the negative x squared minus y squared. We know that x is r cosine theta and y equals r sine theta. Where did that come from? From x squared plus y squared equals r squared, right? You can even check if this is true in here. And yeah, it is true. You can check it on your own, but we're going to think of this as e to the negative then x squared plus y squared. What does that remind us of? E to the negative r squared, dr d theta. All right. And now we integrate just like before. Sorry, re to the negative r theta, r squared. That is very familiar to us. In the previous example, we already did that. So, so we integrate re to the negative r squared. That's going to be negative 1 half e to the negative r squared from 0 to 1. Correct? Yep. Sure. Yeah. So we just have to substitute everything we need. So we just substitute everything we need. Sorry for spacing out. Uh, negative 1 half e to the negative 1. Then we subtract by negative 1 half e to the 0. All right. Okay. From here, this is sure. Uh, this is negative 1 over 2e. This is plus, well, this is 1, so this is 1 half. Let's combine it so it's easier to read. Multiplying this by e, we get e on top as well. So we get 2e on the bottom. So e minus 1 over 2e. And then d theta. Notice that e is just a constant. And we don't have any theta in here. So the integral of just a constant is that constant times theta, right? Sorry. Shouldn't have written this. Okay. So theta from 0 to 2 pi. Now, e minus 1 over 2e can just skate there. And theta, it's 2 pi minus 0, so it's just 2 pi. From here, let's cancel 2 here. So there we go. So this becomes e minus 1 to the power pi over e. If we simplify, we get pi minus pi over e. That's going to be our answer. That's a beautiful marriage of pi and e, even though it's kind of meaningless. Uh, there we go. So the same integral, but S is a circular strip, similar to a donut, with the major radius being 3 and the minor radius being 2. What does this mean? If earlier we had the unit circle, now we have a donut. So this is what a donut looks like. This is not a torus because tori are three-dimensional. This is the circular strip. I am looking for. So the integral is located inside here. So we already know how to integrate from earlier. The same question essentially. We just put it in the polar coordinate system. So let's set it up without even knowing the bonds. So r d theta, e to the negative r squared, right? Now, the angle is easy. Since it is a circle, it goes from 0 to 2 pi, right? The radius is a bit tricky, but it is also easy. This is not centered, so I'm sorry for that. But we know from here, the minor radius is 2, so it's going to be 2, and the major radius or the radius of the entire thing is 3. So the radius we want is a circular strip, so from 2 to 3. We don't want 0 to 2, we don't want 3 up to infinity. We just want 2 to 3. Now, let's do the same thing as before. So set up the integral here, but we already know how to integrate this one. So this is going to be negative 1 half e to the negative r squared from 2 to 3 and then d theta. All right. So there we go. And we just substitute 3 in here. So negative 1 half e to the negative 3. Uh, yeah, negative 3 squared so negative 9. Uh, Minus negative, so plus 1 half e to the negative 4. Okay. So in order to make this much pleasant looking, we multiply both of these terms by e to the 9 over e to the 9. What happens here? Well, bottom becomes 2e to the 9. On top becomes, well, minus 1 in here for this term. And for that term is going to be e to the 5. And of course, we have to integrate this theta. And of course, this is just a constant. A different constant from before, but nevertheless a constant. So there we go. So 0 is just 0. 2 pi becomes 2 pi. So becomes e to the 5 minus 1 over e to the 9. And then the 2 gets cancelled like earlier. So that becomes just pi. And that's our answer. All right. Question number 55. The integral of secant to the power 6y dy dx. As y goes from arctan x to pi over 6, and as x goes from 0 to 1 over square root of 3. So let's have the bounds yet again. So it looks something like this. There we go. So arctan x looks like this. You can use Desmos to do that. Something like that. Yeah, there you go. It's not that good of a drawing, but it's close enough. And y goes pi over 6 is somewhere in here. Now, what is this point? So, tangent of pi over 6 or 30 degrees is sine of pi over 6 over cosine of pi over 6. Remember, sine of pi over 6 is 1 half, and the bottom one is root 3 over 2, or 1 over root 3. So, this is 1 over root 3. So from y, it's arctan x to pi over 6. So it's that way. And for the x, it's from 0 to 1 over square root of 3, which happens to be this point right here. So the area of the region is this. We're trying now to find the integral on that area. All right. So dy doesn't make it easy because this is a nightmare integral. So instead, what we're going to do is to switch dx and dy. Yes, that might make it easier. So we want dx dy. Why do we want this? Because integrating secant to the 6y dx is much easier. The integral that's just x times secant to the power 6y. Again, secant, the y is a constant in the x domain. All right. So we need to set the bounds, but what are those bounds? So from x, we go from 0 to is this unfamiliar graph. This is y equals arctan x, or if we want x, that's going to be tangent y. So from 0 to tangent y is our x bounds. From for y now, because if 0 to y, this would also count, but we don't want that. So we only want from 0 to pi over 6. So it's going to be our y bounds. All right, now that we got that settled, we can finally do some math. Okay, so secant to the power 6y dx, that's going to be x secant to the 6y from 0 to tangent y. And then dy from 0 to pi over 6. All right. Substitute tangent y here, we get tangent y secant to the power 6y. 0, it just becomes 0, so we don't have to take care of that. There and there. How do we integrate this? Well, actually, we can do this way. So secant to the power 5y times secant y tangent y. Does this look familiar to you? 6 dy. If Okay. So we can substitute secant y as u. That's for example, and the derivative of that is secant y tangent y dy, which is exactly this. This is going to be du. Okay. The bounds now. So if y equals 0, u equals secant of 0. What is secant of 0? That's going to be 1. Right? Since secant is 1 over cosine. So 1 over cosine 0 is 1. Alright. How about 1 over cosine of pi over 6? We know cosine of pi over 6 or 30 degrees is square root of 3 over 2. So reciprocal of that is going to be, hold on, 2 over root 3. So that's going to be the upper bound. So from 1 to 2 over square root of 3, which I have been told is greater than 1. Okay. U to the 5, then the u. Alright, from earlier. So now is u to the 6 over 6. That's the integral of u to the 5. And then from 1 to 2 over square root of 3. So 2 over square root of 3 to the power of 6 times 1 6. We subtract that by 1 6. 1 to the 6 is just 1. So over 6 is 6. Alright? Great. So this part becomes 2 to the 6, which is it's 2, it goes 2, 4, 8, 16, 32, 64 over square root of 3 to the 6. Okay, square root, so we have to multiply the 6 by 1 half. So it's 3. So 3 cubed is 27. We multiply by 1 over 6. And then subtract by, okay, I got that wrong in my notes. Subtract by 1, actually. There we go. From here, we can subtract 27 on the numerator. That it. Then we do that. Subtracting 64 minus 27, we get 7 and 3, 37 over 27 times 1, 6. All right, so 27 times 6. Let me just do quick math over here. That's 162 according to my calculations. If it's wrong, I'm going to be ruined. So 37 over 162 is the answer, and yeah, that's going to be the answer. Because I did wrong on that one. So yeah. See you in the next part. There we go. So our next topic is going to be the Laplace transform. So the Laplace transform, in normal terms, it is used to convert something from the time domain to the frequency domain. So it is the brother of the was the older brother of the Fourier transform, which you may know from electronics or whatnot. But the definition of the Laplace transform, uh, which we apply to a function, is going to be the integral from 0 to infinity. I can see that of e to the negative st f of t dt, where uh s is theta plus j omega. Okay, so what do these letters mean? This is just the real part, and j is the square root of negative 1, more commonly known as I, but j is often used in electronics in signal processing because I is usually used for current. So we can use j. We can also use I. It's up to you. All right. So knowing that, and I think last time I also discussed the Laplace transform, let's look at the common Laplace transforms that we all need to know. So the Laplace transform of a constant is 1 over s, and e to the at, its Laplace transform is 1 over s minus a, and Laplace of t to the n is n factorial over s to the n plus 1. All right. So there's a fundamental difference between a function and a transform. A function converts an input, so for example, 1, into an output, which is f of 1. A transform, uh, a transform changes domain. So from time domain, that's going to be f of t. We transform it into the frequency domain. So this is going to be Laplace f of t or big F of s. The convention is to put the capital of the function letter into the Laplace letter, and s is the variable. S is a complex variable. So this is a function from input to output, and from this is the transform from domain to domain, time domain, frequency domain. And the inverse Laplace transform is also similar to this, but in the other directions, from frequency domain to time domain. We're going to be discussing both. The Laplace transform e to the at f of t dt. Now, what does this look like? So Laplace transform, it looks like this. E to the negative st and then e to the at f of t dt. All right. So remember the Laplace transform uh, is e to the negative st f of t dt. This can also be described as f of s, a big F. All right. Now in here, our this we can combine, right? So this becomes e to the at minus st, or let's just put it in the other way around, st plus at. So we can combine this, we get t, and then negative s plus a. But I want the negative outside, so I'm going to put it like this, and then s minus a right here. And let's rebuild the rest of the Laplace transform. Right. This looks familiar to this, with the only exception being the s becoming s minus a. And actually, we can use the Laplace transform in here, but we shift the s a units forward. So this is going to be s minus a instead of s. So if you see something like this, you first look for the Laplace transform of f of t, and then you shift the s a units, how a units backward, I guess, something like that. We're going to be seeing that a lot later on. Next, y prime of t. So this is going to be uh, integral of 0 to infinity e to the negative st y prime of t. So if this is only y, this is going to be y of s. So big Y of s. Sorry, my camera is blocking. Yes, there we go. So this is going to be y of s. But this is prime now, so this is a first derivative. So we need to somehow get the antiderivative of that. Let's use the integration by parts DI method. All right. So e to the negative st goes here. Y prime goes here, of course, because we want the integral of this y. But we need to find the derivative of this. So negative s e to the negative st. Find the answer. We multiply this. And then find 0 to infinity. All right. And then we subtract the integral of this. So minus minus is plus 0 to infinity of s e to the negative st y of t dt. This one, e to the negative infinity is 0. And then y of 0 is just y of 0. While this becomes 1, since e to the 0 is 1. Alright? First part. Second part, we know s is a constant in terms of t, so we can bring that outside. And what remains is this integral, which if we look earlier, that is going to be y of s, which is the Laplace, right? So we have negative y of 0 here, plus s, then big Y of s. That is the integral. All right. A little bonus. Bonus. Laplace of y prime prime of t. We already know the Laplace of y prime of t. We just have to upgrade the derivative by 1. So if this is the Laplace, which is just the lower derivative. So from first derivative to zeroth derivative. From here, second derivative becomes the first derivative. Something like that. Plus, and then s, then the Laplace of y prime. The Laplace of y prime we already know. So let's rewrite this. Uh, so the Laplace of y is just this. So we just multiply by s, we get minus sy of 0 plus s squared big Y of s. That is the second derivative in Laplace form. The Laplace of sine uh, t plus cosine t. Let me check if that's correct. Oh yeah, it is. All right, so it is sine of t, but we're going to be finding the overall uh formula. We know that b equals 1. All right, so how do we solve this? Earlier, from intro to LT, we know that e to the at equals 1 over s minus a. Now, oh, not that one yet. Uh, we know that e to the I theta is cosine theta plus j sine theta. Or if we want I, let's just put I instead. So it's easier for us. There we go. Now, from here, we can take the Laplace of both sides. There we go. So the Laplace of this is 1 over s plus I theta or j theta. Okay? That's going to be the Laplace of this one. But I on the bottom, we don't want that. I wants to be on top. So so we multiply by the conjugate. So we multiply by s minus I theta. Okay, on the bottom, this is a difference of squares. So s squared minus I squared theta squared. So I squared is negative 1. So minus minus is plus. Plus theta squared. Am I right? Oh, no, no, no. Uh, I'm wrong about. Sorry. Let me rephrase that. I was confused for a moment. Let's just yeah, let's do that instead because it generates this. Uh, let's just use J because why not? I actually use I because I already used I. So there we go. We replace it with BT. I replaced with theta earlier and I got confused. Okay, so this becomes 1 over S minus IB. Here we go. And then uh, in order to rationalize or rationalize, in order to put I on the top, we multiply by its conjugate. And since this is the sum of the product of the difference of two squares. No wait. Oh, yeah, this is just sum of was a difference of two squares. So s becomes s squared, then that becomes positive b squared. Because I squared is negative one. So negative of negative b squared is just positive b squared. On top is s plus ib. Alright. We can separate this into s squared plus b squared plus I times b over s squared plus b squared. If we line up the Laplace of cosine bt plus I sine bt, and we realize that I is just a constant and it lines up here, we can see what lines up, right? So cosine of bt is s over s squared plus b squared, and sine of bt equals b over s squared plus b squared. We just have to add them to find sine squared bt plus sine squared sine bt plus cosine bt. Sine bt is b over s squared plus b squared. Cosine bt is s over s squared plus b squared. So because b plus s over, let's just put b squared plus s squared here. We know b is 1, so for sine t plus cosine t, the Laplace of that is going to be 1 plus s over 1 plus s squared. Next, our good cousins, the hyperbolic sine and cosine. Now we do know that since ct is e to the ct minus e to the negative ct over 2, and cosh ct is e to the ct plus e to the negative ct over 2. And if we add them together, we get this becomes gone since it is positive and negative. Then 2e to the ct over 2, or just e to the ct. All right. Since c equals 1 in this example, so we're trying to find the Laplace of this, which is going to be e to the t. This is simply 1 over s minus 1. That's the answer for that. Next, the Laplace of the unit step of t minus a f of t, where this is the unit step function. So what's the unit step function? Well, the unit step function, just call it that, is 0 when x is negative and 1 when x is positive. It looks like this. Uh, it looks like this, actually. There you go. So this is the axis. There we go. So like that. So this is 0, this is 1. Okay? Now, hold on. Now in here, we can define the u of t minus a, something like this. If t minus a is less than 0, then the entire thing is 0. If it is greater than 0, and then the entire thing is 1. So in essence, here's the thing. If this is a, this entire thing is just 0, and then this is 1 from a to infinity. All right. So now in here we're given this. So whatever your f of t is, it has to follow this. So for example, this is f of t. Something like, let me draw an example. And then something like that. All right. So combining these two together, this is A. Let's just say this is A. Uh, Let's just put them on the same thing. Combining these two together, if you were to multiply this, the entire thing before A becomes 0. So this becomes 0. This becomes like that. All right. Right, this was 0. This is undefined in here, and that's what you get left. So this is mu of t minus a. Right, so that's what it does. Now, mm, what we have to do next is to define, we have to define the Laplace transform for this. So let's put it in the Laplace transform. From 0 to infinity of mu of t minus a f of t e to the negative st dt. All right. So from negative infinity to a, whatever a may be, it is just 0. So we can ignore from 0 to a. This is assuming a is positive. If a is negative, it still works. Just that a is now on the left side, not the right side. And actually, we have an explanation of that. And so we just assume a is greater than 0. If a is less than 0, it's a bit wonky, but it still works, I guess. And so by that I mean let's just think about it later. All right. So mu of t minus a, this becomes just the bounds. The bounds are the only thing that changes in this thing. So e to the negative s the f of t remains the same. All right. Now the bounds are different because again from 0 to a it's just 0. All right. So we don't have to find the integral there. Now here is an integral that looks like the Laplace transform, but it's not the Laplace transform. We need from 0 to infinity, not a to infinity. So let's substitute. Let u equals t minus a. Why do we do that? Because if we have infinity in here, u remains infinite. But if we have a in here, u becomes 0. And those bounds are good for Laplace, right? All right. So we need to substitute t for something else. So u equals t minus a, u plus a equals t, right? So t becomes e to the negative s and then u plus a. Oh, and by the way, derivative of u is du, derivative t minus a is dt. There we go. Just forgot. F of what is t now is u plus a. And then du. Let me do a little some things here. E to the negative sa is a constant. We can put that outside. E to the negative su f of u plus a du. Now we call u a dummy variable. What is a dummy variable? On the start we have 0 to infinity of t. In here, we have 0 to infinity of u. It doesn't matter if this is t or u. We can substitute, no, we can replace u with t and it would not change. This means that this can be equal to negative, and there you go, e to the negative st f of t plus a dt. So this is the same as this, essentially. All right. We might say, well, we subtracted a from that, but the bounds are still the same. We've adjusted the bounds, right? The bounds are the same, and well, u doesn't depend that much on t, or something like that. Just remember, just know that it is a dummy variable. We can substitute t. Because if you analyze this integral, you find the integral itself. It wouldn't matter if it's u, if it's a, if it's t, if it's gamma, or whatever. So that's what a dummy variable is. It's just a variable that you can change. Yeah. So this is also the Laplace transform. The Laplace of f of t plus a. So when we're dealing with the unit step in this way, we have to shift by a units, right? So something like that. That is the Laplace transform. The Laplace transform of the Dirac delta t minus a times f of t, where delta is the unit impulse or the Dirac delta function. What is the Dirac delta function? Well, we have the normal distribution, something like that. All right. This is symmetric along the x axis, no, no, the y axis. So whatever's on the left is the same as on the right. All right. And the center is x equals 0. Now, I want to thin this out such that more of the area is concentrated in the middle. All right. But I want to keep the same area. So let's say the area of the entire thing is 1. All right. The area of this, or the integral of this, should also be 1 across its entire domain. Now let's take this to the extreme. So let's take something like that. Uh, that's a bad drawing. Let's take maybe that. Right? It's very thin now, but the area is still 1. All right. The most extreme version of this is that everything is 0 except for let me just draw this properly. Except for x equals 0, where it is infinite, and yet the area is 1. That is the Dirac delta function. Delta x is equal 0 if x is not equal to 0, and infinite if x equals 0, approaches infinity. Right, so and the integral from from negative infinity to infinity, uh, the Dirac delta uh, is always 1 because that's the definition of the Dirac delta function. So that's the short explanation of that. Now, the this is one fact of it, but another fact is the integral of the entire thing. Uh, of this is going to be f of a. Right? So that's going to be the integral of that. Okay, so now watch out because we're going to do the Laplace now. The Laplace transform of delta of t minus a f of t, no, no, sorry, f of t e to the negative st dt. Now the integral from 0 to infinity of delta of t minus a f of t e to the negative st dt. Now we have to be careful that a is greater than 0. All right, 0 to infinity or greater than or equal to 0. Because from 0 to infinity, it only encompasses this. And if, for a example here, if that's where the infinite part is, it needs to encapsulate that in order to have the area. In order to have an area or a Laplace, a valid Laplace transform. And using this principle in here, we can already know the Laplace transform of this. So it's going to be e to the negative sa times f of a. Uh, there we go. That, that is the Laplace. All right. Next, the Laplace of t to the f of t f of t. All right. So we just put the Laplace here. So 0 to infinity of t to the e to the t times e to the negative st test f of t dt. All right. Uh, yeah. All right. Let me just check. Yeah. All right. No. Well, crazy or anything. There we go. All right. So in here, this is a problem for now. So how can we solve that? Hmm. Let's go to the original Laplace transform. What is the definition again? So 0 to the negative s t f of, oh my God. Sorry. Infinity here, e to the negative s t f of t dt. I haven't got much sleep in a while, so this happens. We find the derivative in here in relation to s, and in here we find the partial derivative with respect to s. On this side, the partial derivative is negative s e to the negative st. Oh, sorry. All right. Sorry, not quite right. It's negative t e to the negative st f of t uh, dt. Right. This is similar to Feynman technique that I've shown earlier, but it's quite different now. Hold up. So yeah, if you can check, this is valid. Now, the negative, we need to multiply by negative on both sides in order to remove it. So, negative d over ds f of s equals the integral of t e to the negative st f of t dt. And what is that? That is the Laplace of the f of t. All right, so the Laplace t f of t is just this. And as a bonus, if we were to extend that to nth power, there we go. That's going to be uh, ne negative 1 to the power n, because we're going to do that again. This multiplying negative. So we're going to do that again and again for how many n's there are. And then dn over ds the n. So the nth derivative, this means, of f of s. So that's going to be the general formula. Whew. 63. Laplace of f of t over t. So this is going to be Laplace from 0 to infinity of e to the negative st over t f of t dt. This is a bit more difficult, but let us observe that the integral from s to infinity of e to the negative ut du, sorry, equals negative e to the negative ut over t. Uh, as u goes from s to infinity. Substituting u, we get infinity, that's just 0, minus then negative e to the negative st over t. So everything becomes e to the negative st over t. And when you look at that, we have that right here. So now, we go here. We know that this and this is equivalent, so we can replace that. So s to infinity of e to the negative u t du, then f of t dt. All right, f of t, we can place that somewhere in there. All right, so e to the negative ut f of t du dt. Now, if it was dt first, that would be the Laplace, that would be close to the Laplace transform, right? So let's try switching it. Let's assume S is real for now. This can apply to the complex, but let's just assume that S is real for now because this gets a bit head scratchy after this. So this is the t-axis, this is the u-axis. Can you see that? Okay, not much. So here. So this means the u is goes from S. So let's say it's like here, S, and then it goes up towards infinity. While for t, it's from 0 to infinity. So that's going to be our bounds. Now, if we were to swap them, uh, we need to find yeah, we need to find the bounds now, the new bounds. There's nothing special in here. So it just goes from 0 to infinity in the t-axis, and then the u-axis, it still goes from s to infinity. So we just swapped it, as usual. Now, from here, this is the semi-Laplace transform in the U domain, which is far from the S domain, but we can make use of that. So this is f of u, not f u, that's rude. So from S to infinity, I got that from Black and Red Pen video. And yeah, du. So this is the answer. Yeah. You have to integrate from S to infinity what f of u is. All right, so that's going to be that. All right, next. L of f of t convolution g of t, where this is the convolution operation, whatever this is. All right, so so prepare your seatbelts. This is gonna be a bit long one. So the Laplace of that's too big now. From 0 to infinity of e to the negative st, and then the convolution, which is 0 to t e to the no, sorry, f of t minus v g of v dv dt. All right. Next step. Hmm, hang on. All right. So now 0 to t. So it goes from here and then it stops, right? What else does that? The unit step. But this time instead of t minus a, it's a minus t, or it's negative now since we want the negative form, right? A in this case is going to be t. All right. Hold on. Yeah, since this is now in the V domain, it is T is now V. It's a bit confusing. Sorry. Uh, so we copy this. Then mu of T minus V. Yeah. Because the domain is now V, and we want it up until T since this is 0 to T, right? So 0 to T, something like that. 0 to T, EV. And then dt. The bounds now can be 0 to infinity, from here up to infinity. Knowing that from t up to infinity, the area is just 0. So we're not going, so it's the same effect in that sense. All right, next. Forgot e to the negative st. Why did I forget that? G of v, we can put Actually, we need to swap v and t. Since this is just constants, 0 to infinity, 0 to infinity, we can swap them however we like. And it's good that they're also the same, so we can really easily swap them. All right. So g of v, we can put that outside like here, and then e to the negative st, uh, hold on, f of t minus v, mu of t minus v. All right. All right. So now, what is this? This is a Laplace transform, right? So this is the Laplace transform of f of t minus v, mu of t minus v. Okay. So what was the Laplace transform earlier? Let's go back to not that one. Not that one either. This one. So the integral is e to the negative sa, and then uh, Laplace of f of t minus a. Let's copy that and let's go to this. Oh, not that one. All right. Remember? Let's make it smaller. There you go. So this is the Laplace of mu of t minus a f of t. Right. So what we needed to do is to do this f of t plus a. Now e to the negative sa. So in a in this case is v, right? V in here, and so e to the negative sv, and then the Laplace of f of t minus v plus v. So that's just f of t, right? So t minus v plus v, so it's t, right? So that's it. And then don't forget that we are still trying to find the integral of g of v in here. All right. And then the v, since that's the one that's this one is f of s. This one is integral from 0 to infinity of e to the negative svg of v dv. Familiar? That is the Laplace transform again, but this time g. So big G of s as per convention. So that is the full integral. It turns out that convolution in the time domain or uh that operation in the frequency domain is actually just multiplication, right? And it works in the other direction. Convolution in the frequency domain is just multiplication in the time domain, right? So if you actually the tactic in finding the convolution of two equation or two functions is to turn it into the frequency domain version, multiply them, bring them back to the time domain. That actually works. So good job, right? Next, sine t over t. What is the Laplace transform of that? We already have the Laplace transform of f of t over t. Let's go back to question number 63. And this is the result. Let's bring it here since it is very relevant. All right. Big F of u. What is f? Sine of t. What is its Laplace? Well, it is 1 over squared plus 1, correct? Okay. Now, this is calls for the Laplace in the u domain. So instead of s, we're actually going to be putting u in here. And then we integrate from s to infinities du over u squared plus 1. All right. So this is now uh, arctan of s, right, plus c, because we still have a constant that we don't know about. Oh no, sorry. This is that's differential equations. I forgot. So arctan of u from sorry, in from s to infinity. I almost forgot how to integrate. Oh no. Arctan of infinity is pi over 2. minus arctan s. Now that is the correct answer. What happens when s equals 0? It's pi over 2. So the original integral would be e to the negative st uh, sine t over t dt from 0 to infinity, right? If s equals 0 or is that right? Yeah, if s equals 0, this becomes 1 and then just sine t over t. And we know that if s equals 0, it's just pi over. So that is one more knowledge if you want to unlock. And I think we, is that a question before? Yes, it is a question 48. Let's go back to question 48. Let's see if it corroborates. Yes, indeed it does. All right. And actually, what we did here is just the Laplace transform, but weirder. All right. It's the Feynman technique. The Laplace transform does the same thing. So it's actually really good. It's fun to see that the Laplace transform has other applications in integrals, and it's actually going to have applications in differential equations. Maybe we will see that later. And there we go. So for this next portion, we're going to be doing the inverse Laplace transform. Where in the Laplace transform, we went from the time domain to the frequency domain. Now we're going from the frequency domain or the S domain to the time domain. So I guess the dumb way to do that is to utilize a formula that is similar to the in a forward Laplace transform. But the smart way to do this is to recognize that these used to be, well, time domain functions that we inserted into the frequency domain. So let's start with this. The inverse Laplace of 1 over 4s minus. What do we know? Well, how about we try multiplying both the numerator and the denominator by 1, 4. What we get is 1/4 here over s minus 1 half. All right. So 1/4 is just the constant here, so we can put this outside. And then the inverse Laplace of 1 over s minus 1 half. What function has this as the Laplace transform? That's right, e to the at. All right, the Laplace of e to the at is 1 over s minus a. And a in here is just the 1 half here. So the answer is 1/4 e to the 1 half t. That's the inverse Laplace transform of that. Next, number 67. The inverse Laplace of 1 over s plus 1 and s minus 2. Now, the easiest way to do this is to partial fraction decomposition this. So what can we do here? So the inverse Laplace, so let's just put the inverse Laplace, then a over s plus 1 plus b over s minus 2. So the more famous method of doing this is the cover up method. So if we want to find the a, all right, we need to find the thing that makes its numerator 0, all right? So the thing that makes this numerator 0 is -1. And then we cover this up, and then we substitute -1 in here. So 1 over s, which is -1, minus 2. So -1/3. All right? So that's going to be our a value. For b, s equals 2, that would make it 0. Now let's cover this up. There we go. So 1 over 2 plus 1, that will be 1/3. Positive 1/3. Now, let's put these values as the numerators. So a is -1/3 and b is positive 1/3. Again, these are just constants, so we can put them outside. But in any case, this is the inverse Laplace of e to the at, where a is -1, right? So we can put -1/3 e to the negative t plus this is 1/3 e to the 2t. This is our answer. All right. Next question. Next question is this. Alright. 1 over s cubed minus s squared minus s plus 1. Hmm. How can we use partial fraction decomposition in here? How about we extract s squared in the first two terms, so it becomes s minus 1. And then we subtract negative 1 in here, so it becomes s minus 1. So we can do this instead. So Laplace negative 1 of 1 over s minus 1, as we know, and s squared minus 1. From here, we can gather the Laplace. Uh, oh, sorry. So actually we have two solutions. We're going to use this solution instead. So we know this is s plus 1 and s minus 1. So s minus 1 it has two entities here now, so that's going to have two. And we're going to decompose it using the following way. So a over s plus 1 plus b over s plus s minus 1 plus c over s minus 1 quantity squared. My notebook here has another way, but we're going to be using this method. So partial fraction decomposition. You can still use the cover-up method in a way, in some way, but we're going to be using the let's try using the yeah, we can try using the cover-up method actually. So what is A? A is the condition is s equals negative 1, right? Now we can cover up s negative 1. We can cover this up this. There we go. So now we get Laplace of 1 over s minus 1. Okay, no, not Laplace, sorry. 1 over, then s minus 1. S is negative 1 here, so negative 1 minus 1. All that's squared since there are two of them. So 1 over this becomes negative 2 squared, which becomes 4. And yep, it is 1/4. So A is 1/4. From there, yes. Let me just check this. Maybe it's yeah. Hold on. So now that A is 1/4, we can find B easily instead of doing it one by one. So, 1/4 over S plus 1 plus B over S minus 1 plus C over S minus 1 quantity squared. So now let's combine the sorry the so one quantity squared. So 1/4 we need to multiply by s minus 1 quantity squared. B we need to multiply by s squared minus 1 since we need to multiply s plus 1 and s minus 1. And C we just have to multiply by s plus 1. All right. So we know 1/4 here. So s squared plus 2s minus 1 times 1/4. Then plus bs squared minus b plus cs plus c. All right. This is equal to 1, which is the original numerator. All right. Let's gather up all the s squared terms, the s terms, and the constant terms. So s squared terms is b plus 1/4. So that becomes 0 since there is no s squared term in the original numerator. For the s, we got c, and we got plus 2 over 4, so 1/2. Yeah, 1/2. And that's going to be 0 again. For the constant term, we do have negative b, positive c, and negative 1/4. All that is equal to not 0, but 1. All right? So actually, you just need these two. So we know b equals negative 1/4 and c is negative 1/2. So, bless me. Hey. And yeah, that is the set of the thing that we need to find in here. I hope. Let me check. Oh, no, no, no. I'm sorry. There should be negative in here and then positive here. So it's in positive here and negative in here. Uh, So this is positive one half. I apologize, but that is our lineup now. One fourth, negative one fourth, and positive one half. All right. So let's recombine into something like this. Something like this. We copy that, we paste it down here, right? Slowly. Here we go. A, B, and C, we already know what those are. So A is one fourth positive. B is negative one fourth, so negative. C is one half. All right. This we know. What is this? This is one fourth e to the negative t minus one fourth e to the t. Now this is a bit trickier, but we can still solve it. All right. So how can we solve that? What has square on the bottom is the Laplace transform of t, tn. We know that is n factorial over s to the n plus 1, right? So so the Laplace of t itself, just 1 factorial over s to the 1 plus 1, which is 2. Right? We almost got that here, but we need one more element, which is the shifting. So this needs to be s minus 1 quantity squared, right? How can we do that? We just multiply by e to the at, in which case a equals 1, right? Because as we've shown earlier, the Laplace of e to the at f of t is f of s minus a. So that's how we're going to be tackling this. And there's one half, so we just multiply by one half. Then t e to the t. This is the answer. Great. Next question. 69. E to the negative 3s over s squared plus 4. Okay, so s squared plus 4, if that's the only thing, if the top is just 1, then it's easy. But now there's a numerator, e to the negative 3s. We need to find a way to get. So how do we get that? Hmm. All right. What we need is to find the Laplace first. So inverse Laplace of e to the negative 3s times, this would be great if it was 2 over s squared plus 4, right? We multiply by one half to make it unchanged. Because this is just sine. Sine of 2t, right? Yes, sine of 2t. Now, this is a bit difficult. Okay, so remember earlier that the Laplace of mu of t minus a, oh sorry, f of t, what did we learn about earlier? This is the Laplace of f of t plus a. And we multiply that by e to the negative s a. All right? We already have e to the negative s a right here, where a is equals to 3. All right? So we know that mu is going to be a part of this story. All right. What else can we do? So this is a bit problematic because it has plus a in there. But what if we subtracted the a prior? So instead of mu of t minus a f of t, we instead did t minus a and then f of t minus a. Like we did in the previous question, we get Laplace of f of t, e to the negative s a as well. All right. Since t minus a plus a is t, it just remains Laplace of f of t. And this is f of s, then e to the negative s a. And again, we know what a is already, right? So we have f of s, which is this. We have e to the negative s a, which is this. We can use this property of the unit step function in order to find the inverse Laplace transform. All right. So this is sine of 2t, right? This is the f of t minus a, right? This is actually f of t, right? This is f of t. We need f of t minus a. So this becomes sine of 2t, but t becomes t minus 3. So something like that. Okay? And then we just multiply by e to the u to the t minus a. Okay. So we know a is 3 already. So what the next step is to just multiply it by mu of t minus 3. All right? Then sine of 2t minus 6 to distribute the 2. Right? This is our answer. There you go. Right. To recap, I may have misplaced this. We know f of t already. This is the f of s. We know the inverse Laplace of this, which is sine 2t. But we have e to the negative sa, which requires which requires a mu of t minus a. Our a is already 3, so there we go. But we need f of t minus a since that would make us have the Laplace of s, right? So we need t minus 3 in here instead of t. So 2 times t minus 3. So that will be 2t minus 6. So this is our answer. Number 7, s minus 1 over s squared plus 3s plus 2. There are two possible solutions in here. The first I could possibly know is to use the sinh, I think the hyperbolic sign. But, oh, sorry. But the other one is to use partial fraction decomposition. So we're going to be using that one right now. So partial fraction decomposition. A over S. What is this? So this is S plus 2 and S plus 1, right? So S plus 2 here and S plus 1 over here. Okay. So we can actually use cover up method in here. So to find A, S must be negative 2. Cover up this. We cover up this. So we just focus on S plus 1. So S minus 1 or S plus 1. Since S equals negative 2, so this is going to be negative 2 minus 1 over negative 2 plus 1. Negative 2 plus 1 is negative 1. Negative 2 minus 1 is negative 3. Positive 3 is our value. Let me check. Yes. For S equals negative 1, so we're going to be finding B. So we cover up S plus 1, right? So S minus 1 over S plus 2. Negative 1 minus 1 over negative 1 plus 2. On top, it's going to be negative 2. On bottom is 1. I think you can't see it. Let me just move my... Oops, sorry. Just move my camera. Yeah, so move my camera here so you can see. So in that direction is the solution. Okay. I'm going to be moving this again. So negative 2 is our answer here. All right, let's move this so you can see. Uh, I absent-mindedly, so there we go. So this is negative 2. So the inverse Laplace of 3 over s plus 2 plus b is now negative 2, so negative 2 over s plus 1. So here becomes 3e to the negative 2t minus 2e to the negative t. Yeah, that's the answer. All right. If you write plus c in there, I don't think I don't think you need to write plus c. This is quite small, so can we increase this? There we go. You can increase the size of that. There we go. 4 over s to the 4 minus 1. All right. So actually, uh, this is going to be a partial fraction decomposition. So inverse Laplace of a over s squared plus 1 uh, plus b over s squared minus 1. Okay, so about s squared minus 1. You can partial fraction it further, but I don't want to. Instead, what I'm going to do is to show you the Laplace transforms of some functions. So sine of bt, we already know this. This is b over s squared plus b squared. All right, so that is the Laplace of sine bt. Now, the Laplace of cosine bt is s over s squared plus b squared. If we were to find the hyperbolic version of this, I'm going to put ct instead. So it's going to be c over s squared minus c squared. So it's just the minus version, essentially. And for cosh, ct equals s over s squared minus c squared. This is another way of doing the sinh ct plus minus cosh ct problem earlier, or plus, I think. And I think you can see why the answer was e to the thing, e to the at or e to the ct or something like that. So yeah, in here we got s squared plus 1. In here we got s squared minus 1, and the n is 4. Technically, you do have to write as plus b and cs plus d, but we can actually use this because we will see. So as squared. So this is now s squared minus 1. So a times s squared minus 1 plus b times s squared plus 1. This is equal 4. So a plus b, which is the s squared terms, is 0, while negative a plus b is 4. All right. We know a equals negative b. So, so negative a should be positive b plus b equals 4. So that means b equals 2. And a is negative 2. All right. So we have decomposed it without decomposing it fully, you know. But if you want to complete it, yes, you can do that. But this is just a shortcut. So a is 2, negative 2, sorry, s squared plus 1 plus 2 over s squared minus 1. The s squared plus 1 is cosine of t. Oh no, sine of t, sorry. Sine of t plus 2, and then sinh of t. And t, c is just 1 at that point. So that's the answer here. All right. Question number 72. Why is it so small? Let me just increase the size. The inverse Laplace of this. This looks simple, but it's actually really not that simple. Like, not really complicated, but you'll see what I mean. Now, remember from earlier, I think it was question, no, it was another part. Okay, so remember the Laplace of delta of t minus a f of t. All right. So this was e to the negative sa f of a, correct? All right. So if f of t is 1 and a equals 1, this is it's just the Laplace transform the Dirac delta function. All right. And then that is going to be, well, if f of t is 1, f of a is also 1, so it's just 1 there. A is 1, so it's A is 0 actually, because yeah, A is 0. So e to the 0. So this just becomes 1. Constant 1. All right. Another property we need to look out for is the Laplace of y prime of t. Okay. So this is negative y of 0. Uh Actually not even this. Technically, in real terms, it is the limit of a. So it's not y of 0, it's the limit as of y of a goes to y of 0, right? And you'll see y in a bit, plus s Laplace of whatever it is, right? Why do I want to do this? Because something weird happens when you put the Laplace of the Dirac delta prime t. All right. So again, negative limit as a goes to 0 of y of Dirac delta of a plus s times the Laplace of y Dirac of t. So this is just 1 as we discussed earlier. So this is just s. This, however, is very weird. All right. So let me go back to another question. Is it here? Not that one. Not that one either. Yes, here we go. So this is the original y of 0. The justification for y of 0 is that the lower bound was 0. But we actually don't take the value of 0. We take the limit as it goes to 0. Just so happened that for the majority of functions, the limit, or the majority of common functions, I should say, the limit as something goes to 0, or as something goes to a value, is the point at that value. In other words, normal functions, most functions that we use don't have sudden jump discontinuities like this. Alright, that's a special case, and usually not a neat way. So actually, we're trying to do e to the negative st y of we're going to do, hold on. Actually, it's negative limit as a goes to 0 of y of 0, as well as the infinite one. We just assume that y of t is as a finite value. Why? Because y of infinity could be of infinite value, yet we're trying to say it is a finite value, right? Because we're multiplying by 0. 0 times infinity is a bit trickier to solve, so we just hand wave it away and say it's 0, But it's just an assumption. We're just assuming, oops, sorry. We're just assuming that y of infinity is finite, or at least grows weaker than e to the negative st goes to 0, right? So it's something to do with math, something to do with infinite series. But this is the actual definition of whatever in is in here. All right, not that. Just so happen that most functions we don't really care about the limit. Why is it important in here of all places? Remember what the Dirac delta is. All right, it's 0 everywhere, but as soon as you get to x equals 0, it shoots up to infinity. Right? It's a very weird function in this case. If it was y of 0, it would be infinity. And that would not make sense. A Laplace transform that has infinite, uh, infinity at it is so weird, right? I mean, yeah, there are Laplace transforms where there are points in the Laplace transform is infinite. I guess we work with 1 over s minus 2, right? And at s equals 2, it's infinite. However, the problem with that is the fact that this is going to be infinite everywhere. Like at the entire complex plane, the entire complex domain of S, it's going to have an infinite magnitude, which does not sit well. But knowing that it is the limit and not the value at that limit, which is different, we know that this is 0. So the Laplace transform of uh, Dirac derivative of t is S. Going back to our original function, the inverse Laplace of S follows is just Dirac of t. Actually, the Laplace of s to the n is the nth derivative of t. It's the nth derivative actually, which leads us to our bonus question for this round. The inverse Laplace of s minus 1 quantity squared. Expanding, we get s squared minus 2s plus 1. S squared, that is, if we use the formula here, is going to be Dirac of double derivative of t minus 2 times Dirac derivative of t plus Dirac of t. There we go. As for what the Dirac of t is, Dirac prime of t, I don't have a clear explanation for that. I do know the integral of Dirac of t. That is the unit step function, or let's see, right? Imagine the unit step function is this, and then it just jumps up here, right? So you could say at everywhere else, the derivative is zero, right? But in here, it just jumps up. The rise over run, in this case, the run is zero. You cannot use the definition of the derivative here because this is not continuous, right? So if you use the definition of the derivative here, you would get that, something like that. And actually, you would approach something akin to infinity when you make h zero. Actually, you can use the definition of the derivative. I just realized. Yeah, you can use the definition of the derivative. You would just get infinity, which is exactly what the point at the center or t equal to zero is. It's an infinite thing. So that's another fact for you. 73. ln of s squared plus 4 over s squared plus 9. Hmm. Okay, what can we glean from here, right? All right, let's try finding the derivative of this. All right, because at first glance, this does not look sensical. You know, it's nonsensical in a sense. Why? Because I mean, it is ln, and we haven't touched on anything that has natural logarithm yet. Even in my previous video, I don't think I've touched upon this, but we can actually solve this. So the derivative of this, well, it's hard to find the derivative of this with the we're going to have to use quotient rule and whatnot. But due to the loss of logarithms, we can do ln of s squared plus 4 minus ln of s squared plus 9. All right? The derivative of those would be 2s over s squared plus 4 minus 2s over s squared plus 9. Right? So, mm, from here, what can we do? Well, let's integrate. Let's go back. Instead of s, we replace that with u, right? And instead, we will set the bounds from s to infinity. Does this remind you of something? It should. We will see. So first, hold on. First, we need to find the integral of this. Actually, we already know the integral of that, which is this, just that. Oh, sorry. Uh, there we go. So first one is ln of s squared plus 4. Second one is ln of s squared plus s squared. It's u squared. Sorry. Let me just replace it with u. So instead of s, it's u. All right. And then from s to infinity. Hmm. Now for the fun part. Because this is going to be infinity minus infinity, right? So that's not good. But let's use the laws of logarithms again. So we get u squared plus 4 over u squared plus 9, right? From s to infinity. Now we can find the limit uh, as u goes to infinity in here. The shortcut in here is recognize that the highest power in this is u squared. So we can discard the 4 and the 9 if we're taking the limit up to infinity. right? So now, u squared over u squared, that's just 1. Ln of 1 is just 0. Then we subtract by ln of, well, as u approaches s, so that's going to be s squared plus 4 over s squared plus 9. And we found the, kind of, the original function. All right? So now that we have this original function, now that we found this, what does this mean? Well, if this is our f of s, f of u, right? This is of the form the integral of f of u du from s to infinity. So this is the Laplace of f of t over t. All right. So now we're getting somewhere. All right. The problem is this negative sign. All right. What we can do instead is to put the negative sign here. So instead of that, we're going to have the integral of s infinity of, this is going to be positive now, so we can just put it front. Then that's good. That's going to be negative, so we're going to put it on the back. There we go. And this is going to be ln of s squared plus 4 over s squared plus 9. That which is our original inverse Laplace question. So now that we have this, what next? Well, this is our f of s now. We just need to find f of t. What is f of t? Well, in here, we got 2u over u squared plus 9. This is just 2 cosine of uh, 3t, right? Because 9 is 3 squared. And then minus 2 cosine of 2t over, sorry, that is our f of t. Our actual f of t over t, we just divide by t. This is our Laplace, inverse Laplace. Question number 74. 1 over s minus 3 quant to the power of 4. All right. First thing we note is that this is f of s minus 3, where f of s is 1 over s to the 4. Okay, let's find the Laplace of this f1 of t. So the Laplace of this is uh, sorry, this is of the form n factorial over s to the n plus 1. So, and the time domain is t to the n. You can see that? All right, you can see that. There we go. All right. I just move that down. There we go. So that's going to be the time domain version. So t to the n, so it has to be t cubed. But if that's t cubed, the answer is 6 over s to the 4. We need to divide by 6. Right? For f of s minus 3, we need to multiply by e to the 3t. So our total f of t is e to the 3t times t cubed over 6. There you go. Next, question number 75. The last for the inverse Laplace transforms. The inverse Laplace of 1 over s squared minus 1. Now, we can't do the other thing that we did, which was to recognize the inside, because the inside now is s squared minus 1, not s minus 1. You can do that still, because s squared minus 1 is s plus 1, s minus 1. But I'm going to be doing something else. So this is clearly a variation of sinh and cosh, right? Because the Laplace of sinh is 1 over s squared minus 1, and the Laplace of cosh, or cosh t, is 1 over s over s squared minus 1. Pardon me. So what can we do here? Hmm. Yes. We have square in the bottom. So what if we found the derivative? Because doing that would invoke the quotient rule, right? So let's try it. Laplace of t sinh t is derivative of this negative d over ds 1 over s squared minus 1. So using the quotient rule, so numerator, derivative numerator is just 0, so we ignore that term. So first term is negative, and since it's minus, and then derivative of the denominator times the numerator. The numerator is just 1. The derivative of the denominator is 2s over s squared minus 1. So it's just 2s over s squared minus 1. Can it be of help to us? Squared, sorry, because of the chain rule. Can it be of help to us? Maybe. But let's try the Laplace of t cos t. Yeah. Can this is negative d over ds s over s squared minus 1. Use the quotient rule. So s squared minus 1 quantity squared on bottom. So on top, we have s with s here. So the derivative of that is 1 times the denominator. So we put negative sign here. Then s squared minus 1 minus s times s squared minus times the derivative of the denominator, which is just 2s. All right. So here we get this is 2s squared, so negative 2s squared. So s squared minus 2s squared is negative s squared minus 1 over s squared minus 1 quantity squared. This becomes uh, s squared plus 1 over s squared minus 1 quantity squared. Does that help us in any way? The problem in here is with the 2s terms tripping me out, you know? Huh. How can we do this? We can't do s 2s squared, 2s over s squared minus 1. We can't add that direct. What is the sinh t again? Maybe this will work. How about, let me just properly write that. The Laplace of sinh of t is 1 over s squared minus 1. This is the part where you do have to experiment a bit. If we want this denominator with s squared minus 1 quantity squared, the numerator has to be s squared minus 1. All right. Maybe we can do something with that. What would be the Laplace of s squared, Laplace, sorry. What would be the Laplace of t cos t minus sinh t? All right. S squared plus 1 over s squared minus 1 quantity squared minus s squared minus 1 over s squared minus 1 quantity squared. On the bottom, s squared minus 1 quantity squared. On the top, s squared plus 1 minus s squared plus 1. So it's going to be 2 over s squared minus 1 quantity squared, which is twice what we want. So we just multiply by 1/2. So the original one, the inverse Laplace of, let me just, there we go. The inverse Laplace of 1 over s squared minus 1 quantity squared is 1/2 of t cos t minus sinh t. And there we go. That's the answer. So these problems can be solved using intuition. There is another way of using it. I don't think I've seen it yet. But it's the Laplace transform where you have to use the Laplace transform in another way. But that's going to be it for inverse Laplace transforms. Next one is going to be differential equations. Let's continue with the next segment, which is the ordinary differential equations. So now our question is x squared plus 1 dy over dx equals y, where y of 0 equals 1. First of all, this means that if for x equals 0, oh, sorry, I have the black one here. y equals 1. All right. So that's basically what this means. Now, uh, how do we solve this? First of all, this is a separable ordinary differential equation. It means that we can integrate without much problem. How? Well, you have to separate. So dy over dx, we want y-related terms only. And for the other part, we want x-related terms only. So we want to separate them. So for here, it's dy over dx, and then 1 over y equals 1 over x squared plus 1. What we're gonna do next, and let me just move, not that long. Let's just move this like here, is we're going to integrate this. We're going to integrate this with respect to x. Now remember, the derivative of function of y, for example, y squared, and this is assuming that y is a function of x. So that means that y is f of x or something like that. So y is hiding some x terms inside of it. So the derivative of this is 2y and then dy over dx. Why the dy over dx? It's because of the chain rule. Uh, with the chain rule, remember you have to find the derivative of the outside function, the squared here. So this is the derivative of the outside function, and the inside function, which is dy over dx. For x, for example, if it's x squared, we actually do that, but the derivative of x is just one, so we're just multiplying by one. So it's just an invisible form of the chain rule. All right, so in integration, this means that we can integrate with respect to y. Some people would like to cancel this out, but that's not really what's going on. It just means we're giving we're being granted permission to integrate into y. So the integral of 1 over y in y is ln of y, absolute value of course. And for this is just arctan x. No, we need plus c in at least one side because again in integration there's plus c, right? But we do have an initial condition here and we can use that to find the value of c, the particular value of c that we're trying to find. So x equals 0, so arctan 0. Y equals 1, so ln of 1 plus c here. This is just 0, this is just 0, so c equals 0. So the answer is ln of y equals arctan x, and that's it. And if we want y on its own, we can raise e to both sides. We get y equals e to the arctan of x. Next question. 77. X e to the y dx plus y e to the x dy equals 0, where y of ln 2 equals 0. Again, x equals ln 2, y equals 0. So there you go. Is this separable again? Yes, actually, this is separable. Let's divide both sides by e to the x. So this becomes x e to the negative x, and then yeah, dx. Let's put the x here, dy here, equals 0. And let's divide by e to the y as well. So this becomes y e to the negative y, and yeah, I think I put too much space in here. Just put that there. So now that is our equation. Now it's separable. We've actually separated this now. So we can integrate both sides. So integrate this. Since this addition, we're going to integrate this separately. And there we go. So the integral of this, we can find that using the integration by parts or the DI method. All right. So we put x in here, 1, 0. So we stop there, right? E to the x here, its integral is negative e to the negative x and e to the negative x. Diagonal, and that's what we got. So negative negative x e to the negative x, then minus e to the negative x. Since this is y, which has a similar vibe to it, Oh, I forgot to integrate the other side as well. So we don't forget to integrate that. Okay. So the similar thing here, this is very similar here. The only difference is the variable. So we can actually replace x with y here, and it won't change a thing. So the answer is negative y e to the negative y minus e to the negative. And then the integral of 0 is just c, regardless of whatever uh, variable it is. It's just c. So actually, we don't write equals there. So now the next part is let's try to what do you call this? Factorize e to the x, negative e to the x half. So negative then x plus one e to the negative x, then minus y plus one e to the negative y equals c. So you could present that as your answer, but the rule is, or the convention is, that we want we want the first term here to be positive. We want no negative exponents and whatnot, and we could do a lot of things in order to do that, and no fractions, ideally. If you can't do that, of course you can. But let's see how we can solve this. First of all, we multiply both sides by e to the x, e to the y. What happens? This gets cancelled, but we have e to the y, then x plus 1. And there we go. Y plus 1 e to the x equals e to the x plus y. We can actually multiply both sides by negative 1. So this becomes positive and this also becomes positive. What happens to the c? Well, negative c is also just a constant, so we can envelop the negative into the c. Because c is an arbitrary constant, we can just absorb everything that it gets. So we multiply 2 in there and it still is c. Because it is just an arbitrary constant that we will have to solve later anyway. So that's one. And yeah. And yeah, we still have this initial condition. So let's solve. So it says here y equals 0. So e to the y is 1. Then this is 1 plus ln 2. Then plus y is 0, so it's just 1. E to the x, so e to the ln 2 equals c times e to the ln 2 plus 0. So just ln 2. Now here is 1 plus ln 2. Here is 1 times 2, so it's just 2. Here's 2c. All right. C then is 1 half of this. So 3 plus ln 2 over 2. So that's c. So let's insert. So x plus 1 to the e y plus y plus 1 to the e times e to the x equals 3 plus ln 2 over 2 e to the x plus y. Okay, so we don't want fractions here, so we can multiply by 2 to both sides. Let me just yeah, do that. Let's just erase that one and multiply both sides by 2. That's what I'm doing. Hold on. Uh, so, and there we go. That is our answer. Let me just clean up the 2 here's because it's disturbing me. There we go. Next question. xy plus 3y squared dx plus x squared plus xy dy was 0. This is a homogeneous DE. How can I tell? Look at the total powers of each term here that is enveloped by dx or dy. So, or multiply 2 dx or dy. So this is 1 plus 1, so 2. This is also 2. This is 2, and this is 2 as well. So we can use the homogeneous properties. So what I usually do, and some people do other things, but what I usually do is to multiply by 1 over x squared or 1 over y squared if you prefer that. So this becomes y over x. This becomes 3y squared over x squared, and that is in the x. Plus x squared becomes 1. Xy becomes y over x. This is in the y. Of course, equals 0. Now, let us substitute y over x equals v. That's uh, a new variable, you know. So let's multiply x, so y equals vx. All right. Derivative of y, so we find the and this is equal or dy actually because we're dealing with dy. dy equals this is just chain rule. So v is v prime or dv actually. So x dv plus v dx. All right. Mhm. Yes. Okay, so you can divide by dx, but let's see how this works. All right, so let's replace every dy with this and every y over x with this. So this becomes v plus 3v squared. Dx remains. Plus this becomes 1 plus v. dy becomes x dv plus v dx. Now, let's combine everything that has a dx on one side. So it's v plus 3v squared. And then there's still v dx, then 1 plus v. So let's do that. Plus v. And then all that in the x. And then let's combine everything with the v in it. So it's only with this one. So it's just 1 plus v x d v. Again, equals 0. Yeah. So now let's integrate this. Let's not integrate. Let's solve this. So if this becomes v plus v squared. This becomes 2v plus 4v squared. This becomes 1 plus, well, just 1 plus v times x dv. Now, this is again separable. So let's divide both sides by x and divide by this. Uh, 1, this should be plus 1 over v and then a 2v. So it's good. 2v plus 1 dv. And then, of course, 0. Now we can integrate all three terms. Here, this is a partial fraction problem, and we can use the cover up method. So for let's separate this a over 2v plus b over 2v plus 1. All right. V equals 0, we get a. So we cover this up. Let's select this. Uh-huh. Okay. Let's cover 2v. What do we get? 0. So this becomes 0 plus 1. So 1 over 0 plus 1 is 1. So it's just 1. For v equals negative 1 half. So we can do this again, but we erase this one. We cover that up. So v equals negative 1 half. So on the top becomes negative, actually just positive 1 half. Ooh, I save. And on the bottom, we get 2 times negative 1 half is negative 1. So the answer is negative 1 half. That is indeed correct. All right. So we get this, which is ln x. We get this, which is still integral 1 over 2v, yeah, minus 1 half over 2v plus 1 dv. And then the next part is c, just because the integral of 0 is c. The integral of this is 1 half ln of v. This is negative 1/4 ln of 2v plus 1. You can even check that. And we have ln x here and c on the other side. Let's combine the ln's with respect to the laws of logarithms. So ln of, actually, we don't want the fractions, right? So we multiply both of sides by 4. 4c just becomes c because c is just an arbitrary constant. 4 times ln x here, 2 ln of v here, and minus 1 ln of 2v plus 1. It's still absolute value because v and x can still be negative. Nothing about it says that it can't be negative. There we go. So now we combine all the ln's together using the laws of logarithms. First is this. Since it's positive, it's on the top, and we include x to the power of 4. And then here, since it's positive, it's on the top, we include the power. On the bottom is the subtract here, so it's on the bottom. So 2v plus 1. All right, there we go. And equals c. All right, so this is still v, and we know v equals y over x, right? So let's substitute y over x here. ln of x to the 4, y squared over x squared over 2y over x plus 1. Multiply both the numerator and denominator by x squared in order to simplify. So on the top is, yeah, yeah, yeah. On the top, this cancels out, leaving us with x 4y squared. On the bottom, something cancels out here. And no, actually, it's a bit more complicated than that. Over 2, then this becomes xy plus x squared. We raise e to both sides to remove the natural logarithm. E to the constant is still an arbitrary constant, so we retain c. Actually, since we can multiply by 1 over x here again, so uh to minimize the excess. So x cubed y cubed over 2y plus x, plus or minus. Oh no, my answer key is mistaken. Yeah, it is 2y plus x, sorry. And then, of course, we don't forget equals c. And we don't have initial conditions here, so we're going to leave it at that. Or if you want, you can, of course, rationalize, or not rationalize. Make sure that there are no fractional parts. So let's just rearrange it, and that is the answer. Next. Next question. Y squared dy equals x times x dy minus y dx to the power e to the x over y. The e to the x over y is begging us to have y in the denominator, so we will be doing that. All right. So is this homogeneous? Yes, because there's y squared, so that's power of 2. X times x plus power 2. X times y, so that's another power of 2. So it is indeed uh, xy. So what do we do? We divide by y squared. So 1 over y squared, all that. This becomes dy. Here becomes x squared over y squared, and then dy. Then minus xy, so that will be x over y. Minus x over y dx. All that raised to times e to the x over y. All right. So there. Maybe you can do something about this because it does look like a product rule form, but we're not going for now. Maybe. It doesn't look like a product. Anyway, The next part here should be x over y equals v, substitution, of course. X equals v y. So dx equals uh, y dv plus v dy. That is our, yeah. Dy remains, x squared over y squared becomes v squared. Dy remains minus this, which is v, and then dx is this, y dv plus v dy. And then e to the v. Okay. All right. All right. Yeah. So dy on here, and let's expand this. So v squared dy minus vy dv minus v squared dy to power e to the v. This and that cancel each other out since they're the same but opposite, so it's just zero. So what remains is, so c negative vy dv. And then don't forget e to the v somewhere in there. Maybe like that. Let's write that properly. Vy e to the v dv, right? And then dy on here. Divide by y, so this is inseparable now. So dy over y equals negative v e to the v dv. There we go. Integrate both sides. On one hand, L and Y. On the other hand, this is an integration by parts exercise. So let's just put it here. Can you see that? Yeah, you can see that. Plus, minus, plus, negative V here, so negative 1 and that's 0. E to the V, e to the V, e to the V. All right. So first is negative V, e to the V, plus e to the V, plus C. All right. Hmm. Yes. Let me see if we can still. Yes, I think. So this can become e to the v, then 1 minus v plus c. One more thing, we can put this, we can raise e to both sides to get y equals e to the c, then e to the whatever. E to the c is just an arbitrary constant again. So we can minimize that to c times e to the 1 minus v times e to the v. That's that's your integral. No, that's your answer. Sorry. Number 80. Oh my God, that's long. 2x plus y, 2x plus 4y here, but 2x plus y in here. Hang on. Right, I think there's a slight mistake, so let's just remove the 4. There we go. 2x plus y times dx plus y minus 4x dy equals 0. So I think there was a clerical error somewhere, but yeah. This is still homogeneous. Ugh. Still homogeneous is actually a very long solution. So let's uh, brace in, you know. So we divide by x. That's my favorite thing to do here. The x plus, and then here y over x minus 4 dy equals 0. Let's try this method. So in this method, dx equals 1 and dy equals y prime. So something like that. So it's not dividing by dx or whatever. It's just as uh, a way of making things easier. So y prime here. So we do the same. mm, We do the same routine as the homogeneous earlier, which is to substitute. Then, yeah, there we go. So y prime equals, so here we get v plus xv prime. Let's just put that there. I think yeah, that's fine. Now what can we do here? Yeah, but just substitute everything else. 2 plus y over x becomes 2 plus v. V minus 4 is here, and then we multiply by v plus x v prime. So in this method, this is much easier to write. Next, 2 plus v plus v times v is v squared. Uh, negative 4 times v is negative 4v, and then v minus 4 times x v prime. All right. We multiply all of this. So v squared here minus 3v plus 2. All right. Plus then v minus 4 x v prime equals 0. Divide by 1 over x. Divide by v squared minus 3v plus 2, which as we all know is v minus 1 and v minus 2. All right. I think we can all glean that. And it's one of my favorite things is to, it looks like this. And that's one of my favorite things to do. So we integrate with respect to x. V prime is dv over dx. So that just means that we are allowed to integrate with respect to v. And 0. Oh, all right. Let's just get this out of the way. C. And this, ln x. But this is the more interesting part. So v that's a over v minus 1 plus b over v minus 2. We can use the cover up method. So v equals 1, then cover up v minus 1. So 1 minus 4 over 1 minus 2. 1 minus 4 is negative 3. 1, yeah, negative 3, then on the bottom negative 1, so that's just 3. V then, we need v equals 2 here. Okay, let's just separate that so we don't get confused. And we just erase v minus 2. So on top becomes 2 minus 4. Bottom becomes 2 minus 1. That's negative 2. So now we can replace a and b here with 3 here, negative 2 here. So this is 3 ln of v minus 1 minus 2 ln of v minus 2. How about that? Now we can combine everything in one integral. So this is going to be exciting. One integral. No, one natural log because of the loss of logarithms. So x times v minus 1 cubed over v minus 2 squared equals c. So from there, in we can list e to both sides, and e to the c is just an arbitrary constant, so that changes not. We can write that as c. There we go, and c. Now this v is y over x, remember? So x times y over x minus 1 quantity cube over v minus 2, v minus v is y over x. So now, in order to rationalize this, we need to multiply by x cubed, both here and here. Actually, we don't need x squared. Why? Because we already have this x right here to help us. Okay, let's start on the bottom since it is easier. That x squared means we can enter this unimpeded. So this becomes y minus 2x. Of course, it's more complicated than just, letting it pass through, but we can think of it like that. Squared. This has to match, right? This and that, so we can multiply x on the inside there. In here, we have x here with x squared here. That would be x cubed. So we can go through here and y minus x to the power of 3 plus c. Rationalizing, or not rationalizing, simplifying, we get y minus x quantity cubed equals c times y minus 2x quantity squared. Uh, that's a check. There you go. Number 81. X squared plus 1 times dy over dx plus y was what? What can we do here? Let's try dividing by x squared plus 1. All right. Look at this. Look at what I am doing. dy over dx equal, not equals, plus y times 1 over x squared plus 1 equals what? Integrate, we don't have an option to integrate this. This would be very hard. What can we do? Well, this is the form of a DE, linear ODE, y prime or dy over dx plus p of xy equals q of x. We do have that form right here, right? P of x is 1 over x squared plus 1 and so on. The integrating factor I of x, for which we need to integrate that. We need to multiply, sorry, to both sides in order to make it integrable, is e to the integral of p of x dx. What does this do? Well, if we go and put that there, well, if you see here, let me just look at that. It's actually very fascinating about how it is derived. So let's do that first here, and then we can discover why we do this. So we multiply by this, and then we can integrate that. We get arctangent x. The plus c we can ignore it for that. Uh, just ignore the plus c. We don't need plus c. We just need the antiderivative. Just one antiderivative that would be the easiest, you know? So e to the arctan x dy over dx plus y, sorry, let's put the x first. So e to the arctan x over 1 plus x squared. Actually, let's just put it there so it's simpler to see. Times y plus 1. So what does this do now? Well, this is uh this is a product rule thing because this is just e to the arctan x y, derivative of that. If you look really carefully, look. So it's the second derivative, not second derivative, the derivative of the second term, and then remain the first term. And then for the other one, it's the derivative of the first term and the second term remains. So it is a product rule situation there. Is we're doing it in reverse, and that's what the integrating factor is actually for. All right. And I forgot to e to the arctan here. You need to multiply it to the other side as well. Oh, I forgot to divide it by x squared plus 1. How silly of me. Let's just put 1 plus x squared because it's easier. E to the arctan x, I don't think is integrable. Maybe. No, it's not. Maybe. No, it's not. Okay. So, integral of... no. Just e to the arctan x over 1 plus x squared. And then we integrate with respect to x. Let's get this one out of the way. Integral of derivative is just the original function. So y e to the arctan x. And then here, what is the integral of that? Well, we do have its inside. We do have the outside function and the inside function and its derivative. So this is most likely e to the arctan x, right? You can glean over that. And the fact that this is already in there just shows you how we do. And then we have plus c. All right. Usually, in convention, we want y to be alone, so sad. Uh, we divide by e to the arctan x. So e to the arctan is divided by itself, so 1 plus c e to the negative arctan x. That is our d. Wow. Oh no. I got scared, but let's not be scared because this is just an ordinary differential equation as a solution. So negative x cosecant squared y dy over dx plus x cotangent y equals x cosecant x cosine x, sorry, minus cotangent y. Okay. Now, what we can do here is substitution. Let cotangent y equal v. Its derivative is negative cosecant squared y dy over dx, and then dv over dx on the other side. So this becomes dv over dx. This will only cotangent x cotangent y. This becomes v. So x v cotangent x, right? Equals x cosine x minus v. Right. So put everything that has a v on this side. Eh? And yeah, no, not the cosine v, just the v. So x dv over dx plus sorry, xv cotangent x plus v equals x cosine x on one side. Okay, so v, well, we can simplify this to be v times x cot x plus 1. All right, let's replace that. There we go. Divide both sides by x. So this gets 5 big booms. And yeah, v and then cotangent x plus 1 over x. And then cosine x on the other side. This is a linear ODE, so we can use the e to the something. So e to the something, cotangent x plus 1 over x dx. Cotangent x is ln sine x. Uh-huh. And then 1 over x, the integral of that is the x is here, right? So don't misconstrue that. That's just ln x. This becomes actually, since this is addition in the exponentiation, this is multiplication down. So it's just e to the ln x, e to the ln sine x, yeah. So we can do that. So this is sine x, this is x, and that is our integrating factor. Multiplying ln x sine x both sides. So x sine x dv over dx plus v comes next. And then this becomes x times cotangent times sine is cosine. So x cosine x. This becomes sine x equals x sine x cosine x. This becomes a product rule. So this is just d over dx times x sine x x v. So x sine x v equals x sine x cosine x. And I do believe we had a question about similar to this earlier in this video. Although honestly, it's been like months since I've recorded that. So a little bit of trivia is that the recording takes months in between because of work and because of school. But I do love this, so I've come back. So this is just the inside. So xv sin x. This is just the integral of whatever the integral of that is. Uh, wait, the hell? Oh, I think I forgot to. Yeah. So the to find the integral of this, I got confused on my notes. Sorry. So this is just x and then sine 2x, then 1 half. Since it is 2 sine x cosine x, 1 half. We put 1 half x in here because we can reduce that to 0. Nice. Sine 2x here becomes 1 half, negative 1 half cosine 2x, and negative 1/4 sine 2x. Diagonals. Alright, so negative 1/4 x cosine 2x plus 1/8 sine 2x and plus c. Multiply by 8. So we got 8x and then v is, what is v again? Cotangent y. So cotangent y sine x. Plus negative 1/4 x cosine 2x. No, 1/4 is just 2 now. Plus sine 2x plus a times c is just an arbitrary constant. So we get that. Done. 83. Y plus xy prime plus 2x squared y equals e to the negative x squared. The negative x squared is giving me jingle bells. But need not worry because we do need to do something. This looks like what do you call it? Wait, yeah, 2x squared. Oh, yeah. This looks like what do you call that? A linear ODE. So xy prime plus y we can be factorized like this, so x squared plus 1, and then e to the negative x squared. Do we divide by x? So this becomes that 2x plus 1 over x equals 1 over x e to the negative x squared. Whatever's going on the right side, I will explain that later. All right, so we integrate e to the integral of 2x plus 1 over x dx. And then it is x squared plus ln x. Again, e to the x squared, e to the ln x. So this is just x e to the x squared. Okay, so here becomes e to the x e to the x squared y prime plus y times 2x squared. Yes. 2x squared plus 1 e to the x squared. Is that right? Yeah, yeah, it is. Oh, it's correct. That's correct. And of course, 1 over x e to the negative x squared times x e to the x squared, that will become the big one. Here is the derivative of x e to the x squared y equals 1. Integrate both sides with respect to x. In here we get x e to the x squared y equals x plus c. And honestly, that's a good answer already. You can isolate y, but I'll consider that. Y prime minus 1 over 2x times y plus x cubed y cubed equals 0. What is this? Hmm, maybe it's linear? Let's see. So this is troubling us. Let's put it on the back burner. So y prime, that's slang for the right hand side. All right. I created that slang, but negative x cubed y cubed. This is actually a Bernoulli. So it's like this is a special case of the linear ODE, as I previously discussed on this channel, except that there is a power of y here, and that gives me trouble. So what can we do here is to multiply both sides mm, by y to the negative 3. So this is gone here. So y to the negative 3 y prime minus 1 over 2x y to the negative 2 equals negative x cubed. First, y to the negative 2 equals v because negative 2 y to the negative 3 equals, it's alright, y prime, forgot y prime, equals v prime. This is already that, so y to the negative 3 y prime equals negative 1 half v. Alright, so now let's transform this into the appropriate version. So negative 1 half v prime minus 1 over 2x, then that's v, and then negative x cubed. This is very long. Right? All of these ordinary differential equations are really long, and these are the easy ODEs. There are ODEs that are literally impossible to solve. But anyway, we multiply by negative 2 to isolate v prime here. And nicely enough, it gets rid of negative 1 half here. So that's just 1 over x times v and 2x cubed. That's very nice. It gets rid of all the negatives. Now, this is a normal linear differential equation, linear ordinary differential equation. So uh, we can whip out this old formula. And it's just e to the ln x, which is just x, which actually just makes sense. This is what this is what's resulting, and yeah, we've already seen that before, haven't we? So this is just 2x to the 4. We integrate both sides. We all know this is xv, so the derivative of xv, so the integral of that is just xv. And then for here, it is just the power rule, so 2 over 5 x to the 5 plus c. And then again, v from back when is y to the negative 2, right? So xy to the negative 2 equals 2/5 x to the 5 plus c. Let's multiply 5 times 5y squared. So 5 goes here. On the other hand is 2x to the 5y squared plus cy squared. 5 times c is just c, so that's going to be our answer. I think that's permissible enough. 85. Secant y dy over dx minus 1 over x cosine y tangent y equals cosine x sine y tan y. Okay, so, secant y on its own, I don't know. How about secant squared y? So how can we do that? All right. So we're going to multiply by secant y, both sides. This becomes secant squared y dy over dx. So it's begging us to integrate this maybe and get tangent y, right? Minus cosine y and secant y is just 1, so they annihilate. So tangent y remains. This becomes cosine x, of course. Sine y times secant y is sine y over cosine y, so tangent x. Tangent y, sorry. Tangent y times tangent y, so there's square here. Okay, I just remembered why this question is difficult. Okay, so tangent y, let's use u. So the derivative is secant squared y dy over dx. Again, this was created like months ago. And I just realized why this question is very difficult. So, no big deal. So that becomes that 1 over x times u equals cosine x times u squared. This is Bernoulli again. Oh no. So we do it again. We do the Bernoulli and multiply by u to the negative 2. All right. And next is this and this cosine x. There we go. I haven't used the right side for some time now. Let's go to the middle. Of course, u to the negative 2 equals v. No, u to the negative 1, sorry, equals. Then negative u to the negative 2 du over dx equals dv over dx. This is positive, so we just put negative here. This is 1 over x times v. This is just cosine x. Multiply by negative 1. There you go. Plus 1 over x v. 1 over x times v cos negative cosine x. We've encountered this before. Literally, the previous question was just this. So, just multiplied by x, but to make it formal, we use our good old buddy, the integrating factor. So this is e to the ln x, which is at x. So x dv over x, which is d over dx, dx times xv. You can check for yourself. And then negative x cosine x. So negative x cosine x is just easy. So let's just rip out the DI method. So negative x, negative 1, and 0. This becomes cosine x. The integral is sine x. Don't forget, and negative cosine x here. Integrate. Our integral is negative x sine x minus cosine x. V is u to the negative 2. So that becomes that. U is tangent, right? So where's u? Where's that first? No. U is tangent. So u to the negative is cotangent. So it's cotangent squared y. And of course I forgot to put plus c anywhere in here. Let's just put plus c retroactively and we are done. This is an equal sign. There we go. So yeah, that is 100 that is number 85 ordinary differential equations. And now for question number 86, which is this. Y over 1 plus x squared y squared plus 3x squared dx plus x over 1 plus x squared y squared dy equals. Now, one of the techniques we use here is to find out if it is exact. Because if it is exact, we do have easy ways to solve this. So first we find its exactness. How do we do that? Let's say this is m and say this is n. First, we have to find the partial derivative with respect to y. M is attached to x, so we need to find the partial with respect to y. This has to equal the partial of n with respect to x since it is attached to y. Okay, so that's going to be our check. So we can the shorthand for this is my plus nx, and w- we can deal with everything later. So my is it's 3x squared has no y terms, so we can say this is 0. So the constant in the y world, while this has some y terms. So uh, uh, we can use the quotient rule. First is derivative on top, which is 1 times bottom minus top times derivative of bottom, which is 1 plus 2x squared y. Uh, so 1 is not because it's just a constant. So, yeah, remove that there. All right, let me just move this here. We need to, uh, we need to simplify this. So, this becomes 2x squared y squared since we multiplied by y. We subtract from x squared y squared. This becomes 1 minus x squared y squared over 1 plus x squared y squared. Forgot the squared on the outside since it is the quotient rule. There we go. So that's my. Now what nx? Well, that is this part already. So there's x here, so that's okay. So derivative of x is 1 times 1 plus x squared y squared minus x times uh 2xy squared. Yeah. Over 1 plus x squared y squared squared. Yeah. On top is 1 minus x squared y squared. You can check that. These are the same, so this means this is exact. What can we do now? Well, with that, we can integrate both sides, but here's how we do it. So mx, so m is actually the partial of some function x. So this is y over 1 plus x squared y squared plus 3x squared. All right. And then n is uh, the partial of some y. Is that right? Because it has the y in here. Yes. So this is x over 1 plus x squared y squared. All right. So let's try integrating this fy first. So since this is fy, we need to integrate with respect to y. All right. I'm going to combine this in xy quantities squared. Right. This seem familiar? This is arctan of xy. Why arctan xy? Well, how about the x on the top? Well, remember that we have to integrate the outside term, so this is the denominator. And we have to integrate the inner term with respect to y's. Inner term, yeah. The inside function with respect to y. So the integral of that is just x. So that is what is on the top. And then usually we use plus c, but we have to actually do this g of x, y, because the integral of g of x, the derivative of g of x with respect to y is 0. So everything that has x or constant is 0 in the y. So we need to do that. Next, hmm, ugh, on the top, we integrate that as well. Fx equals, or integral fx dx this time equals y over 1 plus xy quantity squared dx plus integral of 3x squared dx. Okay, so this one is also subject to the same conditions as before. This time it's x. So it's arctan of xy. This is x cubed, and then we add g of y here. Again, for the same reason, because we the partial differentiated by x with respect to x. So now we have two functions, and we just have to compare them. So they both have arctan x. So arctan xy is both there. X cubed is the function of x described here, so we have x cubed. G of y does not have anything on the y side, so we can assume that it doesn't exist. Or actually, yeah, it's 0, right? And then, of course, equals c because we integrated, right? Actually, you can think of the g of y as c or something to that effect. You can also think of g of x as x cubed plus c, but I just put it there. Again, c is just arbitrary constant, as I have reiterated over and over again. Next question. So xy dx plus y cubed minus 4x squared dy. So, what about this? This is, uh, let's check using the exactness method. Maybe this is exact. Then after that we can hunt for the solution. So so all right. Mm, my is the derivative of this is 2x. And x is derivative of that. Y cube is gone. Derivative of this is negative 8x. This is inexact, so we need to either do something else or make this an exact form. So there are actually uh, two forms we can try. So it's either e to the my minus nx over n dx, or e to the nx minus my over m dy. This is an expanded form of, yes, indeed, the linear ODEs. All right. So now that we have that, let's try one of these. Maybe this would work, or maybe this would work. I don't know. Again, this is m, this is n. Hmm. Hmm. Yes. Looking at it, if we tried the first one, this would be our denominator, and that does not look easy to integrate. But if we use the second one, the denominator would be 2xy, which would be, I think, easier. So let's try that instead. So e to the nx is negative 8x minus my, which is 2x, over m, which is 2xy. E to the negative 10x over 2xy. We cancel x, cancel 10 to become 5 and 2. We get negative 5 over y dy. This is e to the negative 5 lny, or y to the negative 5. Alright, so we multiply y to the negative 5 to the original. Uh, uh-huh. Hold on. There we go. We multiply y to the negative 5 to both sides here. We get 2x to y to the negative 4 dx plus y to the negative 2 minus 4x to squared y to the negative 5 dy 0. Let's try let's try integrating. Let's try checking. So my now is negative 8x to the uh, negative 8x of y to the negative 5. And x now is, so the y squared is y to the negative 2 is gone. This is what remains. So negative 4 times 2 is 8. Then x y to the negative 5. Yeah, it's exact. Right? You can even check that yourself. So now that we have everything, now that we have an exact form, actually we can be sure we have an exact form if we do the math correctly. We can we can now solve for this. Fx or m or f partial x is 2x y to the negative 4. All right. Now for to find f, we integrate this with respect to x. All right. So this becomes x squared y to the negative 4 plus again g of y, since we did not have that. Now the second method for this, if you don't want to integrate twice, is to differentiate this. So the derivative of this is or partial differentiated with respect to y to get the second half, hopefully. So this becomes x squared y to the negative 5, and then we have to multiply by negative 4. And then plus g of y. G of y corresponds to y to the negative 2. And then integrate, or g prime of y, sorry. G prime of y corresponds to y to the negative 2. And we have to integrate that, which grants us negative y to the negative 1 plus c. So that's what we put as g of y. So f is now x squared y to the negative 4 plus, no, sorry, negative. So minus y to the negative 1 plus c. Or if we want the differential equation instead of a function, we equate to c instead. There we go. Nice. Next, this is y equals xy prime plus y prime squared plus 1. Ooh, so this is a bit weird. This is what we call a clear-out differential equation. And this is the form that it takes. What do we do here? Because there's this term, we can't use linear, so that's out of the equation. What we can actually do is y prime, we differentiate both sides. So on one side, y prime. On the other side is, it's just product rule. So x, y prime. So y prime plus x, y prime prime plus derivative of this is 2y prime and then y prime prime, chain rule. And then 1 is just a constant. What happens here is that we can subtract by y prime on both sides. That cancel out. So leaving us with 0 here, and xy prime prime plus 2y prime, sorry, y prime prime. And factoring out, so we get x plus 2y prime equals 0. We now have two choices. So on one hand, y prime prime equals 0. y prime equals c. All right, integrating it, it becomes c, and then y equals c. Actually, no, we won't do that. We will keep on trucking. Okay, so that's the first part. On the second part, this one, x plus 2y prime equals 0. There we go. Y prime is negative 1 half x. So y equals negative x squared over 4. All right. Yes. So the next part is, hold on, remembering the original, or the original, let me just, there we go. So remember the original differential equation. Actually, we don't need to integrate this again. We can put the y primes as c's in here. So this becomes y equals cx plus c squared plus 1. So these are the possible solutions for this differential equation, namely y equals negative x squared over 4 and y equals cx plus c squared plus 1. That's wonderful. Uh, Let me spell out this is a Clairaut, this is French. Clairaut differential equation. It's an ordinary differential equation. It's very cool. That was relaxing. This is not relaxing. dy over dx equals x plus y quantity cubed. So I was not satisfied with squared, so we got a cube. And oh no, the page is long. So let's try solving this. First, the technique here is to substitute x plus y plus 1 as v. Then 1 plus y prime equals v prime. Y prime then is v prime minus 1. Can you see that? You can. All right. So now, yes, so y prime, let's put the y over the x as y prime so I don't have difficulty writing that. Y prime is v prime minus 1 now. X plus y is v cubed. All right. V prime is v cubed plus 1. V prime over v cubed plus 1 equals 1. And I think you can start seeing the problem. We integrate, and yeah, if you don't know, if you don't have this plus 1, if you don't have that, it would be much easier to solve. But since we have that plus 1, we have to do a little bit of work. Just a little bit. First, oh God. Factorize v cubed plus 1 into v plus 1 and v squared minus v plus 1 dv here. All right, let's ignore the dx for now. We know what the integral for that is. Ooh. And then we decompose it into a v plus 1 plus b, bv plus c since it is now a quadratic dv. So now we can't use, I think we can use the cover-up method, but it's highly inefficient. So we're not going to be doing that. Instead, what we're going to do is to, yeah, we have to solve this bv plus c here and then v plus 1. All right. So this is equal to 1. So this is another method that's similar to the cover up strategy, but this is a bit harder. So pay attention. If v equals negative 1, this entire term falls apart. So we are left with a. So this is put negative 1 in v. So v times negative 1 times negative 1 is negative positive 1. Negative 1 is positive 1 plus 1 plus 1. A is 1/3. Great. So we replace this with 1/3. And again, we can put this here. All right. So now that that is 1/3, we can go for other values of v. So we can't go for the roots of this because the roots of this is probably irrational, so it's not good. But what we can do is go to a random value, like 0. So this is 0, 0 minus 0 plus 1, so that's just 1. So 1/3 plus b times 0 is 0, so that's we're c, and 0 plus 1 is just 1, so that's 1. And then equals 1. This is very easily just 2/3, right? So we got 2/3 here. Is that correct? 2/3. Yep. Next. All right. So we want v now. Let's remove c, replace it with its actual value, 2/3. We want b now, so v equals 1 would be a good choice. 1 minus 1 is 0, plus 1 is still 1. So 1/3 remains. Plus b remains, 2/3 is still there. And v plus 1 is 2 equals 1. Now we isolate b. First, subtract by 1/3. So we got b plus 2/3, 2 equals 2/3. Divide by 2 to get 1/3. So b plus 2/3 equals 1/3. And then b equals negative 1/3. And that is the value. Using these three values and the original integral, let's bring this down, down. A is, let's just also bring this down here. So A is 1/3, B is negative 1/3, and C is 2/3. All right. We can factor by 3 in order to remove the 1/3 terms. So 1 over v plus 1 plus negative v plus 2 over v squared minus v plus 1. Oh my god. This is a bit difficult, right? But it's fine. Let's just, yeah, let's just separate this. Yeah, there we go. And then integral of negative v plus 2 over v squared minus v plus 1. This would be great if instead of negative v plus 2 is negative outside. So we replace this with a negative in order to have this switcheroo around. So it's v minus 2 instead. It would also be great if we multiply this by 2, but we need to divide by 2. So there, and let's just multiply it already. It's 2v minus 4. And this would be great if it was 2v minus 1 instead. So instead of 4, this would be 1. But the negative 3 has to live somewhere, so we put it somewhere here. It's like forgotten, but not really. So now this is way easier to integrate, but we have the addition of this term. Let's complete the square. So this is 3 over, then to complete the square here, you need v minus 1/2 squared. Since this is 2 times 1/2 times v, right? It's 1/2. But this is 1/4 only, so we need to add 3/4 here. Let's do some things in advance and don't and write it in that form because we're going to have a little bit of trouble. Right? I already feel the trouble brewing. All right. So the integral of, let me just go back, x squared, a squared plus x squared is arctangent or 1 over a arctangent of x over a. Right? You can even think of that. So knowing that, we're going to be using that for this part right here because It's problematic. This becomes ln of v plus 1. This become, or 1/3, sorry, minus 1/6 of ln of v squared minus v plus 1. This becomes, so negative, this is negative, so it becomes positive. Yes, this becomes positive. 1/6 times 3, since this is 3, times, of course, 1 over a, so that's 2 over 3. Arctangent of this over a. So v minus 1/2 over square root of 3 over 2. Oh, brother, this is getting long. Uh, what is going on? Even I don't know what I'm looking at. Uh, don't worry, guys. Everything is all right. Maybe. So yeah, that is in the integral. And we forgot this part right here. This part. So as we all know, that's just x. But we have to write plus c here. Let's let's simplify this in order to make it look better. Now, here, let's multiply by 6. Uh, hold on. Still have this. We just cancel that out, right? 1/2, 2 over root 3, 1 over root 3. Hang on. Uh, where did everything go? Oh, no, no, no. I figured out where everything went. Okay. So that just becomes 1 over root 3. Let's just, where, oh, damn it. 1 over root 3. And let's select that like that. So we multiply by 6. Since this is irrational on the bottom, let's just rationalize it. There we go. The right way to use the word rationalize. We multiply by 6. Wait, since c is an arbitrary constant, so let's just remain c. 1/3 times 6 is 2. ln of, let's turn v into is x plus y plus 1. So x plus y plus 1, but there's a plus 1, so plus 2. Minus 1/6, this is 1 now. So ln of x plus y plus 1 squared minus x minus y, and then minus 1 plus 1 is 0, so that's it. Plus 2 times root 3, since 1/3 is 2, 1/3 times 6 is 2 times root 3. Arctangent of the inside of here. Let me just put root 3 over 2 on top, so 2 over root 3. And then v is x plus y plus 1 minus 1/2 is plus 1/2. That is your answer. Oh my God. And there's even plus c in. And if you want to like combine, yeah, you could. But do you want to? I'm tired already. Anyway, next question. Hopefully this is relaxing. Y prime prime plus 1 over x y prime equals 2. This looks like linear but in second derivative form. And it actually is. If we look at y prime as a sort of variable on its own, it is a variable on its own. So v, let's substitute y prime as v. So this becomes v prime plus v over x equals 2. And again, we can use uh, this technique. So e to the ln x, which is just x. So xv prime plus v equals 2x. Integrate both sides. This we can see by inspection, it's just xv. On other side is x squared plus c. All right. And then we can isolate v here as x plus c over x. Actually, c1, since v is still y prime. So y prime equals x plus c1 over x. All right. So integrating both sides, we get x squared over 2 plus c1 ln x plus c2. Your answer. So actually, it is you can pretend it is a first order differential equation, and then you can go back to it being a second order. That's very nice. All right, an actual second order differential equation. So y prime prime plus 7y prime plus 6y equals 0. This is what we call an auxiliary ODE. And here's how it works. What? Hang on. There's a typo again. There is a typo. So it's y prime prime. Sorry. It's y prime prime. I don't think y prime prime prime. It's y prime prime. There we go. This is an auxiliary ODE. What can we do here? I think I've already explained this, but what we can do is to transform this into uh, a quadratic or a polynomial. We go m squared or d. Actually, some people use d instead. So m squared, so 2 refers to the amount of derivatives you perform, but in here it is now a polynomial. As to how that works, it's because of e to the x being a thing here. So let's just say m squared here, and then 7m and then 6. Find the roots. So this is m plus 1 and m plus 6. The roots is -1 and -6. All right. These roots would become the coefficient of the power in the answer. So usually this is a function of in t. So DE we always like t or maybe x if you want, but x and t all work the same. So this is C1 e to the negative t plus C2 e to the negative 6t. All right. So the roots became coefficients for the powers of e. And that's very cool. And this is actually the answer. Next. Y prime prime plus 6y prime plus 9y. So again, uh we can use the method earlier. We can transform this into some polynomial, and then we can solve for the roots of that polynomial. This time this is m plus 3 oops, not cube squared equals 0. So m equals just -3. So there's one root, but it is twice. Okay, this is m equals -3 twice. Because the graph is something like that. In some number theory stuff, we count this point twice. All right. So this is m equals -3 twice. So if we want to use the auxiliary thing, we can use C1 e to the -3t plus C2 e to the -3t. The problem with this is that the C1 and C2 can't combine it in order to have C. So we need something else to differentiate e to the -3t other than the arbitrary constant, and that's going to be t. All right. So if this was m plus 3 quantity cubed, so it's -3 times. So what's going to happen is actually just increase the power of t here. So that's what you do. Next, y prime prime plus 4y prime plus 20y equals 0. All right. So this has no real roots. Let's try to uh complete the square. So this is again m squared plus 4m plus 20 equals 0. Completing the square grants us this. But we have an excess of 16. This is m plus 2 quantity squared plus 16 equals 0. Alright? To find m, we put 16 on the other side, so it's that. We square root that. We get m plus 2 equals plus or minus 4i, which is the imaginary unit. So m is -2 plus or minus 4i. And for this, the real part corresponds to the here, and the imaginary part corresponds to cosine or sine, as we will see later. Since it's plus minus, there's two, so it's cosine and sine. So y equals e to the negative 2t, which is the real part, cosine of 4, not 4, 4t, which is the imaginary part. So we had C1 here, plus C2 e to the negative 2t sine of 4t, again, the imaginary part. That's your answer. Question number 94. Y prime prime plus 4y prime plus 20y equals 90. We have now the addition of 90. We have two parts in here, YC and YP. Particular and I think complementary, but yeah, this is the YC is just the auxiliary. So let's just do it. So it's just m squared plus 4y, sorry. M plus 20 equals 0. As we've discussed earlier, we already know this DE, so YC is the DE from earlier because again, it's the same question, right? Right. So let's just copy paste actually. Why not? Yeah. There we go. Smooth and remove this and just put C in here. Nice, very sneaky. Now the next part is YP. All right. So in YP, you have, this is the method of undetermined coefficients, what we're going to do here. So let me finish right. Okay, so what we have to do is to find functions that would result in 90. In this case, this would be AT plus B. All right. So this is the form. In here, 90 is just 90 plus 0. So something like that. But we have to find YP. Alright, so next, we find the derivative of this is just a, and the second derivative is 0. Now we insert that into y prime prime plus 4y prime plus 20y. All of it is, oh, sorry, all of it is particular, alright? Y prime prime is 0, 4y prime is 4a, and 20yp is 20at plus 20b. Alright, so this is equal 90. So this is what we usually do in what do you call it? Partial fractions, right? The cover up method you can use here. So for t equals 0, this is removed, this is also removed. So 4a plus 20b equals 0. For t equals 1, this becomes 20a plus 4a, so 24a plus 20b equals 9. All right. Nice. In order to solve this, we subtract this to this. So 4a minus 24a, that's negative 20a. This becomes 0. So 0 minus 9 is negative 9. A equals 9 over 20. Substituting it into one of these, we find that b equals negative 9 over 100. All right. Can we test if this is correct? So 9 over 20 times 4 is 9 over 5 minus 9 over 5. So because 9 over 100 times 20 is 9 over 5. So that is equals to 0. So the check is correct. This is correct. So now that we have those, we can add them together in order to have our final answer. So e to the negative 2t, c1, actually, hold on. You know what? Let's just copy it, Don't have to, this is the magic of the technology, so we can just copy. So that is the first part of this, which corresponds to YC. Now for the YP, we do have A and B here, and this is our answer. So AT plus B, so A is 9 over 20, T minus 9 over 100, which is the B. That is the answer. So next question. 9 prime prime plus 6y prime plus 9y equals 6 such t. Y of 0 equals 0, y prime of 0 equals 1. All right. So in here, we're actually going to be using something called the Laplace transform, which we've done in the question, right? We've dedicated like 30 questions, was it, for the Laplace transform? So again, the Laplace of y prime, y first. So Laplace of y is just big Y. The Laplace of y prime, this is y of s. Okay, so y of t, then y of s. The Laplace of y prime is negative y of 0 plus sy of s. You can see that? You can see that. Then the Laplace of y prime prime is negative y of 0 minus sy prime. Was it? No, 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 sorry. Negative y prime 0 minus sy of 0 plus s squared y of s. There we go. So now we have this entire thing. The Laplace of this is the Laplace of a sinh, as we've discussed, is 1 sinh t, 1 over s squared minus 1. Okay, so let's continue. So y prime prime, as we've discussed, is negative y prime of 0 minus sy of 0 plus s squared y of s. 6y prime is 6 times this, so uh, negative 6 y of 0 plus 6s y of s. And then 9y, so plus 9y of s equals 6 over s squared minus 1. Alright. Y prime of 0 is 1, so that's just negative 1. This is 0, this is 0, and this is s squared plus 6s plus 9 y of s equals 6 over s minus 1 squared. Squared minus 1. Okay, isolate this term, so add 1 to the other side. Okay, so this is 6 plus s squared minus 1, so that's going to be s squared plus 5. And here on the other side. So now y of s is s squared plus 5 on top. Then s plus 1, s minus 1, we can do that. Over, this is s plus 3 quantity squared. Okay, so solving this is very difficult. So you just have to take my word on this one. This is negative 3/4 over s plus 1 plus 3/16. Hold on, let me just check my notes. 3/16 over s minus 1 minus 107 over 48 over s plus 3 plus 7 over 4 over s plus 3 quantity squared. The notes I do recall, yeah. So I'll just zoom in here. Hope you can see it. This, don't just ignore that. This is the solution for that, which includes a lot of mathematics that I don't want to show on camera because I might go insane if I show all of it. So what we can do instead is just trust me on this one. Trust me that it's correct. If it's not correct, it's a bit difficult to accept. But whatever the case, the problem, and it's just gonna be the coefficients that's incorrect in that case. So now that we have that, this is frequency domain Laplace transform. Let's put it back in time domain, inverse Laplace transform. So this is e to the negative t with 3 negative 3 over 4 as the coefficient. This is e to the t with 3 over 16 as its coefficient. This is e to the negative 3t with 107 over 48 as its coefficient. And this is mhm, a bit more involved. But it is 7 over 4t e to the negative 3t as a coefficient. You can even test it because this is the derivative of 1 over s plus 3, and then there's a negative sign, so it's a positive. So that is the answer. Yeah, that is indeed the why. Pay no attention to the coefficients, they might be wrong. Right? So for question number 96, I have some word problems. So this spices up yeah, spices up the 100 integrals quiz. A lake has a carrying capacity of 300,000 fish. At the start of an experiment, 1,000 fish were released. 6 months later, 4,250 fish were spotted. Question. A year after the start of the experiment, how many fish are there? Another question. Similarly, what is the growth rate a year after the experiment? And another, how long from the start of the experiment until the lake reaches half capacity? So this is a logistics equation. The adept among you, such as engineers or engineering students who are in like what was it? Quiz B teams, I guess, would already know this method by heart using your calculators. But we're going to be using our we're going to be deriving how it is how it is solved. So this is the logistics equation or logistic growth. Oh, my camera's blocking it. So it's just the logistics growth. What is logistic growth? We have exponential growth, something like that. So it is growth without limitation. So it just expands and expands and expands. Something that doubles in size every time step is exponential growth. So that would be exponential growth. The differential equation for that is dp over dt equals kp. So this just means that the growth of your population is dependent on the population itself. So if you have 10 units or 10 people, your growth would be 10k. So k would be a constant. So if it was 1,000, it would still be 1,000k. So something like that. And what you would do here is you would solve this differential equation. But this is exponential growth. We need logistic growth. What is the difference? Sorry. In logistic growth, we have to consider the maximum, the carrying capacity. All right. We want the growth to stagnate if it gets close to the maximum population. So this can be solved, by multiplying m minus p right here. So this term actually it encourages growth your if your population is low, but it discourages growth when your population reaches m. So for if this is m, to m minus m, that's going to be zero. So your population growth is zero. So no new organisms are no new net organisms are born or die. They still get born and die, but they won't grow after that, the population. So we need to solve this differential equation. First, let's just write dp over dt as p prime. And then kpm minus kp squared. Let's put kpm on one side. So p prime equals k. Let's put m here and then p. Oh, no, equals minus equals negative kp squared. This is Bernoulli, as we've discussed earlier. So we need to multiply p negative 2, then minus p prime, sorry, k m p negative 1 equals negative k p, okay, just k, negative k. All right, so now we substitute. So p to the negative 1 equals v, and p negative 2, negative, what? Uh, see where I got wrong. Okay, so yeah, I got confused. So negative p to the negative 2, and then p prime equals v prime. This is positive, so we just put negative v prime here, minus k m, and then that's v equals negative k. V plus k m v equals k. So now, this is linear, v prime. So we use the integrating factor method. So km, and then what is this in response to? T. Yeah, t. Because this is all in respect to t, right? Because time. Okay? So this e to the kmt. So we just put ve to the kmt equals integral ke to the kmt. All right. So this integral is 1 over m. Huh, that's, hold on, kp squared. That doesn't make sense, right? Hang on. All right, so 1 over m, as we have discussed, e to the kmt plus c, and v e to the kmt. Now let's divide by this so we can isolate v here. 1 over m remains the c e to the negative kmt. V again is, let's see here. Ah, yes, 1 over p. And p is the population. So to find the population, we got p equals 1 over m plus c e to the negative kmt. We multiply by m, we get m over 1 plus, since c is just an arbitrary constant, that's just c, e to the negative kmt. That is the formula of population growth. From there, we can try finding the, what is it? The population. A year after the start of the experiment, how many fish are there? So at the start of the experiment, 1,000 fish. All right, let's copy this question right here. Ayan. Yeah. So P of 0, which is the, uh, this is in respect to times, since exponential growth or logistic growth depends on time, right? P of 0 is, it's not, there we go. P of 0 is 1,000. And then 6 months later, or P of 6. So each unit is, each unit T is months. Okay. So this is 4 to 50. We want a year after. So a year is 12 months. So we need P of 12. We have this already. So we can plug in some numbers. We need C. All right. So how can we find C? First, you can plug in the 1,000 here and the one there, but let's try finding C. Uh, actually, no. Okay, so oh, I'm going to find C anyway. Yeah, so P of Z at T equals 0, we have 1,000 fish. Here, this is M, so the maximum is 300,000 over 1 plus, we don't know C, e to the K we don't know. So K M is 300,000. Uh-huh. Then multiplied by T, which is 0. So this is e to the 0. So this is just 1. So 300,000 over 1 plus C. Okay. Try to solve for that. So 1 plus C equals 300,000 over 1,000. Divide. We get C is 299. All right. We now have C. We just need K, which is a bit more difficult. P of 6 is 300,000 again over 1 plus C, or C is not 199. C e to the negative K times 300,000 times 6. At this point, I don't think we can do that by hand because it's lateral logarithm and there's 300,000 and whatnot. So we're going to be using the calculator. Just use any calculator of your choice. But to simplify this so it's easier for a calculator to solve, let's try to isolate K. So first, this is for 250, we know that. Okay, so first we get, okay, K. So we multiply this, we swap this. So 300,000 over 4,250 equals 1 plus 299 e to the negative k times 1.8 million. Yeah. So now we subtract by 1, so negative 1 plus. Then we divide by 299. So, and then we apply the natural logarithm. There we go. All right, so let's move this. Let's just move all of this. Yeah, and there we go. To find k, we need to divide by 1.8 million. 6 times 300,000 is 1.8 million. And then that's still negative k, so we have to multiply by negative 1. So that's going to be your k. You can solve that using a calculator. The value we found is 8.099 times 10 to the negative 7. K is K in units is fish. So we multiply by fish per second. This is seconds per fish. Why? Because its companions is KMT. M is fish and time is in second. Oh, sorry. So it's actually invert. So it's hertz per fish, I guess. That's a weird unit, but 1 over fish second. So that's the unit, but honestly, you don't need the unit. So now P of 12 is 300,000 over 1 plus 299 e to the negative 8.099 times 10 to the negative 7 times 300,000 times 12, that's 6, is 17,446 fish. That is A done. That is question A done. Question B is, what is the growth rate a year after the experiment? This is very easy. We just have to take this, the original dp equals kp m minus p. So dp or dt equals kp m minus p. We need to know k, and we already know k is 8.099 less than negative 7. So that's it. 8.99 times 10 to the negative 7 inverse fish second times p, which is our population. Uh, it says here we need the growth rate a year after the experiment. So this is 17,446. Yes. 17,446. Yeah. 4 to times the maximum minus 7 minus 17,446. Multiplying all this together, we get 3,992. The unit here is P is fish, and this is also fish. So this is fish squared. So the unit is fish over second. So fish per second. So 3992, around 3992 fish per second. Okay, sometimes unit analysis is also good. Now, how long from the start of the experiment till the lake reaches half capacity? So we need P of t such that the population is 150,000. Again, we just put the formula. So P equals M over 1 plus C e to the negative kmt. We know C, we know K. So I got tired of writing that. But C and K. C is 299 and K is 8.099 times 10 to the negative 7. 1 over fish second. Yeah. Just believe it. Just believe it. Yeah. And C is unitless, so there's that, I guess. Right. So now uh we need to format this. Just write it down. Let's just write it down now. Negative 8.0997 times 300,000 t. Yeah, we need to find t in this point. So yeah, we need 150,000. So now to find t, we can insert this in the calculator. But again, there is a calculator technique for here. T is negative 1 over 8.099 times 10 to the negative 7 times 300,000 fish. Natural logarithm of 1 over 299 times 300,000 over 150,000 minus 1. This is around 23.46 months. So around 2 years. So in summary, question A is 17,446 fish. B is, did I say fish per second? It's fish per month. I I just realized that I said fish per second. That's so fast. Fish month. Okay. This is fish per month. Okay. I apologize for that. But it's fish per month because fish don't grow that fast. I don't think I know fish that grow that fast, but and for C is 23.46 months, which is approximately 1 year, 11 months, 13 days. You need to wait a long time. Question number 97. A 60-liter capacity vat has 70% alcohol by volume and water. At the start, there is a total of 10-liter solution. Pure water is poured into the vat at a rate of 10 liters per minute, and the solution is being drained at a rate of 5 liters per minute simultaneously. After 4 minutes, what is the percentage of alcohol in the vat? And both the draining and the pouring stops when the vat is full. What is the percentage of the alcohol then? Okay, so this is a mixture problem, and the differential equation for this is dA over dt, A for alcohol, is A going in minus A going out. So we need to figure out what's going in and what's going out. Okay, what is going in? Well, the alcohol going in is nothing because it's pure water that's going in. So there's no alcohol going in. So the only alcohol that is going out. So what is the alcohol going out? First, we can do what we can do here is the general formula, which is there's the alcohol concentration. So the alcohol concentration is in uh, liters alcohol per, is this correct? Liters alcohol per liter water, or no? Yeah. So the concentration, liter alcohol per liter water, we multiply that by liter water or liter mixture actually per minute. Yeah. Liter water, liter mixture. Yeah. Something like that. Or maybe it's for something. Anyway, that's the equation that we want. So this cancels out somehow, and we get liter alcohol per minute. So that's what we want. So the alcohol going out is, well, uh A of T, which is the amount of alcohol in the vat already in that unit time. Divided by the liter of water, how much water is in here. So pure water is being poured in the vat, 10 liters per minute, and it's being drained uh, 5 uh, being drained at a rate of 5 liters per minute simultaneously. Is that correct? No, no, no. Six. No, this is correct. Incorrect. Okay. So there's 60 liters initially, and then 5 liters net is being added. So it's 5. This is wrong. Yeah. Yeah. Okay. This is a very difficult problem. I'm gonna whip out the calculator in this one. I might be wrong. And then we multiply by the liter mixture per minute. Wait, liter water. Oh, yeah, the liter that is going is going out per minute. Sorry. This is concentration. This is the pour, or the pour rate. This is the rate at which it goes out. So the rate at which it goes out is 5 liters per minute. Or five. Just five. So let's rearrange. dA over dt is it 60 liters? So there's 10 liters here. Yeah, I might be wrong there. But we'll not be wrong here. So A over 5, we can divide this by 5. So D plus 12 now. Okay. We can put A on the other side. So dA over A. Uh, we can put dt, negative dt over D plus 12. It's just natural logarithm. Is that what I did? We do natural logarithm here. So ln of A is negative ln of T plus C. And then we raise e to both sides. We get A equals e to the this. So this is T plus 12 to the negative 1, or 1 over T plus 12. Plus, and then e times e to the C, which is just a constant. So we just multiply it by C. Now from here, we can draw from the original problem. At start, so A of 0, this is a 60-liter vat with 70% of it being alcohol. So that's going to be 42 liters. So this is 42. And this is T equals 0, so C equals C over 12. C then is 504. So A is 504 over T plus 12. Let me just double check if I didn't do anything wrong. 60 liters. Why not 10 liters? I might have read it wrong. Anyway, so now that we know all this, we know the equation now. After 4 minutes, what is the percentage of the alcohol in vat? We can glean from here what the percentage of alcohol is. So A of uh oh, no, hold on. there is 10-liter solution. That's why there is this 10. The capacity is 60 liters. So let me just uh this instead of 12, this becomes 2, so not much changes. Sorry, I forgot. Yeah, this is going to be a mistake in the exams. I will do. Glad I don't take differential equations anymore. So instead of 12, it's 2. So instead of c over 12, it's c over 2. So c is 84. All right, I made a mistake. Oh no, no one would take me seriously. But yeah, 42 liters here. So 2 here. Damn. And this is 84. There we go. So 84, let me leave this again for, wait. Oh no, not 60 liters because we haven't filled the thing yet. So it's just 10 liters, which is 7. Okay. Right, let's get back on track. This is 7. Oh no, because 7 is C over 2. So not this one. Oop. C is 14. There we go. Now we're on the right track. So 4 is 14 over 4 plus 2, which is 2.33 liters. How much of water is that? So V uh V of T, or the amount of water in there, is 10 liters at the start, not 60 as I've initially guessed, plus 5T, which is 5 liters times the amount of time. So T becomes, T is 4, so 10 plus 20 is 30. So it's 30 liters, uh, yes, 30 total? I don't know, 30 liters overall. Yeah, so, yeah, this is mix. So there's a lot of mistakes. Let me rephrase to it again. So there's 30 here now. So V4 is 30. All right. So we need percentage. So percentage is gonna be A4 over V of 4, which is 2.33 liters over 30 liters. That is going to be around 7.78%. How about when it is full? So when is it full? So this is where the 60 now comes in. So this needs to be 60, so t needs to be 10. So this is at t equals 10. So we just need ta of 10, which is going to be 14 over 10 plus 2 is 1.167 liters. And knowing that it's 60 liters, the percentage for that is going to be 1.94%. That is 1.167 divided by 60 liters. Now, that's the answers. Okay, so let's recap so there's no more confusion. I'll put that thing right. Uh, So first of all, the formula is A in minus A out. Okay? The formula for alcohol is usually this. So it's liter alcohol over liter mixture times liter mixture over minute. So this is the outflow rate or pour rate. This could also be inflow rate. So this is the concentration of either the thing that is going out or in or out. So you need to be careful in which this is. 16 liters is the capacity. So I initially thought it was the uh, again, it's been a long time. So 10 liters solution. This is where it's the initial condition, and this is 70% alcohol by volume. All right, so that's going to be useful here. So in here, the alcohol going in is 0 because it's just pure water. Alcohol going out is this formula. So for A of T, which is the alcohol in that vat at that time, over 10 plus 5T, which is the volume of the mixture. All right, and then times 5, which is 5 liters per minute, which is how much is going out here. Okay, why 10 plus 5T? Because 5 times T, that is the net inflow or the net flow, all right, is positive 5T. Mixture is going up at 5 liters per minute. Okay, so just simplify and uh, find the DE for that, and then solve for the differential equation like this, and then we find the initial conditions for C. We need A of 0, which we already have, which is this. So it's 14. So C is 14. All right. So A of 0 is 10 liters times 70%, so 7 liters. And A of 0 is C over 2. So that's why C is 14. Now, for A of 4, we just find 14 over 4 plus 2, so 2.33 liters. V of 4 is just 30 liters, given by this formula. So 10 liters the initial plus 5 times the amount of time that has elapsed. So the percentage is just A4 over V of 4. Next is when it's full, which is 60 liters, which is where it comes in. And then T equals 10 for that. And then we just find the equation for 10. So now that is the answer. That's the answer. These are the answers. 7.78% and 1.94%. Finally, next question. Sorry about uh the confusion. Yeah. But at the end of the day, it's still correct. Find the set of curves for which all horizontal parabola with its vertex at the origin is orthogonal to each curve. What does that mean? So, all right. So, the setup here is uh we have all of the horizontal parabolae, right? So it just means that it is of this shape, either going up or it is going down. What are the set of curves for which every point they meet, it is orthogonal or right angle. So something like that maybe, and then maybe something like that. So all the um, intersectional and intersection points, all the curves is orthogonal to all the family of curves of the parabola. What we first do is identify the equation of all the parabolae. So that's going to be y minus k for a, y minus k equals x minus h quantity squared. This is the y coordinate of the vertex, the k. H is the x coordinate of the vertex. So vertex is h and then k. Vertex is at the origin, which is 0, 0. So k and h is 0 now. So for a, then y equals x squared. A is I think it is the eccentricity, or how steep it is. And it's actually the focus. So A is the unit for the focus. So what you need to do. So in here, we need to find the differential equation of this. By that, I mean we need to eliminate this y here. So we need to find the differential equation without y. So we need to do that by differentiating, of course. So the derivative of this is 4a y prime. And then this is equal to x, since that is the derivative of x squared. No plus c in here because it's a derivative. Okay, so 4a here and here. So we can isolate 4a to get 2x over y prime. Okay, let's move that to the here. Now let's substitute it here. So instead of 4ay, it is 2x over y prime y equals x squared. Isolate y prime. y, sorry, 2xy equals x squared y prime. Then y prime equals 2y over x. So that's the differential equation for this. Now to find the orthogonal, find the set of curves for which all blah 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 is orthogonal to each curve. We need to find the orthogonal slope. The orthogonal slope is the negative reciprocal. So this is negative and then the reciprocal of this. That is That is uh, the orthogonal slope for a line, right? So negative reciprocal. So it's also the same in differential equations. So in here, we can multiply both sides by 2y, and then negative x here. Integrating, we get here y squared, we get here negative x squared over 2 plus c. Let's move this move x squared over 2 to the other side. There we go. Equals c. Multiplying both sides by 2, we get x squared plus 2y squared equals c is just an arbitrary constant, so it's just c. This is the family of curves for which all of this is orthogonal. So what is x squared plus 2y squared equals c? It's actually ellipses. So the family of curves orthogonal would look like ellipses, something like that. So all of those would be orthogonal, as is said. All right. So you can check in Desmos if that's true. And I think it is. Just set all c's as the same. Anyway, question number 99. 20 degrees coffee is put on a heater that is constantly at 150 degrees Celsius. After 1 minute, the temperature is recorded as 50 degrees Celsius. The temperature of liquid coffee obeys Newton's law of cooling, yet stops at 100 degrees Celsius, after which it boils to steam. What time does liquid coffee get to this point? Second scenario, after putting the boiling coffee in a 20-degree room, it cooled down from 100 to 80 in a minute. What time, from the start of putting the coffee in the room, does it reach 50 degrees Celsius? Newton's law of cooling is this. The change in temperature is related to the temperature, the contrast of the temperature and the ambient temperature, the object temperature and the ambient temperature. All right. So in the first scenario, the ambient temperature is 150 degrees Celsius. So that's going to be amp. There we go. There we go. So we can solve for t now by this is just a differential equation. So dt over t minus 150 equals k dt. Okay, this is ln of t minus 150 equals kt plus c. Raising e to both sides gets us t minus 150 equals ce to the kt. T then is 150 plus c e to the kt. What is k? That's what we need to know. This is t of t since it is relative to time. So t of 0 is uh, after 1 minute. So it's actually t of 1. Sorry. The temperature is recorded as 50 degrees Celsius. 20-degree coffee is put on a heater. So actually 0 is better. So let's put that there. T0 is 20. It's also 150 plus c to the 0, so just c. And then this is 150 plus c e to the kt, so just k because t is 1 now. All right, so find c. C is just negative 130 as shown here algebraically. All right, so now that is negative 130, we can replace this. Now, we need the value of k. So 50 minus 150 over negative 130, then the natural logarithm of that would be the value of k. The value of k is negative 0.26. There we go. And I think it is inverse minutes. But it's just a constant, so what else, right? Now, we need this. So we need the temperature, we need the time at which it stops at 100 degrees Celsius. So 100 is 150 minus 130 e to the negative 0.26 t. We need to find t time. And luckily, I have already calculated. It is 3.68 minutes. All right. After putting boiling coffee in a 20 degrees Celsius room, so our boiling coffee means this is an entirely new scenario, so 100 degrees. And then the T ambient here is 20 degrees Celsius from the second question. It cooled down from 100 to 80 in a minute. So T1 is 80 degrees. What time from the start does it reach 50 degrees Celsius? So let's do that again. Uh, so T equals T amp plus CE to the KT. Right, T ambient is 20. And C is, we don't know. So CE to the KT. Now T of 0 is 100 degrees, is also 20 plus C. So C is 80. T of 1 is 80 degrees, is also 20 plus 80 e to the k times 1. K here is, actually I haven't calculated it yet. So I used a different method to take the book in the notebook. So let us solve for k. Uh, to find this algebraically, we get 80 minus 20 over 80 and then ln. So ln of 80 minus 20 over 80, that would be negative 0.29 inverse minutes. Now that we have that information, we can finally have T. So we know the temperature we need, which is 50, 50, 50 equals 20 plus 80 e to the negative 0.29 inverse minutes T. We just need to find T. And T is actually 3.41 minutes. Now, if you watched my previous video on this, on how to use your calculator, I think using Casio, but I don't have that Casio anymore. Uh, you can find other methods to find this, and you can try finding other methods in somewhere else. But this is the answer. All right. For question number 100. The spring force is described as F equals Ks, where K is the spring constant and S is the distance. Sorry, this should be displacement of the spring from its equilibrium position. A 98.1 Newton weight hangs on the spring, which can extend it by zero point 0.5 meters. The weight is lifted 1 meters above its equilibrium position, then is let go without providing additional velocity, producing an oscillation motion that does not decay. Use G equals 9.21 meters per second. Find the general solution, particular solution, period of the spring, and its position relative to its equilibrium position at t equals 3 seconds. So, what is the formula for this? Well, this is physics now, so we need to draw the model now. So we have a spring that with a weight extends by some point, because a spring that does not have a weight has a certain what do you call this, a certain length, and then if you put an object like this thing, it extends, right? It wants to extend because it is being acted upon by a weight, but it is being counteracted upon by the spring force. All right, so yeah, so that is it. But then there is another force that is acting on this. In equilibrium, it is doing nothing. It's just the weight and the spring force. As soon as you introduce additional movement through it, for example, maybe you lifted the spring and then you let it bounce like this, there is oscillation. So yes, there is the spring force. So let's spring, and then there's weight. There's also an additional force acting on that direction maybe. Uh, that is the decay factor, right? So the three forces acting on a spring when it is oscillating is the spring force plus the decay force, which tells it how it decays, plus the weight. All this must be zero. All right. So yeah, because it is in equilibrium. Yeah. All right. Now, the spring force is Ks. All right. S is the distance. So we can say that is x. The weight is mass times acceleration. All right. And we know the acceleration is 9.81 meters per second squared. But we also know this is m times x prime prime. Since acceleration is double derivative of distance with relation to time. The decay force is some factor d, so d for decay, and then x prime. All right, let's rearrange. Plus decay x prime, which is the decay factor, plus kx plus 0. This is an auxiliary. Uh, this is an auxiliary ODE, right? Here, the oscillating motion, the oscillating motion does not decay. So the decay factor that then is 0. There is no decay force going here. Actually, the decay force is very weird to think about. So it's just nothing about it. But what I mean by decay is when it oscillates, there is uh there's this force that stabilizes it, right? In the real world, it's like air resistance, it's the spring, it's like friction and whatnot. So it really decays in the real world. In this example, it does not decay. So those not happening, right? No heat, no air resistance, just pure spring. So this is our formula now. A 98.1 Newton weight hangs on the spring, which can extend it by zero point 0.5 meters. We need the spring constant, which is K. Where can we find the spring constant? Well, actually, a spring constant, so this is F equals Ks. F equals Ks, right? S is the from the equilibrium position, and then you added the weight. So extend the weight by zero point 0.5 meters. 0.5 meters. It produces a force of 98.1. Oh, uh, 98.1 newtons. Okay. Why 98.1 newtons again? So this is the weight in equilibrium, which it doesn't move. This is the diagram. So weight goes down, but spring goes up, and they equalize each other. It's called static equilibrium. Static equilibrium, nothing moves. So in the scenario where nothing moves, spring force and weight must be equal. So the force here is 98.1 as well. And multiplying by 2, we get 196.2 newtons per meter. That is the spring constant. So we can bring it here. The mass is, actually, we don't know the mass. But that is easy because we already have the Newton. So 98.1 Newton. That means we divide by 9.81 to find the mass. So it's 10 kilograms. So it's 10 x prime prime plus 196.2 x equals 0. The auxiliary, uh, so let's not use m. Let's use like r squared. So 10r squared plus 196.2 equals 0. So r squared equals negative 119.62. R is plus minus 4.43 I. So 4.43 is not exact. Alright. So it's just that. It's Is a very, what do you call this? Irrational number, you know. So since there's no real, so we don't have E, we just have cosine and sine. So cosine, C1 cosine of 4.43t plus C2 sine of 4.43t. So this is our x. This is x of t, right? So actually, this is our first, this is general solution. What is the particular solution? All right. At zero, the weight is lifted 1 meters above. So x of zero equals 1 meter. So like 1 meter. All right. So x of zero, so sine of zero is zero. Cosine of zero is one. So this is just C1. C1 equals one, right? And then what is written here? Then is let go without providing additional velocity. What does that mean? It means that x prime of 0 is 0. So when let go, at that instant there is no velocity. It only it only has velocity when it is affected by gravity. So that's when it goes down. But it has no initial velocity, so it is 0. Now, we need x prime here. So this is going to be negative 4.43 C1 cosine of sine, sorry, 4.43 T plus C2, 4.43. Honestly, we don't even need to, but you know, completeness. Cosine of 4.43 T. Okay. Now, this is now 0. This is just C2. So 4.43 C2 times 1 equals 0. So just C2 equals 0. So now x, the particular solution is cosine of 4.43t. Now, next question is to find the period of the spring, find its frequency as well. So the motion of uh, the the object is going to look like this. So its cosine, so it starts at 1. So like 1. And then it goes there, 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 there. Okay. So the formula for the sine for a sinusoid like this is cosine of 2 pi f of t. F being the frequency, 2 pi f being the radian frequency. All right. So now, what do we do here? We just need the period. Okay, we can glean the frequency here because 2 pi f and 4.43 is should be equal to each other. So let's first find the frequency. 2 pi f is 4.43. Uh, yeah, 4.43. So f, or hertz actually. So f is 4.43 hertz over 2 pi. This is cyclic frequency. This is a radian frequency. The period should be calculated. 0.705 hertz. That's the frequency. The period, or P, is just 1 over the frequency. Actually, period is more T instead of P. So period is 1.418 seconds. So it takes 1.48 seconds to go back from top and then go back to top. So it takes 1.41. So the temporal distance between this is from, yeah, 1.418 seconds. D, find its position relative to equilibrium at t equals 3. So this is just a matter of substituting. So 4.43 times 3. 4.43 4.43 actually is radian hertz. So I neglected to mention it here. It's radian hertz. So rad hertz. So where does rad go? Because 2 pi is actually in radians, so that cancels out. So it becomes normal hertz. So times next 3. 3 something, a 3 radian second, something like that, or 3 inverse radian second, some weird thing like that, you know. So 3 is, if we go there, that's it's gonna be 0.75 meters. So in here, it's like maybe here. That's 3 seconds. Ah, no, it repeats. So it goes back there, maybe somewhere in here. That's 3 seconds. There we go. And that is the 100th question. And there we go. We have completed 100 questions yet again for the 100 integrals. Let me show you my setup. So it's not the best setup. I mean, there's the keyboards right there and the drawing pad there. And I'm recording on OBS on OneNote and whatnot. And the notebook is here, calculator, and the figurine just to keep me sane. And yeah, so to be honest, this 100 integrals part 2 has been in the making ever since I was in like first year. I'm now in third year, so there's that. So I guess it took me a long time to, there's my other figurines. So it took me a long time to make this. Partially because I'm lazy. Also partially because, some school problems like projects, ACADS, and whatnot. I'm glad to say that I'm not failing. Or maybe I am proud of what I have been able to accomplish in school and on this channel. So there we go, I guess. So, and yeah, 100 integrals part 2. Will I do another or part 3 of the 100 integrals? Maybe when I'm graduated, but I'm not a graduate yet. And integrals, it's now, I mean, I don't study integrals anymore. I don't study differential equations anymore. Again, this was made when I was first year, second year. So I was studying differential equations. Then, now I'm not. And this seems redundant because who is going to benefit it? I was supposed to send this to my classmates, but now they're not studying differential equations anymore. I guess I can send it to like lower years, maybe. And maybe you can learn from this too, So, yeah, a little bit of, words from me, as a normal guy. So, yeah. This is inspired by Black Pen, Red Pen's 100 Integrals, And yeah. If you've noticed, this is noticeably better than the 100 Integrals Part 1. And that is partially because I found the new software, like OneNote, which I have been using ever since that. This is my second year, so yeah. So uh, now that 100 questions, not integrals anymore because half of them is not even an integral. So we're going to be ending this on an integral. And there we go, ladies and gentlemen. After Laplace transforms, inverse Laplace transforms, ordinary differential equations, and its applications, we have come back to the title of this video, an integral. Oh my god. So I've picked a special integral. I was debating on what integral I should be putting here. Should I put a meme? Should I put a joke, maybe an inside joke? But I wanted to put something that's really out there for the final integral. The integral from 0 to 1, ln of 1 minus x over x dx. At first glance, if that 1 wasn't there and that negative was a positive, I would be done right now. But it isn't. And that is not integrable easily, right? ln of 1 minus x over x, that doesn't have an elementary antiderivative. So what we have to do is to step away from that, and I will have to introduce to you power series. Specifically, something you may know from high school, which is the infinite geometric series. So this is 1 plus x squared plus x cubed plus that. We all know this is 1 over 1 minus x, all right? Because the original version is a plus ar plus ar. So a over 1 minus r. So it's just 1 over 1 minus x. Yeah. How can we prove this? Let's say this is s sum, all right? If we multiply it by, say, x, so xs, this is x plus x squared plus x cubed plus that, and we wouldn't run out of terms until like infinity and whatnot. Because infinity is weird, all right? So what if we subtracted, so s minus xs, this would cancel, this would cancel, this would cancel, all of that would cancel except the 1. So now s 1 minus x equals 1, s equals 1 minus 1 minus 1 over 1 minus x. So normally, x has to, absolute value of x has to be less than 1. Otherwise, we get 1 over 0 or really weird things like, you know, uh, like this, for example. So 1 plus 2 squared plus 2 cubed. Conventional wisdom dictates that this would be divergent. But if you use this, the answer would be negative 1. Notice how I said normally this would be divergent. But if you continued it analytically, analytic continuation, negative 1 would make sense here. How that works, I don't know. I am an undergrad. So just trust me that 1 over 1 minus x works for any x except 1. Um, less than 1, greater than negative 1, yes, it works normally. And for the other one, it works because of something called analytic continuation. And I think that's the foundation of something called p-adic numbers. You can research that if you want. P-adics and adics for that. So let's get off that the train and just focus on this. Okay, so we need the bounds to be from 0 to 1. And from the looks of it, there's a 1 in here. That's a bit weird. However, this is just a limit, all right? So this can be the limit as x goes to 1, all right? So we're not doing anything wrong here from the bounds. And if even we exceeded the bounds anyway, we would just say analytic continuation to 1. Now, next. So, we integrate then this power series. We integrate both sides with respect to x. And the result might shock you. Okay, so the integral of this. On the left-hand side, this is x to the n plus 1 over n plus 1. Again, the sum. On the right, this is negative ln of 1 minus x. Right? Now, plus c, we disregard it for now. We will look into plus c. All right? Come. Wait, hold on. Now, what can we do here? Well, we know we have ln of 1 minus x. So, to have ln of 1 minus x, that's just negative the integral from n equals 0 to infinity of x to the n plus 1 over n plus 1. Right? Right. So, from here we can substitute ln of 1 minus x to here. The absolute value doesn't matter because it's just from 0 to 1, so no negatives here. Sorry. Uh, Integral from 0 to 1 of, oh, well, 1 over x since the x is in the denominator. And then n equals 0 to infinity, x to the n plus 1 over n plus 1. This is a method that's uses power series in order to solve hard integrals like this one. Sometimes this is the only method. Negative, I forgot. So sorry. So negative, and then from 0 to 1, We multiply 1 over x by this. This becomes x to the n due to the loss of exponents over n plus 1. Integrate. So we get negative x to the n plus 1 over summation of summation again, and then n plus 1 quantity squared from 0 to 1. All right. So substitute like normal. So negative sum of n equals 0 to infinity. Oh, by the way, I think we swapped we inadvertently swapped the integral and the summation. We can do that because we are expecting a finite sum for here and for here. So we're expecting finite sum, not infinity, which is usually what we want. So I'm just doing hand wavy here. Just trust the process sometimes. So if x is 1, so just 1 to the n plus 1, it's just 1. If this is 0, this would just be 0. So we don't have to worry about that. So 1 over n plus 1 quantity squared. Okay. Now, let's adjust it so that this is just n the bottom. We do that by adjusting the start. So we start at 1. So instead of 0, we start at 1 and it has the same effect. And since it is infinity, it doesn't matter really. So now, what does this mean? Well, 1 over 1 plus 1 over 4 plus 1 over 9 plus 1 over 16. This is zeta 2. Oh, not zeta. Yeah, I forgot how to, yeah, something like that. Zeta of 2, which is the Riemann zeta function. And actually, this is the Bessel problem. Just that now we have a negative here. All right. The answer for the Bessel problem, I don't want to get into specifics of it. Essentially, and I think of this, pi squared over 6. How beautiful is that? So let me recap. This, 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 this ln, it just has natural logarithm. Somehow the answer is pi squared over 6 on the negative of it at least. And that is question number 101. Thank you for watching, everybody. If you've reached this part or just skipped here, I appreciate your view. And, I appreciate you going on my journey to do this 100 integral. This 100 integrals has been in the works for like years, just a year. This has been in the work for a year, and seeing it being completed is just it makes me proud. And for those of you who have been in my channel for a long time, you've seen me do electrostatics, like circuit analysis, and some calculus stuff. See me do the DE series, the integral series. Uh, Probably you watched that because you had an exam, and I provided a source, and whatnot. So thank you for all that. And what's next? Is 100 integrals over? Is the integral series over? For now, yes. I won't be doing any integrals, unfortunately. I don't think there's anything new here. But what comes next? I am planning on a new series related to electronics. So you have that to look forward to. Of course, that will come when I've already finished a lot of my responsibilities. But I I really want to do that next, right? For those of you watching, I will now have a separate chat for those of you watching. For my friends, thank you for inspiring me, of course. For my teachers, of course, thank you for inspiring me to become a YouTuber in math and whatnot. There's this one teacher I was inspired by who did a YouTube channel. I said I should make that as well. I should make an integral, and I did. And of course, Black Pen Red Pen, the YouTuber who this series uh is a copycat essentially too. Thank you for that. Thank you for the idea, I guess. I just expanded upon it. Uh, Adobe Photoshop, thank you for doing the first half of this, the 100 integrals one. But now OneNote is here, so thank you for that. For my friends in college, thank you. Uh, Thank you for listening here. For my some of my friends in college who've given me the opportunity to participate in quiz bees and whatnot. Thank you for giving me the opportunity for that. And to me, uh, you might be watching this in the future, so you know, tell me what you've done. Maybe. Wish you good luck. Wish you all good luck as well. And I will see you in the next video.